Hey everyone, and welcome to the Applied Data Science with Python course. So every time you shop online, watch a video, book a cab, or use a banking app, data is being created. But the real power is not just in collecting data. It's in understanding it, cleaning it, finding patterns, and using it to make smarter decisions. And that is exactly what this course will help you learn. In this course, we will take you step by step into the world of data science using Python. So you don't need to feel overwhelmed by big terms like NumPy, Pandas, visualization, or statistics. Here, we will break everything down in a simple and a practical way. Here's what we will be covering. First, we will understand what data science is, why it matters, and how Python is used to solve real-world data problems. Then, we will explore the complete data science workflow from understanding a problem and collecting it to cleaning, analyzing, visualizing, and preparing it for machine learning. Next, we will get into important Python libraries like NumPy, where you will learn how to work with arrays, numbers, matrices, and even calculations. After that, we will move to Pandas, one of the most useful tools in data science. You will learn how to work with series and data frames, filter data, sort data, and handle missing values, and clean messy datasets. We will also cover practical data operations like working with datetime values, text data, summary statistics, and data exploration. Then comes one of the most exciting parts, data visualization. Here you will learn how to create charts and graphs using Matplotlib, Seaborn and Plotly so you can understand data visually and present insights clearly. We will also touch on important math and statistics concepts like distributions, outliers, and linear algebra, which form the base of many data science and machine learning techniques. Finally, we will see how all of these skills come together to prepare data for real-world analysis and future machine learning models. By the end of this course, you will understand how to take raw data, clean it, explore it, visualize it, and use it to find meaningful insights in Python. So let's get started and learn how data science actually works in the real world. Also, if you're ready to take your skills in Python and data science to the next level, check out Simplilearn's Data Science with Python full course. So this course is perfect for anyone who wants to master Python programming for data analysis, visualization, and machine learning. So you will learn how to work with key Python libraries like NumPy, Pandas, and Matplotlib for data wrangling and analysis. You will be diving deep into data visualization, feature engineering, and statistical methods that are crucial in the field of data science. Plus, you will get a hands-on experience through real-world projects like sales analysis, marketing campaign analysis, and more. Upon completing the course, you will earn a course completion certificate from Simplilearn, which can boost your career and showcase your new skills to the employers. So check the description below for the link and start your data science journey today with Simplilearn. Before we get started, here's a quick quiz for you. Which Python library is used mainly to work with tables, rows, columns, and structured data? Is it A, NumPy, B, Pandas, C, Matplotlib, or is it D, Plotly? Please drop your answers in the comments below and let's get started.
Okay, so we're just on lesson one, just going to get basically a roadmap of what we're going to study. So this should just highlight different topics. I'll just quickly touch on what we intend to cover over our next kind of 12 sessions that we have dedicated to data science. So the first topic which we will study tonight is really going to be lesson two, but here it's kind of topic number one, which is our introduction to data science, right? So just focusing on some foundations, like some definitions. What is data science? What packages are going to help us in data science? And just quick overview of those before we dive into them further. And then get an idea of the process that we would use in solving data science problems. Like what kind of process will we follow typically? I think that'll be a big highlight is that process because we will follow that process as we dive into more data science problems. So that's going to be in the intro. That will segue us into the next couple of lessons, which will cover some really foundational packages for us inside of Python, namely the NumPy package and the Pandas package. So NumPy we're going to get to today, and that's going to cover basically the usage of NumPy in data science, why we use it, some syntax, some examples, some practice with it. So we'll get familiar with NumPy. And then that will lead us into the next lesson, which will be on Pandas. So that's another Python package that we will study and get a lot of practice with. Yeah, Pandas is going to be incredibly useful for us because as the name suggests, like data science, where we're going to be working with data, most of it's going to be structured, and Pandas is going to help us work with that structured data and explore it and slice and dice it and do a lot of fun things with it. So Pandas, if you're a big like Excel fan, Microsoft Excel, and you work a lot with spreadsheets, there's a lot of similar functionality that Pandas kind of provides, but we're going to be doing it in code, right? So it's going to be pretty exciting there. So we'll do NumPy, we'll do Pandas. That will segue us into how do we kind of tell a story with our data. So, we will be talking about data visualization, for example. That's one big way to tell a story, which is to focus on drawing graphs, building out plots. That's always important. It's useful in two ways. One, so we can get a handle on what the data actually means. We can visualize it. That's helpful. And two, it helps us externally tell a story, right? So if you wanted to share any insights, usually a picture is pretty powerful. And so drawing those graphs going to be incredibly useful. So we're going to study some different code and different packages that can help us build visualizations of our data. So that's going to be pretty useful. And that's in lesson 5. Then following that will be some math and stats fundamentals. So we can't get away from the fact that there is some math and stats involved in data science, of course. So mainly just want to get some background on it. I don't mean to scare anyone and think that we need to be experts on math and statistics. That's not really the case. But there are some basic concepts that I think we should be aware of, and I'll do my best to break those down. I have a math background. I went to graduate school for math. I studied math in undergrad, so I like to think I have a good grasp on it and can help you guys too. It's again not the intention to be an expert in math, but just to go over the basic concepts we would need to be able to work with our data, right? So there will be some basic math and stats fundamentals we'll cover because it's necessary. You can't get away from it when you're talking about data science. So we'll cover that. We'll also go into probability because we also will need to talk about how our data is distributed and a little bit about probability. Not too in depth, but just enough to cover the basics of what we would need to again describe like how data is distributed, what that means. So we'll look at some different distributions and kind of how to interpret those. That'll be more important for us than the nitty-gritty kind of math details, I think. Okay. Finally, we'll get into some interesting topics to round out our math and stats detour. So if you look back at this, we kind of take a little bit of a detour, and this will be lesson 6, 7, and 8. That will be a little bit of a detour in covering math and stats and probability, and then advanced stats, which really will cover hypothesis testing. So that'll be interesting. It'll give us a way to kind of think about how do we formalize doing things like A/B testing, or how do we formalize doing like a hypothesis test between like a control group and an experiment group. So how do we quantify that, which is an important aspect of data science and something that people usually care about, especially with products. When you're rolling out new features, usually you roll it out to a smaller group and compare it to kind of a baseline group, and you want to quantify those differences. So we'll talk about that in that advanced statistics lesson. Then we pivot to the last 2 lessons of the course, which will be, I think, are my 2 favorite, which will be getting us really doing a lot of data preparation for modeling. So we're not covering modeling in this course because that will be in the next one in machine learning. But lessons 9 and 10, which are here, data wrangling, feature engineering, will be incredibly useful for getting our data prepared for modeling. So we need to learn how to clean it up, how to slice and dice kind of raw data, how to create new features out of existing data, how to fill in missing values, how to do scaling, how to do grouping. Those are those kind of slice and dice operations. So a lot of things in those 2 lessons that will help us prepare our data for modeling. Okay, so that's kind of the gist of those last 2 lessons, just getting our data prepared and cleaned up, ready to be modeled off of. Okay, so if I were to summarize that, we have kind of our intro, which we'll cover today. NumPy we'll cover today. That's an important package that will help us work with our data. Pandas as well, that'll follow that. Then we'll go into building plots. Then we'll go into math and stats detour for a few lessons, and then finish up with getting our data, working with our data, right? Getting it prepared for modeling. So a lot of exciting topics. Hopefully you guys, feel excited about that too. A lot of really cool things that we'll cover. But that's kind of the roadmap. Okay, so we're moving on to lesson two. All right, so lesson two, our intro to data science. So we're going to get just some background on what data science is, what it is as a field, and then some of the again, some of the processes, some of the packages that we'll need, some of the tools that we'll need to work on data science. So by the end of this lesson, we want to be able to talk about data science in general, just define what it is and what we would be doing in data science. Like, what is, if you're a data scientist, what kind of things are you doing? Mainly want to focus on the process too. Like, what are the steps to solving problems systematically that we will end up following? Jabe, it's the ebooks. I think it's the ebooks. Oh, you may need to update your course. Okay. And then we'll take a look at so I was saying that we will basically go through the steps to solve problems. I want to definitely highlight that process. Then we want to look at some of the packages that are going to help us do different things in data science, like data analysis, data manipulation, data visualization. So what are some common packages in the Python ecosystem that we will use to accomplish data science? And then lastly, there's a description of some plots. I'm going to skip those because we're going to have a whole section on visualization where we'll go through those plots in more detail. But kind of briefly, I can show what those look like. But we have a whole section dedicated to building those plots, so I'm not concerned about going through them right now. But those are at the end of this lesson. Okay, so let's dive into it. So, what is data science? Okay, so what is data science? We had to put a definition to it. It is a multidisciplinary field that uses scientific methods, processes, algorithms, systems this is the big part of it, derive meaningful insights from structured and unstructured data. So that's the big part of it is obviously data is in the name, data science. So our goal with data science is to derive meaningful insights from data. And so that can involve many things. That can involve building models, which we will learn how to do later on when we get into machine learning. That can involve building out visualizations. That can involve doing hypothesis testing. That can involve many different things, but we're deriving some type of insight or finding out something interesting about our data that we have through different methods. So it's kind of, I always like to say it's the science of working with data, which is kind of a weird way of saying it because that's obviously the name data science, but it truly is the science of extracting insight from data is this field. And there's a lot involved in it that blends a lot of different disciplines together. It's why we say it's multidisciplinary because we kind of bring together multiple aspects of math and stats, computer science, domain expertise to be able to derive those insights. So there's there's ideas and concepts borrowed from science, like doing hypothesis testing. There's obviously math and stats, a lot borrowed from there. There's a lot borrowed from visualization and analysis that we use in data science, but we kind of blend that with technology, right? With computer science. So being able to use Python is a big deal. That will be our language of choice for doing anything data science. That's why we kind of reviewed it in the beginning. So we'll certainly use Python. We'll certainly use different tools within Python to process data. Those are data processing tools. So we kind of blend those together to form the field of data science. So those scientific methods, along with tools working with data from technology like Python, blend those together, we kind of get data science. So where do we see data science today? There's a lot of different applications, and we'll try to describe some of them to you, which is, for example, like wearable devices. So think about like Fitbits or Apple Watches. They're always crunching data from their sensors, right? So there's some type of biometrics that are captured and sent over the internet essentially to basically allow us to do some type of analysis or some type of derivation of insight from that data. And then we can kind of visualize that with some graphs or some meaningful metrics, so that the person wearing that device can make some sort of decision. So there's some type of insight derived, and usually some type of algorithm being applied to that. Maybe a model's being built working with the data that's captured from the wearable device, or we're just plotting that data, or we're summarizing it in some way, but making it really useful to the end user to make a decision off of. So we're deriving insights there, from all of the data collected in the wearable device. So that's kind of one application. Search engines use data science to personalize results or offer recommendations as people type in their queries. So essentially, like, you have suggestions, right? Like, and these could be based on your previous browser history, all kinds of data, like your cookies or your what's trending in the world, or like your region. Though you probably have noticed this, right? When you're searching on search engines, you get these suggestions. Those recommendations are kind of powered by data science, right? So data is going into that to derive some insight that, hey, this is what we should suggest, and that's it gets surfaced there. One of the things that we'll look into down the road when we get into machine learning, which is the next course after this, will be recommendation systems. So how do we actually build those models that do recommendation? But in order to build those, you really need data. So that's where we got to start, is working with data to get in a position to model off of it. Finance, we see usage of data. For instance, there could be like some type of model that's built to determine a loan decision. So there could be the application, and then there could be additional data that's gathered via the details in the application. And then that all that data can be brought together and kind of analyzed through the use of a model that could predict, yes, we should give this loan, or no, we should deny this loan. So again, you're deriving some type of insight from that data to make a decision, right? To make some sort of loan decision in finance. Or like we see a lot of fraud decisions made as well. Like, is this transaction fraud or not fraud? That's another big use case of data science. So based on the data of transactions, are they fraudulent or not fraudulent? Okay. A lot of other applications, those are just a few. And as we go along throughout this course, we'll really study a bunch more and get into some more use cases as we go along. This is just a preview. But what I want to go to next is kind of the process by which we attack data science problems. So we know that we should be deriving insights from data. That's what data science does. Okay. All right, let's talk about the process. Okay, so the process is outlined roughly here, but I'm going to take us through every single step. But if I had to break this down into basically a handful of key steps, it mostly starts at here, which is kind of initial problem formulation, which involves collecting data. So usually you have problem formulation. So you need to know, like, what are, do we want to build a recommendation system for movies? Do we want to figure out if transactions are fraud or not fraud? Like, we're coming up with some problem that we want to solve, and then going out and collecting data that might help us analyze that problem further. So we'll talk about that. Then comes the kind of data preparation phase, I would call it. So data prep, meaning that we are preparing our data for modeling, with that goal in mind. Is our goal is to actually build some sort of model to tell us something, to help us make a decision or derive some insight, right? And so we will do a couple steps. I'll describe what they mean in a moment, of doing some data preparation in order to get ready for modeling. Then comes the actual modeling phase. The actual modeling phase, which involves building, training, evaluating, all of that. And so then comes the modeling phase, and then comes the actual deployment of the model, meaning that we use it in the real world, to bring our insights into an actual system, integrated into actual system, so that those decisions can actually be made and used by an end user, let's say. I believe you can call a data science process even if no model is built. Step 4, 5. Um, you can, but so I think that's fair is to say like if even if you're not building a model, so you're thinking just steps 1, 2, 3, 4, or even just 1, 2, 3. I think that's fair, but most of the time in this course or in this program, we're really going to be building models. So I want us to have this in mind is like even if we stop here and don't do any model building, this is what we have our eyes to is the ability to model if we want to. Okay. But I think it's a fair point is that it could be, it's a fair point that you could just imagine getting your data together as really like kind of a data science process. Is feature engineering the feature that will use feature, I'm going to describe what feature engineering is in a moment. I'm going to go into that in further detail in the next couple of slides. So just hang on when I say feature engineering. We'll talk about it. I was thinking for A/B testing and probably there's no model. Would you call this a data science project? That's up for debate. A/B testing, sometimes that falls under analytics. Sometimes that falls under data science. We'll talk about doing A/B testing. So even when there is no model, so I think it's fair to say it's part of data science, which would kind of just be steps 1, 2, 3, 4. So yeah, I see where you're coming from. I see where you're coming from. Yeah, traditionally A/B testing is more like experimentation analytics. I agree it's not traditional data science, but we will cover it because it's an important aspect of data science with the idea that the part of deploying a model and seeing what the results are would be like an experiment, right? It would be, we think of it as an experiment where I build some model, see what the results are on a different group than a kind of a baseline control group that's not exposed to that model. So it's important for us to know what it is. You could argue the actual process of doing A/B testing is not really data science, but if you add in that context of usually people are interested in using it in conjunction with building a model and exposing it to users as an experiment. Does that make sense? All right, let's go into each of these steps and talk a little bit more about them. Okay, so usually things start in the beginning with a problem definition, which is a goal or a question that will be addressed through collecting and analyzing and deriving insight from data. So that's the very first step, and usually this is actually something that you would work together with other colleagues usually to come up with. So usually you may come up with this with like a product manager or with another engineering group or something like that to come up with a problem like, hey, we need to build a recommendation system for our users to get better recommendations for their movies or for their shows or for the products on our website. So there usually is going to be a question or a goal, or hey, we want to come up with a sales forecast for the next 3 quarters, given the data we already have for this quarter or the previous quarters. So, usually you have to start with a problem. So you have to start with a problem definition that you want to address. And honestly, that goes hand in hand with the next step, which is once you have a problem in mind, you then have to collect data around that problem. So you have to gather the relevant data sets, which could also involve working with external partners to do that. So maybe you have to work with data engineers to help you go out and collect that data or make that data accessible. You may have to work with, you may have to do it yourself and go and gather historical data that can help answer that problem. So sometimes this is up to you. You have to go and go out and collect that historical data or that data that's relevant to your problem. That is totally possible. But sometimes you're also working with external partners like a data engineer to make that possible to go and collect the data. But of course, the key word here is relevant, right? The data needs to be relevant to the problem that you're solving, and that can be a challenge. So I know these are listed as the first 2 steps and they seem pretty straightforward. but they can be the most challenging at times, is defining the right problem and collecting the right data, getting that available. It's not always trivial. But in this course, we'll usually assume that we have these two things. We'll usually assume that, yes, there's a problem we know we want to address. For practice purposes, we have that. And then we also have data already available for us. We don't have to go out and fish for it and collect it and scrape it from somewhere. We'll assume that's already been done, and we're just using the data that we have available. So in this course, these two steps will usually be done for us, mainly just for so that we can practice all the other steps. But in the real world, that would usually be, someone you're working together to formulate a problem with external stakeholders, and you're also gathering data either by yourself or with the help of maybe like a data engineer or someone like that. Okay. So again, these two things we'll usually have in this course, which leads us to the next phase, which is that data preparation phase. So this is where I said we need to clean the data and explore it a little bit. So usually this process can take some time. So it can be a very time-consuming process. But the typical tasks we're doing here are getting a handle on any missing data. So figuring out a strategy to handle missing data, we'll talk about that. How to identify and handle outliers, we'll talk about that. Maybe duplicate data, inconsistent data that doesn't make sense. We can identify that, we can get rid of it or have some strategy to handle it. So getting a handle on cleaning up our data is going to be an important task, and that might take some time. That might take some time to work with our data and kind of we have to learn how to do the proper code, clean it up, get it to a good state. And then once we do that, we can start to explore it a bit to gain insights. And this is where we'll usually use visualization at our disposal. So maybe we'll build some graphs to quickly visualize, get some patterns, see what the data looks like, figure out if there's any relationships in the data. That's what we'll learn about visualization that will really help us. So when we say explore, we're mostly talking about building graphs to help us kind of tell a story about what we see in that data, assuming that it's been cleaned up, right? Assuming that we have it cleaned up, we've removed all our missing values, outliers, inconsistent values. We now have a clean set of data. We can start to explore it. So usually doing visualizations. It could also be, it's not only visualization, but it could also be summaries. So maybe it's really useful to tell a story like what is the average for all these users, or what is the average sales for the last few weeks? What is the median sales? Like those kind of statistics might be really useful summaries to tell a story about the data. Okay. Okay. So we have our steps here: problem definition, data collection, cleaning, exploration, first three steps. Okay. And again, we're going to, like, as we go along, we will deal with these problems. We'll have actual examples that will deal with this process. So we'll see this process from end to end many times as we get into our examples later on. Bronze, silver, gold. So usually those are like data engineering terms to refer to basically how clean the data is. So like bronze is kind of like the rawest form. It's usually like data that has not been aggregated in any way. It's usually pretty raw. It hasn't been cleaned up in any way. Silver might be cleaned up, but not really aggregated. So silver might be like we've removed missing values. We've removed outliers. So silver is a bit cleaned up, but it's still kind of raw. And then gold would usually be like our final transformations have been applied to it. Like maybe we've done some averaging, we've done some transformations. So usually those are terms that you see to refer to the different like stages of quality. Gold being like the highest quality, like the final data set. By the way, we don't really use those terms too often. I think you see those terms a lot in like data engineering. Don't really see them that much here, just because the assumption is that we're always going to clean up, like our models aren't going to be good unless we get to a gold state, right? And unless we clean up our data, unless we do the right transformations that make sense, like our models really aren't going to be useful until we reach that state. So we're always going to be pushing to like clean up and get to a good state. Okay. So we have 1, 2, 3. Let's look at the next few steps. So once our data is clean and we've explored it a little bit, this is step 4, which is feature engineering. So this is the other kind of data preparation step that I talked about. So feature engineering, what is that? It is a creation or transformation of new features. So you might ask, what is a feature? A feature is just a variable that is an input to a model. Okay. A feature is just an input. So I want you to think of, like, in an Excel spreadsheet, a feature is something like a column. It's an independent variable, like a column that we would use to build a model off of. Like, that will be one input. We would call it a feature that's going into the model as an input. Okay. So feature engineering is the process of kind of building new features. And those can be by doing simple transformations. Like maybe we do some scaling, like dividing by 10, multiplying by 10. Those are simple scaling we can do to features. We could do more complex transformations, like doing a linear transformation to it. We could take a square root, we could take a logarithm, we could take an exponential, many different transforms we can do to our data to create new features. And sometimes that makes sense to do that. Sometimes we don't need to do that much feature engineering, but that's something we will get a feel for as we start to do examples. Is like, when does it make sense to do feature engineering, and when do we not have to? So feature engineering will be more of an art than a science, honestly. And we're going to do plenty of examples where we do feature engineering to see what kinds of transformations we typically will do. Everything we're talking about will be part of the current data we're working with. Is it always performed? No, we don't necessarily always do feature engineering, but it is a step. Like, we can and we should evaluate if we should. Okay. So will we always do it? No, but we have the ability to do it. And it's a step worth calling out because it can be very valuable to do. So again, we haven't learned how to do that yet, so it may not make that much sense to us, but I'm calling it out as a very important step in the process. And as we start to do examples later down the road, we're going to come back and spend some time on feature engineering because it is an important step. It is an important step often to do it. Okay. So this was step 4, and this was data prep. So draw a line here because this is all like the data prep, and then these couple of steps here are all modeling oriented. So once we have our data prepared, we've cleaned it up, we've done exploration to determine what we should keep, we've done some engineering to do some scaling or transform the features that we have, we can now build a model. And so this will all be something we will learn in our next we will learn how to build models in our next course on ML, but just calling it out as, that would be the next natural step. Is once we have our data cleaned up to derive an insight from it, we may want to build a model off of it. And so that will involve kind of defining a model, training it on this data that we've prepared as step number 5. And then step number 6 will be kind of an evaluation step of determining if we have a good enough model by evaluating it. By the way, this process isn't necessarily linear in the sense that we may iterate here and go back and, repeat these steps. So we may go back and forth and keep repeating these by building a new model, determining if it's good enough, repeating and repeating and repeating that process. And we may even go all the way back up to here and build some new features if the model isn't doing that well either. That may be possible. So by no means is this process always linear. We may repeat, especially this model training and building and evaluation steps. We definitely can repeat these back and forth until we kind of converge on a good enough model. That's something we'll discuss when we get into modeling. I don't want to go into details now, but that is, suffice to say, like, we can iterate those steps quite a bit, and we can spend a lot of time on it for sure as a data scientist. Okay. And then, oh, by the way, there's one more. So there should be a step here on deployment, which is kind of mentioned here, but I would argue it's its own step. But once we have the model done, then we can kind of deploy it. Now, deployment means a lot of different things. There's a lot of different ways to do that. We won't get into that till much, much later in the program. It's not really going to be a focus for us at the moment. We're mainly going to focus in on all of the data preparation steps and then all of the modeling, and then leave this part till kind of the very end of the program. Okay. But it is important part. Like we need to make you, once we build a model, we do want to have it be useful in the real world. So we need a way for it to be integrated into existing systems, which can be different. There are different ways to do that. Okay. All right. So let's go back and circle around to Python. I know, we spent some time on it already, but just to reiterate that Python will be our friend here when we're doing data science. So it's going to be the preferred programming language for anything data science, and that's true in the industry. Python is widely used, mainly because it has so many great packages to help us work with data, namely NumPy and Pandas, which are the first two we will look at. And then it has many others to help us build models like Scikit-learn, which we'll get familiar with. And then it has others to do visualization that we'll study. So it basically has packages that do most of the tasks for us that we're interested in doing. So that's why we'll stick with Python. It's really great for data science. So we've talked about this before. Why people prefer to use Python is because it's open source, interpreted. It has so many great packages that are oriented for data science and can help us do data science really easily. A lot of people used to use R to do data science, but it's been a shift over towards Python because of its flexibility. Python can integrate with other systems pretty easily, whereas R is more difficult to use. Yeah, R is it's like a scientific analysis language. It's used in a lot of like statistics. A lot of statistics people like using R, but for doing data science, it's almost exclusively done in Python. So you don't see R too often. I've really never seen it. I've only seen Python in the industry. So no worries about the R. Historically, R has been around. R has been around for a while, but Python is by far and away the most used data science language. I've for sure. Okay. So I want to briefly tell you about some of the packages that we are going to study in our course that are in Python that we will use to do data science. So I just want to briefly talk about them. And then, of course, we're going to have a couple of lessons dedicated to going into those, like NumPy and Pandas and all the visualization libraries. So the first one is NumPy. So NumPy is short for numerical Python. So that's why it's called NumPy, the numerical Python. And it is a Python package for doing computing, basically scientific computing, using these array structures that NumPy has created. And so many things are built off of NumPy arrays and the ability to operate on these NumPy arrays. So NumPy came around and created these multi-dimensional arrays, which are essentially like matrices, and also had a lot of different computing tools around the matrices and arrays that so many other packages are built off of. So we're going to learn Pandas. Pandas is built off of NumPy. So is Matplotlib, which is for plotting, and so many other packages are built off of NumPy. So it's a really foundational package for working with data because data will be stored in NumPy arrays. The NumPy array is the kind of foundational data type of NumPy, and so many things work with NumPy arrays. Okay, so we're gonna have a whole lesson dedicated to NumPy coming up next, but NumPy is going to be the first place we're going to start just because it's so important for working with data. Its multi-dimensional arrays are so useful for storing and manipulating data. So it's pretty important. What is a Fourier transform? It is a transformation of data into like a signal, basically like a signal transformation. So you go from like basically like a time series into like a frequency series. It's used in signal processing. Okay, so the second package that we will study, so we'll start with NumPy. We'll start with that today. So right after this lesson, we'll dive right into NumPy and start working with examples of the NumPy arrays. But right after that is the library Pandas, which we'll spend a lot of time with. Pandas is a library built off of NumPy. So it depends on NumPy. And it basically comes around and provides a more structure to manipulating data. So if you're, like I said earlier, if you're familiar with Excel, Pandas has a lot of functionality that mimics what you would do with a spreadsheet. Basically, like structured row column data is what Pandas excels at. So Pandas is going to be a really fundamental package for us to manipulate data that's structured in kind of a row column matrix format, but it's built off of NumPy. So it uses NumPy under the hood to do all the manipulation, but Pandas provides its own data structures to kind of put data into almost like a spreadsheet format that we can manipulate. Okay. So really, Pandas is going to be really, really powerful for us to manipulate data, and we'll use it all the time. So if anything coming out of this course, you guys will be Pandas experts, if anything else. Yeah, I mean, of course, you'll learn more than that, but I think you'll come away as being really, really good users of Pandas and NumPy for that matter, but certainly Pandas. So we're going to study NumPy first, and then we'll have a lesson dedicated to Pandas right after NumPy. So we'll have a lot more to say about it, but I just wanted to kind of preview that, it's a really important package in the data science ecosystem because it helps us manipulate that structured data that's in like a row column format, like a table. Okay. Then another package is the SciPy package, which is short for Scientific Python. It is another open source library that's built on top of NumPy. So it uses NumPy arrays as its underlying data structures to do the manipulations. SciPy contains a lot of scientific formulas and a lot of scientific computing tools that we'll use, especially when we get into hypothesis testing. So it contains a lot of like z-test, t-test distributions, things like that. So it's tailored for that. It also has things like the Fourier transform as well. It has different linear algebra manipulations as well. So SciPy will be really useful when we get into our hypothesis testing and A/B testing. It has those kind of those distributions that we'll need to do our tests, like a student t-test or a z-test or those kind of things. We'll use SciPy for. So really important package. We'll see later we do hypothesis testing. Another one that is going to be useful from time to time is the stats models package. So it is one that basically has a lot of statistics oriented things. It has some basic models in there, like linear regression or logistic regression. We will generally favor a different package to do those kind of models, but just calling it out that stats models does have some useful stuff when it comes to doing statistical testing. So there are some like chi-square tests or ANOVA tests that we will borrow from stats models that SciPy doesn't have. We can borrow from stats models. So we will use it when we get into hypothesis testing as well. So these last two, so SciPy and stats models, are two packages that we'll use when we get into A/B hypothesis testing. Okay. So that brings us to Scikit-learn. Now, this is going to be our primary package for doing machine learning. So this will be one that we'll build all of our models and machine learning off of when we get into our machine learning course. So we won't really use Scikit-learn in this current course, but when we get into machine learning, it will be our go-to package to do all of our machine learning with. It is a fantastic, fantastic library that's been developed over years to contain all the basic models that we would ever want to build. Scikit-learn is really awesome. So it can build models for so many different use cases, and it's a really easy package to use. It has a really nice interface, really easy interface. So we will see that later on when we get into our next course on machine learning. But just calling it out, that is a very popular data science library, Scikit-learn. So when we get into our modeling, we will use Scikit-learn. When we do our data prep manipulations, we'll be using NumPy and Pandas. Finally, for visualization, we will be using a library called Matplotlib. So it is kind of the foundational Python plotting library. that borrows inspiration from MATLAB. So if you guys have ever used the MATLAB plotting, it's actually very inspired by that, hence the name Matplot from MATLAB. But it's going to be our main tool for using for building graphs. Okay, so it's a foundational library for building graphs. Almost every other library that does visualizations is built off of this one, built off of Matplotlib. So when we get into our visualization course, we will come back and talk a lot about Matplotlib and practice with Matplotlib quite a bit. What is that course called? Machine learning. The next course is called machine learning. Okay. And then another visualization library that we will lean on heavily is the Seaborn library. This is one that is built on top of Matplotlib. So Matplotlib is kind of like NumPy. It's the foundation, and then a lot of things are built on top of it. Seaborn being one of them. Seaborn being one of them. And it basically has just better aesthetics. It provides not only like better aesthetics than just basic Matplotlib, it also has more scientific kind of plots and more interesting plots than the regular ones you get out of the box with Matplotlib. So it has really interesting histograms, file-in plots, heat maps. It can do statistical error, like confidence interval bars. So it just builds better plots than basic Matplotlib. Matplotlib is very basic. It's really easy to use. You can build a lot of plots with it, as we're going to learn. But Seaborn is really nice. It makes things aesthetically pleasing, and so we'll also use Seaborn from time to time. It's another plotting library that we'll get some practice with when we get into visualization. And another one of those is Plotly. So we have Seaborn and Plotly both built off of Matplotlib in order to do plots. Now, Plotly's specialty is for building interactive graphs. So when you build a Plotly graph, you can actually, it'll pop up in your web browser, kind of like Jupyter Notebooks do. And you can click around in the graph and mark down points. You can zoom in, you can zoom out. But you can zoom in, you can zoom out, you can do a lot of interactions with Plotly. So if you want to build an interactive graph, Plotly is a good package. Again, it's built off of Matplotlib. So we'll get some practice with Plotly. So these three we're going to practice when we get into visualization. Seaborn, Matplotlib is the basic foundation. Seaborn and Plotly both build off of it. We'll get some practice with all three of those when we get into visualization. Okay. So what I wanted to do is take a 5-minute break. I know we've been going for a little over an hour. I want to take a 5-minute break, and then when we come back, we'll finish up this lesson. It has some plot examples. I'm going to just briefly go through those, mainly because we're going to have a whole lesson dedicated to visualization. So I don't want to spend too much time on plotting just yet, because we will get to that. But after that, we'll get into NumPy. So we'll get right into NumPy and some of the code, which will be nice. So the rest of these slides just go through some plots that we will be building later on when we get into our visualization. So just wanted to briefly go through those just to show you some of the different types of plots we'll do. So the easiest kind is basically a line plot that connects different points. So this would be like if we were plotting out something over time, like a stock price or a sales value over different quarters or weeks, temperatures over time, something like that. So basic kind of plot, we'll be able to build that, no problem. We can even mark different points on those. That'll be easy to do with Matplotlib or Seaborn or Plotly. That'll be really easy to do. So again, we'll show you how to build these with code later on when we get into visualizations, but just showing you the possibilities right now. Scatter plots will do these, which have different points kind of scattered throughout on two axes here. This is usually helpful to figure out how the data is kind of maybe clustered together, or figure out if there's relationships between two variables, like if they tend to trend the same direction or in the opposite direction, or if they're kind of just distributed all over the place. So we'll be able to build scatter plots. That'll be helpful. Area plots that show like cumulative areas on top of each other, we'll be able to show that. That'll be pretty easy to graph for different, maybe tracking total sales over successive quarters, showing different contributions of categories we'll be able to do. So we'll be able to do an area plot. basic bar plot we'll be able to do. Again, all of these examples were built using Matplotlib, so we'll be able to do that. But they have equivalent versions in Plotly and Seaborn. So again, those are built off of Matplotlib. So we can even put grids in the background to show to kind of assist the viewing of it, to give an idea of where the different points are in the grid. So that will be easy to do. Histograms. Now, histograms are going to be extremely useful for us. We'll build histograms a lot because they will help us visualize how data is distributed, which is extremely important to know. You know, is it kind of distributed like this in this picture, which is kind of like a bell curve, or is it flat? Does it have kind of two peaks to it? Knowing this distribution will be extremely useful to us. So we will often build a histogram that kind of looks like this. So histograms will be extremely useful. We can build pie graphs, which show different percentages. So, you know, there may be certain situations where that makes sense. We're telling a story of our data. It makes sense to use a pie graph. That'll be easy to do. Again, these are all just examples of what's possible. We have to show you how to build these, and we will when we get into the data visualization lesson, which is what this kind of note says at the bottom. Once we get into that lesson, we will show you how to do the code to build these. Okay, so just to wrap up this first introductory lesson, we have shown you what data science is, which is kind of the extraction of insight, deriving insight from data. And we have a bunch of different packages that are going to help us do that. We also have a process, which is going to help us do that, which is usually defining a problem, collecting data, doing data preparation, and then doing modeling after that. So, you know, basic foundations at this point. What we're going to do is now go into NumPy. So we're going to start with NumPy and then go into Pandas after that. So we're going to start studying these packages. They're going to help us do some of these different tasks in data science. Okay. All right. So let's talk about NumPy. Now, remember, NumPy is the open source library that is used for doing, math and scientific computing on basically these arrays. So we are going to take a look at the NumPy array object as the first thing that we'll look at. Now, the NumPy array object behaves very similar to a list. So we learned about lists in our previous course, and the NumPy array is very similar to a list. We can slice it like a list. We can access elements like a list. It's ordered like a list, but it's a lot faster to do mathematics with the array. And it comes with a bunch of built-in functions like mean, median, mode, all these special things on the array that we don't get with a list. For instance, Python lists do not have a notion of an average. You can't calculate the average of a list without doing a manual calculation. So, but a NumPy array has a mean function that comes built in that we can take the average. NumPy has like an average function that we can take of an array or a median or a mode. So arrays are really advantageous to work with inside of NumPy. So let's take a look at some examples of a NumPy array. So in the first cell here, I want to point your attention to two things. One is that in order to use NumPy, we import it. Do you see how we import NumPy? And we do this thing called as MP. Now, what this is we do an alias. This is called an alias NumPy as NP. We basically shorthand it to NP, which is an industry standard. So anytime you're looking at code and you see NP dot something, that is short for NumPy. So in the industry, if everyone is going to shorthand NumPy to NP. That's just what people do. So as is the way to alias and import so that when we use NumPy in our code, we don't have to type out the full word NumPy. We can just do NP. So that's why you see NP here, is because, and really throughout our code, we use NP. You see it all over the place. It's a shorthand alias for the NumPy package that we're using. So we are importing this package, meaning that we are going to use it in our code, but we are aliasing it to NP. This is the industry standard to do. Most of these packages have a nice alias to them. Like Pandas will have an alias, Matplotlib will have an alias, just to make it shorter. All right. So the next thing I want to point our attention to is building a NumPy array. So notice that we can build this NumPy array by doing np.array. So np.array builds a NumPy array object. And what we're passing in is just a list of data. Okay, so we have a list of integers that we pass into this NP array, which will build a NumPy array out of this list. So NumPy arrays can be built out of lists, they can be built out of tuples, they can be built out of other NumPy arrays. There's many ways to build a NumPy array, but the most common is to pass in a list, to convert a list into a NumPy array. So here we are building a NumPy array from a list, which is pretty typical. By the way, you guys remember I said that I'm going to be writing a lot of comments. I'll share these notebooks in our Slack after the classes, but I encourage you guys to do the same thing, is to write comments in your notebooks. Okay, try to write comments in your notebooks to outline what the code's actually doing. How do you install NumPy? You just need to do, so inside of a cell, you can run this command like pip install NumPy. Try running that inside of a Jupyter cell. Yeah, this command is not going to work for you because this is like a generic. This is on Windows, like a generic Windows command. But if you're inside, are you inside of a notebook, Mariel? If you're inside of a notebook, just run this inside of a cell. It should install it. Yeah, that works too. You can open your terminal and do pip install. If you do that, you'll probably have to restart your kernel. No, so Colab comes with NumPy already installed. Yeah, so that's another advantage of Colab, is it already has that installed. We don't need to worry about it. Yeah, so if it says requirement already satisfied, which is what this is going to say if I run this, it's because it's already installed. So this means that I already have it installed. Yeah, you already have it installed. Yep. So in Colab, it already exists. This one, new cell and this command. If you can't get it to work in your VS Code, I really encourage you to do Colab as much as you can. Just to get something that works, because NumPy is already installed in Colab, so there's really nothing you need to do extra. Thanks, Tim. That'd be great. That'd be great. Okay. All right. So this builds, going back to this builds a NumPy array off of a list. So if we run this code, what's happening is we are building an array and storing it in this array variable, and we can print the array. Now look at what the array looks like. It kind of looks like a list when we print it, except the way we can tell this is a NumPy array is that it does not, when we print it, it does not have the commas. Notice that the data in there does not have the commas, and that's because it's being treated as a NumPy array. So it doesn't have the commas. It's not, at that point, it's now an array, it's not a list. So it looks slightly differently. And you can even see when we print out the type that this array is actually a NumPy n-dimensional array, which is the foundational data type NumPy. So this is an NumPy ND array, which is the foundational data type of NumPy. So we have created a NumPy array, and now you can see what its type is this MP ND array. Okay. Were you guys able to run this first cell if you run it? It's not going to do anything but show this. You should see this, and then you should see it's printing out the type. You should see those two things. And do we see how that this is creating a NumPy array? So np.array is how that's the function we use to build a NumPy array. And we're passing in a list of data to build that array. All right. Yeah, it might take a moment to start up the kernel. All right. Okay. What I wanted to do is go to the next cell and talk about how we can create some matrices, essentially multi-dimensional arrays. So this array that we've created so far is actually just a one-dimensional array because it only has one dimension to it. It basically has one list of data. But of course, we would be interested in working a lot of times with multi-dimensional data because that's typically like what a spreadsheet has, right? Rows and columns. So just to give you guys an example, like NumPy actually supports 0 dimensions, which is basically a constant. So a single number, a single value is considered a 0D array. So a single value is considered as 0 dimensions, is just a single value. So if we built a NumPy array and just passed in a single integer, or it doesn't have to be integer, it could be float like 24.6, whatever it is, that would be considered a 0 dimensional array. But we've already built a 1D array, which is just a single list, basically a flat list with, so just if we use a list with a list of, I should say a single list of values is a 1D array. So we've already seen that. It is a scalar. Yeah, we would call that a scalar. Yes. Good. Yes, that's true. Scalar. Perfect. So a single list of values is going to be a one-dimensional array here. Now, what gets interesting is now when we do a list that has list as its elements. So this is a list of lists is now a 2D array. So I want you guys to see that how we're building a NumPy array out of a list, but look at what the elements of the list are. They're actually lists themselves. So you see how within this overall list, the first element is a list that is 111. That kind of mimics basically like a row. So you think of it as like each list is like a row in a matrix. So this two-dimensional array is really like a matrix, right? So this is an interesting use case where, of course we could have more than just these two. So we could have a third list here that is like 4, 5, 6, and that would be valid as well. So this would be basically a matrix that has 3 rows and each row has basically three items in it. So we would think of it as basically having 3 columns, right? So it's like a 3 by 3 matrix, but it is 2 dimensions. The two-dimensional array. It has rows and columns at this point. So it has rows and columns. The two-dimensional array. Let me ask you guys, do we see how this has 2 dimensions to it? It's a list of lists. So it has 2 dimensions. Does all the lists need to have the same rows? What do you think? What do you think would happen if, let's try it. Let's try making this a smaller dimension. Do you think this is going to be allowed? Let's see. So yeah, this gives us an error. So yeah, you're exactly right. This will give us an error that the dimensions do not match. So this is not allowed, but let's see if I add in the 6, this should now be okay. And there it is. This is now okay. No more error. Okay, no more error. So yeah, it's still going to be an error if the shapes do not match. So again, if we made this a smaller one, that's going to be an error. And it's going to tell us that we have one dimension that is inhomogeneous, meaning it doesn't match. It's not the same. They have one dimension that's not the same. Its shape doesn't match. It's not correct. So therefore, we should correct that and make sure it is matching. Okay. So that is a two-dimensional array, list of lists. By the way, that doesn't have to stop there. We could keep going. So now we have a three-dimensional array, which has lists of lists of lists. So it basically has one of these matrices as each element. So see how this has basically an overall list. So this has each, it has a list where each element is a 2D array, right? Each element is a matrix. So here is one of those matrices, is the first element. And then here is another 2D matrix that is the next element. And this forms a three-dimensional array. So if we print this out, we can see that we get this 3D array where this matrix is the first item, this matrix is the second item, and on and on and on. Didn't understand how 2D is different from 3D. Do you see how, okay, so do you see how with the 2D, basically we take this whole thing and that's just one element of the 3D. This 2D matrix is one element, and then we have another 2D matrix as the next element. So we have matrices are now the elements of the 3D array. Whereas look at what's the elements of the 2D array. They're just lists. It doesn't have to be two. That's just the example we have. It doesn't have to be two. But by the way, one thing that gives away the dimensions is how many of these brackets we have. So you see how we have two brackets and see how this has three brackets? So what's an example of using a 3D array? Yeah, so something that uses a 3D array would be like a batch of images. So let me give you an example. So an image is like a 2D array because it has pixels, right? It's basically an image is broken down like this that has pixels with whatever resolution. And so if we have a collection of those, it's like we have a collection of these guys is a 3D array. Like if we have 100 of those, it's like a 3D array. Does that example make sense? Like a collection of images would be a 3D array because every image is a two-dimensional matrix of pixels. Does this example make sense though? Like this is a good one, I think. I'm glad you asked it because I think it's a good one for thinking about what a 3D array is. Every element is a 2D matrix. Okay. Perfect. All right, perfect. So just to recap this, we have the NumPy array. So we're able to build NumPy arrays using the np.array, and we're able to take a list of data and populate it into an array. And then what we're going to do is just build off of this to learn how to manipulate that array and do different things with that array coming up next. All right, so let's go to the next notebook. Let's go to 3.02. Okay, perfect. So let's go to our next notebook. Okay, do you guys have the 3.02 notebook? Do you have it up? That's the next one we're going to do. So take a moment to pull that one up. Yep, I see some thumbs up. Okay, so we're going to build off of that NumPy array by taking a look at some attributes of arrays. So assuming we have an array, no matter how many dimensions it is, what are some attributes of this array that are useful to us? Okay, so let's take a look at an example where, again, here we import NumPy and we're initially making a 2D array, right? So we make a 2D array. So then what we're going to do is print out a bunch of the attributes about this array. And we're going to explain what they do. So the first is, if we ever want to know how many dimensions an array has, there's actually an attribute for that, which is called ndim. So if we just do dot ndim, by the way, let me call that out here, is we access attributes of an object by using the syntax object dot attribute. So in this case, we have our array as our object. So it would be like i.e. array dot shape would be an attribute. Shape is an attribute of the array. Array is our object here. Okay, so that's our syntax to access different attributes. So the first attribute we're going to learn about is called indim, which gives us the number of dimensions. And so when we print that out, you can see what it's going to be. It's going to be 2. And that makes sense. It's a 2-dimensional array. Okay, so the first is indim, which gives us the number. This gives us the number of dimensions, which equals 2 in this case. Okay, and that makes sense. We know it's a 2-dimensional array based on the fact that our elements are 1D lists. So we have a list of lists. It's going to be 2 dimensions. Now shape gives us the quantity. So it gives us basically the number of rows and columns. So in this case, what this is saying is we have 2 rows and 3 elements in each row. So shape is giving us an idea of how many elements we actually have, or what the shape of this matrix is. That's why it's called shape. So in this case, we have a 2D array that kind of looks like this, right? Where we have 1, 2, 3, and then in this example, 4, 2, 5. So we have 2 rows, and we have 3 columns. 2 rows and 3 columns. Hence, we get a shape of 2 by 3. Does that make sense? 2 by 3. Okay. So shape is going to be incredibly useful as we go forward because there's a lot of times where if we have an array, we actually just want to know how many rows and columns it has, which is the shape. So the shape is a good attribute to know. Does the bracket define it as a 2D versus 3D array? It's the fact that it's 2 brackets defines it as a 2D array. It has 2 brackets here. It's a list of lists. This is 2D. It's the fact that it has. So I meant to say that in this shape we're going to see 2 entries. Sorry, in the shape we're going to see 2 entries. So the dimensions will match how many entries we have here. So if we have two entries, because it's two-dimensional. That's the thing that. So sorry, Roberto, I was wrong on what I told you. It is when we have 2 entries here, that's because it's 2 dimensions, not the fact that this is a 2. It's 2 entries in the shape. By the way, how can we get a 3rd row? We could just add in another list here, right? So if we add in another list that has 3 elements, like 7, 8, 9, this is still a 2-dimensional array. But what I want you to notice is that it's going to turn into, this shape is going to turn different and this size is going to turn different, but it should still be 2D. So see how this shape went from 2 by 3 to 3 by 3? So now I want to talk about the size. The size is the total number of elements in the array. So in this case, we have 3 by 3, so we have 9 total elements. So this will always be the product of the shape, right? Okay, do we see what size is? Size just gives us the total number of elements. Okay, total number of elements, which is really just a multiplication of the shape. There's 3 rows, 3 items in each row. So 3 by 3 is 9 total elements. Okay, so that's the total number. The size is the total number of elements. Now, the D type is telling us what every member's type is. So maybe not that interesting, but this is kind of the default. So this gives us what each element's data type. So we can grab, in this case, they're all integers, but they're an int64. So we can also grab how many bytes each one takes up, which is the item size attribute. This is each element's memory footprint, each element's memory size, which is going to be 8 bytes. And we can also get, if we want to, very rare we would actually need to access this, but we can actually get the memory reference for the array data. So array.data, we won't really ever need to worry about this, but this is actually really important for Pandas to be able to access later on, because everything in Pandas is built off of NumPy. It needs to manipulate the raw memory often in order to do different calculations with that data. So it typically will need access to that data attribute, but we generally will never need to know what that memory address is. Okay. I think the one that we'll use the most is probably going to be shape. We'll probably worry about the shape the most when we're working with NumPy arrays. Okay, perfect. Okay, let me show you a couple of functions. All elements in a sheet array must have the same data type. No, they don't have to. Just like a list, they don't have to. When we're working with data, they typically will, but they don't have to. All right, I want to show you a couple of functions we can do to manipulate the shape of an array. So the first one is we can actually reshape an array using the array.reshape function. So this is a function that we can pass in. So we can do array.reshape, and then we put in the a tuple with the new shape. So in this case, we're putting in 4, 3, which is to say we want to take this existing array that is a one-dimensional array. So notice this is a 1D array, and we want to turn it into a two-dimensional array, right? That is 4 by 3, okay? 4 by 3, meaning there should be 4 rows and 3 columns. And but first of all, let me ask you guys, do you think this is even possible? What do you think needs to be true in order to reshape this properly? What do you think? If I want to take a flat 1D array and put it into something that's 4 by 3, how many elements do I need to do that? Perfect. You guys are right on top of it. 12. Perfect. Yep. I need 12 elements. So what happens if I don't have 12? Do we think this is going to work? Yeah, let's try it. Error. And look at what the error tells us. I cannot reshape something of size 11 into shape 4 by 3. It even tells us directly, we can't do that. So yes, that is definitely a prerequisite to using reshape, is that you need this total number of elements to match the number of elements that you start with. And then it will work. So if you're going to use reshape, you can reshape into any shape that you want to. So we could even reshape this into 3 by 4. That would be okay. We could do 3 by 4 because that totals up to 12. We could do 2 by 6. That would be okay. But could we do 2 by 7? No, we don't know how to reshape something that is 14 into a shape 12. We only have 12 items. 2 by 3 by 2? Sure, we could do that. That'd be a 3-dimensional. We could do that. And now we have a 3D array because we have each element is 3 by 2. And we have 2 of them. So each matrix is 3 by 2. And we have 2 of those. So we could do that. So that's what reshape does, is reshape can take an existing array and move it into a new shape, assuming that the shapes align properly. So reshape can do that for us. So that's actually incredibly useful. We'll use reshape from time to time. And then we can actually do the reverse of reshape. So we can always take something and flatten it out into a 1D array. Okay, we can always do that as well. So the flatten function can take something and put it into, so this will always give us a 1D array. So no matter what shape we start with, we can flatten it out into a one-dimensional version of it, okay, by using the flatten function. So this does a particular reshape that will completely flatten the array. So you can see it takes this three-dimensional array here and goes ahead and reshapes it, or basically flattens it right into this exactly flat one-dimensional array. So flatten always returns a 1D array. Pretty straightforward. Is there any benefits? Yeah, sometimes we want to take something that is in one shape and move it into another because we're going to manipulate it. We're going to assume it has a particular shape to manipulate it. We'll see that later on when we get into deep learning, especially when we work with images or text. It's going to be important to reshape things from time to time. So maybe not this second, but when we get into deep learning, we'll go ahead and reshape. Is that there is a transpose function. Now, what this does is it swaps rows and columns. So it transposes this into whatever was our rows. So this 1, 2, 3 now becomes the columns. And so this was a 2 by 3 matrix. It now transposes into a 3 by 2 matrix. So transpose swaps our rows and columns, and that's going to be useful down the road too for different algebra calculations we may need to do. We may need to transpose from time to time. Okay, so we're going to start with doing some arithmetic operations. So just to show you guys that when you have data in NumPy arrays, you can do element-wise operations, meaning that we can do operations that go element by element, match them up, and do some type of mathematical operation between them. So things like addition, subtraction, multiplication, division, we can do those between elements. So for instance, we have these two arrays of the same size, the same shape, and we can go ahead and add them together, meaning that like this position is going to be added to this position is going to be added to this position is going to be added to this position. Okay. So when we do that, we get basically 40 in every slot because we get 30 plus 10 is 40, 20 plus 20 is 40, and 10 plus 30 is also 40. But look at the syntax of it. There's actually two different ways to do it. You can do the numpy dot add, and then you pass in A and B. So this is one way to do it. One way to add is to use np.add, and then you pass in your array 1 and array 2. So you can do that. And so we add those two and store it in the result. And notice that the result is a same shape array, but just with each element added together from the original arrays. So that's one way to do it. The other is you could just do regular arithmetic. So you could just do A plus B. This is an alternative. Alternative is to just use standard arithmetic operations. It doesn't really matter which one you do. I've seen both. Both will result in the same kind of array. So we could store, we could do something like result equals A plus B, and then store that in the result, and then print the result. So it's same thing as before. We get the same array. So you can do either one, np.add A plus B. Either one will do that element-wise addition between the elements. Okay, pretty straightforward. We also have the same thing for subtract, multiply, and divide. So for instance, when we have these, now we have a 2D array. So this is now two-dimensional, but the same exact thing is going to happen. We're going to go through and subtract. This is going to do, this is the same as A minus B. So this takes A and subtracts B from it. So we have 30 minus 10 is 20, 40 minus 20 is 20, 60 minus 30, and then we do 50 minus 40. So we're subtracting those elements in the same positions to get a result. This 2D array, that is the result of subtracting every element from the original arrays. So again, you could do A minus B, you could do np.subtract. Either way should work. 2D plus 3D, could you do it? Well, you could try it out. So this is a 2D, we could try it out. So let's copy this guy. let's do this guy, which is going to be a, let's see. So let's do a 3D array. So let's do one of these guys. And then let's do another one, but let's just change up the numbers. So let's do 10, 15, 20, 25, 30, 45. Let's do np dot subtract a and b. Let's see what we get. So we actually do get a result, and the reason we do is something called broadcasting, which is an interesting idea in NumPy that what they do is they basically will force the shapes to be aligned when you do a mathematical operation, but you might get some unintended consequences of doing that. For instance, we get some of these actually work where we get 30 minus 30, 40, 40, 60, 60. So we get these zeros here for this first guy. But notice that we basically take this and apply it to this. It basically takes this and subtracts to this guy secondarily. So we have 30 minus 10 is 20. And then 30 minus 15 is 15. Sorry, 40 minus 15 is 25. And so the shapes, the dimensions don't have to be the same. Dimensions don't have to be the same, but you can get unintended results. So be careful is the thing I would say. Be careful of doing the subtraction of NumPy will try to force the results to fit by taking this and applying it to this 2D matrix here, right? So it can work. You're just going to get maybe some unintended results that don't really make sense, but are possible in NumPy. If you subtract a bigger value from smaller, it'll give you a negative. Try doing, in this example, what would happen if we put B first? You get negatives. So yeah, it's still possible. You just get negatives there. Okay. So we can take like 30 times 10, 20 times 20, 10 times 30, and we can get those multiplications. So if we do that, we get this array, which is going to be 300, 400, 300. So these are just element-wise multiplications. Again, the alternative is to do A times B, and that would be the same thing. So if we just did result equals A times B, that would be the same thing. But we can do np dot multiply to make it more explicit the operation we're doing, that it's A times B. And this is not to be confused with matrix multiplication. So that's something I should call out here, is that matrix multiplication is a different matrix multiplication is different and will be covered later. So traditional matrix multiplication will be covered later, and that requires the matrices to be compatible, and it's a completely different operation than doing element-wise multiplication, okay? Which is just A star B or asterisk B or np dot multiply. We can do division. So notice that this is again a scenario where the shapes are not the same. We have a 2D array and we're dividing it by a 1D array. Now what happens is we basically take this and divide it by this, and then take this and divide it by this and get this second row. So this size is going to basically match the larger of the two shapes. So this first shape is two-dimensional, 2D. So basically the shape of this is 2 by 3 shape. and this is only basically a 1 by 3, not even, it's just a 3 element shape because it's just a 1D array. So it's a 1D array. So therefore, when we do the division, it's going to do that broadcasting thing that I mentioned earlier and try to force this to be able to divide by this. And the way NumPy will do that is say, okay, which is the bigger shape? This is the bigger shape because it has more dimensions. Try to take this and divide it by these guys. What do you think is going to happen if we reduce this size? If we did this, do you think this would work? If I reduce this down to only having 2 elements, do you think this division would work? Error. It doesn't broadcast that way. No. So you could even see it even says it tries to broadcast, but it doesn't know how to. So even with broadcasting, the shapes still need to align to some degree. So this still needs to be like so it needs to be a valid shape to be able to broadcast to each one of these dimensions here. Let's try it. Yes, we can divide B by A. We're just going to take, now this again is going to try to match the shape and just do this divided by this divided by this. But remember that A divided by B is not the same as B divided by A. They're not the same result. Yeah, you can get a division by, so try making one of these zeros. So try, let's say this was all zeros and we did A divided by B. Do you think that'll work? Do you think this will work? Yeah, it basically now it technically returns a result, but they're all infinity. Yeah, it basically says that we have a warning we cannot divide by 0. So it basically says that sure you could do it, but you're going to get infinities all over the place, and it's not you get a warning that you're dividing by 0. So it's kind of like an error there. Okay. All right. So let's go to doing exponents. So we can do element-wise exponents where every element in A is raised to a power of something in B. So for instance, we like 2 squared, we do 2 cubed, 2 to the 4th, 2 to the 5th, 2 to the 6th. And you can see what each one of those would be is this. So this just does every element in A, each element in A gets raised to the exponent of the corresponding element in B. So we get 2 squared, as I said, 2 cubed, 2 to the 4th, 2 to the 5th, 2 to the 6th. That may be useful from time to time. We may have a reason to take elements from one list and exponentiate them from another list. So there's a power function here to do that. So that may be useful. Before we move on to the statistics functions, which are going to be really interesting. So in fact, I can just show you a quick example of that. So we could call a NumPy array from an existing, so we could have inside of a list, we could have np.array, and then we could have 1, 2, 3, and then we could have an np.array, and then we could have 4, 5, 6. So this should make, so if we let me display X. So this makes a 2D array. Does this make sense? Like I'm defining an array as the input elements to build an array. Okay. So what's great about NumPy is with the arrays, it can easily do statistics on arrays. So it can find the medians, it can find the average, it can find the standard deviation, it can find the variance. Now I know we haven't technically defined what each of those are, but that's okay. It's useful to know that given the different statistical functions that we may want to do, NumPy can easily compute them on collections of data, collections of arrays, right? Or data that's inside of an array. So for instance, if we have this 2D array here, we can compute the median of all elements in the array, which would be np.median. So there's a built-in function from NumPy, np.median. So we can do np.median finds the median of an array. Okay, so this will calculate the median. So if you're, again, we will get to what the median is later on in our statistics overview later on, but the median is kind of the 50th percentile, like the middle element, right? The middle element of we basically order it from least to greatest and find that middle element. So in this case, the middle element is 4 out of all these elements that we have. Okay, np.median. We can take the average, which is the mean. So that's very nice. We can take the average. So we can do np.mean, which will take the average of this array. So it'll average all the elements together, and we get an average of 6.3333. So that's very convenient for us that we can compute an average of an array. I want you to, now this seems really straightforward, but I want you to see how powerful this is that lists, for example, do not have this ability. There is no built-in mean function for a list. So that's why this is so useful that NumPy has this ability, and it's really optimized. It's really fast to find the mean, really fast to find the median. It's a really optimized function to do it. If we wanted to find the average, we would have to do it manually on a list. We'd have to total up all the elements and divide by the size of the list. Not that that's hard to do, but it is something manual that we would have to define. It does not automatically exist like what we see here with np.mean as a simple function that we can apply. And we can apply it to NumPy arrays very easily to compute the average. So same thing with standard deviation and variance. Those are more advanced statistical functions that figure out the spread of the data away from the average. Again, we're going to learn about these later on, but np.std does the standard deviation, and then var does the variance. So, and really the standard deviation is the square root of the variance. So if you took this variance, sorry, if you took the standard deviation and just raised it to the second power, you would get the variance, but you can compute them separately this way. Okay. So pretty convenient that NumPy provides those statistical operations. We're going to be using these quite a bit especially when we do like exploration of our data and we want to find an average, we want to find what the standard deviation is. This is going to be really useful to use the NumPy function to compute that on an array of data. Okay, really useful. Okay, let's talk about percentile then. So NumPy also has a percentile function. So we can take an array and compute the 50th percentile, which would be the median. Again, we haven't learned what a percentile is, but if you think about ordering all the elements and figuring out like the median is at the 50th percentile, and then half the data is below that. So there's a point where like 25% of the data is below this certain value, and then 75% of the data is below this certain value, or 95% of the data is below this value. So the percentile is something that ranges between 0 to 100 we can take. So like the 99th percentile means that like 99% of the data is below this certain value. Okay, so like 99th percentile means that 99% of the data falls below that value if we ordered it and kind of sorted it that way. So we can compute any percentile we want by just passing in the array and then giving it a number between 0 to 100. Okay, so and this should be a whole number, 0 to 100. So for instance, we can compute the 99 percentile. Oops, I have to actually run this. Let me run that. There we go. So 99% of the values are below 22.8, which kind of makes sense because most numbers are pretty low. So there's really only one number below that number, which is the 24. So if I did the 100th percentile, that would basically be the max, right? It'd basically be that 24. So only 100% of the numbers are below the max. So it kind of makes sense. And then if I did the 50th percentile, that would be the median. Half the values are below that, half are above. So that matches the median that we found here, which was 4. Okay, so we can do percentile. All right, finally, wanted to mention that NumPy, you can manipulate strings in NumPy. Now, this is less often used because typically when we're working with NumPy data, we typically don't have strings inside of there. We usually are dealing with numerical data, hence why it's called numerical Python NumPy. But it is possible to work with strings and do different string manipulations. So for instance, if we have a NumPy array that has 2 strings hello world, and then another array that has welcome learners, so these are 2 1D arrays, we can actually concatenate element-wise strings by using the np.character module. And instead of doing the reason it's inside of the character module is instead of doing like a numerical addition, so typical arithmetic, it's doing a string addition, which is concatenation. So it's doing character addition here, which will concatenate these 2 strings, hello and welcome. So those end up merged together, concatenated together, and then world learners get concatenated together. So this is a string concatenation. Element-wise string concatenation. So it's from the np.char or character module within NumPy. Okay. Very rare. It's very rare we would have to do this, but I'm just pointing this out that it does exist. Okay. If for some reason we need to manipulate strings, we will have that ability too. Okay. All right. So then we can replace substrings with new strings. So if we have this original string called hello, how are you? We can print it out and we can replace, we can use a character replacement to replace within this string, replace hello with hi. So once we do that, we can print out the new string. So then we get hi, how are you as the new string. So this does a string replacement if we can find the substring. So if hello exists, so we should test this out and see like, is there something, so we could just put in something that doesn't exist in there, it's not going to be replaced. So this is saying, okay, let's try to do a replacement of this string. Let's replace something with hi, but something doesn't exist. So it's just going to return to us. It's not going to replace anything. It's just going to return to us the original string. But this does exist. So that's going to be replaced with hi. I'm going to do a string replacement if we want to. We can also manipulate strings to do uppercase everything, lowercase everything. You can see how those, like this is all lowercase, but we do dot upper, pass in the string, it will uppercase everything. This is all uppercase, we can lowercase everything. You can see how that all works. Okay. Again, very rare we would ever need to manipulate strings, but if we did, there's this character module that can help us manipulate strings. Very rare that we would need to because most of our data is going to be numerical inside of an NumPy array. All right, so just to recap, we have our arithmetic operations, basic arithmetic between NumPy arrays we can do, pretty straightforward. We can even use our standard, we can use NP add or we can use A plus B, NP subtract, A minus B, multiply, divide. We can all use those basic arithmetic operations. We also have a power function, which will raise things to exponents. These incredibly useful. We'll use these all the time going forward. are the statistical functions like average, standard deviation, variance, median. We'll be able to compute really easily on an array. Okay. All right. So let's go to our next notebook and continue working with NumPy. So go to the 3.04 notebook. All right, now the whole point of this one is to practice accessing data within the notebook, or sorry, within the NumPy array. And truly, this is going to be great because it's going to work exactly the same as a list. We're going to be able to access elements by their position and also slice, just as we did with lists, right? So everything's going to work the same, which is going to be really nice. The one unique difference is that with NumPy arrays, we can have multiple dimensions. So that's where we need to actually be careful, is that if we want to access elements that are in different shapes, like they're in a second row, third column position, how do we do that? And it's actually going to be really easy to do if we just think about it as kind of a coordinate, passing in like an index as if it was a coordinate of this is exactly what I want to access. Okay. All right. So if you take a look at this picture, this is a really great picture to break down a 2D NumPy array. So imagine we had a 2D NumPy array whose shape was 2 rows by 3 columns. So it's a 2 by 3 shape, all right? And we have elements 1, 2, 3, and 4, 5, 6 in our array. So we have 2 rows. Each row has 3 elements. Okay, so a 2 by 3 shape. Now, the element that is right here is at index 0 because it is at the first row. So it's at index 0 in terms of the row, right? So there's 2 rows. So it's either going to be index 0 or index 1 for the row coordinate. So it's at index 0 for the row, but which column is it in? It's in the first column. So it is at index 0 for the column. So this coordinate for this guy would be like if we passed in 0, 0 as the index, right? So if we passed in 0, 0 as our index, we could access that element right there, because what this is signaling is we are at row 0 and we are at column 0. Okay. So with multi-dimensional arrays, we have to be careful about that, is that things can be accessed by their coordinate now, their index coordinate, rather than just a single index like we saw with list, right? With a list, it was just, okay, we can grab something at index 0, index 1, index 2, maybe index -1. But with a 2D array, we're actually grabbing things at their coordinate, right? So row 0, column 0 is, this should give me the element 1, which is this guy, right? If I were to access that element. All right. So let's try accessing. So let's take a look at this guy. This guy is now going to be at same row. So this guy is still going to be at row 0, but it's going to now be at column 1, right? So it's now here, column 1. So we should be able to access that too, sitting at row 0, column 1 index. So this should equal 2, right? This item should be that element 2, okay? And then lastly, from the same example, we have this 3. This 3 we should be able to get from, we're still within row 0, but we're now at column index 2. And this should equal 3. Okay, so in a 2D array, this first entry is what row we want to go to. So imagine like scanning over this grid. What row do we want to go to? Okay, row 0, that's the first row. What column do we want to go to? Okay, column 2, that's the last column. That's the third column here. Let me ask you guys, does that make sense in terms of thinking about it like a grid and a coordinate of how we access elements Okay, so let's see how this works inside of code. So if we let's create some arrays. All right, so let's create some arrays to practice with. So we create a 1D array, we create a 2D array, and we're going to create a 3D array so we can practice accessing certain elements. So if we look at the 1D array, this behaves exactly like a list. In fact, I'm going to write that down. This behaves just like a list, the 1D array. We can access like the third element or the first element, or, in this case, we're accessing the fourth element, which is at index 3, and that returns to us the 4. So we're doing that just like a list. In fact, we can also do the very last element, which would be at the -1 index, and that is the 6. So it behaves, a 1D array behaves exactly like a list, not much different in terms of accessing the elements there. We don't need to worry about coordinates because there's no rows and columns. It's just it's basically like a list, right? Very easy to access things. Okay. So, and for instance, we can add two elements from these positions together. This adds the position 1 and position 0 elements together, and so that ends up being 3. And we can see that because that is 2 plus 1, which is 3. So pretty easy to do. All right. So here is that exact. Here's another picture of everything we just drew earlier, where we're thinking of the elements at these positions as coordinates, right? So the element right here in the first row, first column is at coordinate 0, 0. And then the element right here is at coordinate 0, 1, 0, 2. And then if we go down to the next row, this element would be at row 1, column 0 index, row 1, column 1 index, row 1, column 2, on and on and on, however many rows and columns we have. So we think of accessing elements that way by their row and column index in a 2D array. All right. So for example, let's get the element that's in the first row. So this should be the first row because that is index 0. And this should be the third column. This should be the third column, right? Is the index 2. So if we go back to our 2D array, it should be the first row, which is this guy. And then the third column, it should be a 3. And it is, right? So if we print that out, we get a 3. How do we feel about that example? Do we see how we're accessing it from inside these brackets, just like we would a list, but now it's a coordinate? Do you see that one? Okay. And we also have, now we can grab something from the second row and from the second row, and this, because this is now 1 and this is now the second column. So if we go back to our array, second row, second column should be this guy here, right? Second row is this guy, second column is this guy, so this should be the 5, which it is. We print that out, we get the 5. Okay, that's what that coordinate represents. Second row, second column. All right, very good. I want to take a look at a 3D array now, which is going to be a little interesting in that we're just going to add an extra coordinate to the mix. So with the 3D array, we basically need to know which matrix are we talking about. So remember, a 3D array is going to look like this. We basically have rows and columns, row, column, row, column, row, column. We basically have an array of matrices as our 3D array. So the first coordinate is going to say, which matrix are we at? Are we at this one? Are we at this one? Are we at this one? Okay. All right. So in the 3D example, what I wanted us to see though is that notice that like the first coordinate is going to say, are we talking about this matrix or are we talking about this matrix? So we're actually going to have 3 coordinates. So this first coordinate is relating to which matrix are we talking about? And then once we know what this is, like this 0 would say, okay, we're talking about this first matrix. Then it's the same as usual with these two coordinates here are now what row and column within that matrix are we talking about? Okay, so with 3D, that first coordinate is which matrix is it? Is it the first, the second, the third, the fourth? Because remember, in a 3D array, every element is a matrix. Every element is a 2D array. So the first coordinate is saying, which matrix are we talking about? All right. And then once we know which matrix it is, we can use the next two coordinates to figure out what row and column of that matrix are we talking about. So let's see an example. So look at how this 3D has 3 elements. So if we break this down, this is saying that we want to access within the second matrix. That's what this first coordinate is saying. Within the second matrix, I want to access the element that's at row 0, column 0, right? This is the second matrix. Second matrix. So in the setup, it's like we have a matrix here, we have a matrix here, we have a matrix. Actually, we only have 2 in our example. So this element means we want to look at that second matrix, and we want to grab the element that's at coordinate 0, comma 0. So let's go back to our matrix and see what that should be. So what is the second matrix? It's this guy. This is the second matrix that is within our array. And then we want to access row 0, column 0. That should be this. It should be this 7, right? So row 0, column 0 of that second matrix should be that 7. And that's exactly what we get if we print out this coordinate. We get 7. Matrix refers to row? Kind of, yeah. It's because in a 3D array, every element is a matrix, is a 2D matrix, right? Okay. All right. How do we feel about this three-dimensional indexing? Does that make sense? This is matrix. This is the second matrix, and then this is row 0, column 0 of that second matrix. Finally, I want to mention that we could do negative indexing for all of this, right? So that still applies. Like if we did -3, that would be, third from the last. So if we go back to our 1D array, we could do -1, we could do -3. So -1, -2, -3 should be the 4 here. So we can still use our negative indexing as we would with any list. So that does not change. We can still use minus indexing. We can even use it in the 2D array. So if you imagine there, this is now in terms of the column, because now this is saying in a 2D array, we want to grab the element that's in the second row, but in the last column. That's what the -1 would mean in this case. Second row, but the last column, because we have a -1 index there. So second row, last column, let's go verify that's a 6. So second row, last column would be this guy. Yep, that would be a 6, right? Because this is our second row, and this is our last column is a 6. So that's a nice thing. That's a convenient thing. We don't need to know exactly how many rows there are. If we just want to grab the last one, it's just a -1. So this is second row, last column. And then if you look at the 3D example, we have in our second matrix, the second row, last column again. So we can grab that. So that should be second matrix, but then the second row and last column. So second matrix would be this guy. Second row is here, and then last column would be the 12, right? So there it is. There's that coordinate. Gets us to the 12. All right. Okay. the natural next thing to do is to take a look at slicing. Because we know we can index into a multi-dimensional array, we should be able to slice those as well to extract multiple elements at once. That would be the next natural thing to do. So we're just going to extend everything we know from list slicing. We're just going to apply it here. It has the same exact syntax as what we did with lists, where we do start and end, or start and step just like we did with lists. And so all those rules apply. It's just now, again, we have multiple coordinates to consider here. So we can slice rows, we can slice columns, we can slice in 3D like matrices, rows, and columns. So we have all of those options at our disposal to do slicing. So when it comes to a 1D array, though, that's going to behave just like a list. So when we run this, this should slice just like a list would, where, for instance, we're going to slice starting at 1, going up to 7, but not actually including 7. So 1D array behaves just like a list, behaves just like that. No surprises there with the slicing. We've already learned that before. We can slice just like with the colon there to slice out a section of that list, or of that 1D array, I should say. All right, and so same thing with like having a starting point but no stopping point. Remember what that means is we start here and go all the way to the end of the list. So no stopping index means we slice to the end of the array. In this case, it's an array. So we start at index 5, which would be this string, and include everything to the end, right? So it should be those. We can have a step value. So this would be every third element starting at index 1. So this should be starting at 7 and including every third element. So that would be 4. And then there's really no third element beyond that. So it just would be 7 and 4. Okay, so we can have a step size there. We could do every other element, right, which would be slightly different. So every other element would be 7, 5, and 3. So that's all pretty standard. Nothing that interesting going on there. I think what's going to be more interesting is slicing in the 2D array setup. So if we do that, let's imagine we have a 2D array. Now, what can you guys tell me, what is the shape of this? What is the shape? What do you guys think the shape of this array is? The shape, not the number of elements, but the shape. 2 by 5. Yep. Remember, the shape is number of rows and columns. Number of rows and columns. So it's 2. There are only 2 rows because there are only 2 lists, and we have 5 entries in every list. So it's a 2 by 5. So it's a 2 by 5 that looks like this. 2 by 5 where we have 11, 22, 33, 44, 55, and then we have 66, 77, 88, 99, 110. So we have a 2 by 5 matrix that looks like that. Okay, now let's go ahead and slice. So what I want you to pay attention to is notice how we are allowed to slice in each dimension that we want to. So for instance, here, this means let's take the first row. That's what this means, first row. But let's grab the index 2 column, which is the third column, and go up to the index 3 column, but we would not actually include that. So it would only be this index 2 column. So that should just be row 0, and it should just be this guy here. This is the index 2 column. We technically would go up to this one, but not include this one. So we really only get 33 from that slice. So let me write that down. So here we select the first row, and slice the columns. So we can do that. We can actually do any combination of that we want. We can slice rows, we can slice columns, we can even do, so let me show you another example here is that we can swap this to do, we can grab the first, we can grab the first two rows essentially. Remember, it's not gonna, we basically are gonna go all the way up to the second row, but there's only index 2 row, but there is no index 2 row, so it's gonna include, it should include both. And then we can include, let's do the first column, index 1 column, which actually be the second column, up to the third. So that actually will grab that array right there. So this grabs this 2D matrix right here. Now, why does that happen? It's because we're including both rows, because we're slicing out row 0 and row 1, right? So we get both of those rows, and we are slicing out the first, the second column, which starts here, and we're going up to the third column, but not including it. So we should get these two guys here, which we do. Okay, so if I were to draw this out, I think it'll be clear when I draw it out. So let's draw out the matrix again. We have an 11, we have a 22, we have a 33, we have a 44, we have a 55, and then we have 66, we have 77, we have 88, we have 99, and we have 110. So what we are slicing out is we're slicing out the first two rows. So we should be looking here within the first two rows, but we're only grabbing columns that start at index 1 and go up to index 3, but do not include index 3. So they should be sliced out to really here all the way up to here. Okay, does that make sense on that slice? 0 to 2, 1 to 3. Notice how we're slicing in each dimension. We're grabbing a certain collection of rows and a certain collection of columns, right? We're grabbing a certain collection of rows, certain collection of columns. Yeah, so how we got 33 previously is that we, let me clear this out and then let me undo this. So it was this index that got us there, which was to say we're grabbing something from the first row, that's index 0. So we're looking within this row, and we're going to the second column up to the third, but not including the third, which is what gets us the 33, because the second column index is starting right here. We would go up to here, but we don't actually include that, so we only get the 33. We don't count the first index to start for which operation. No, we don't count the last index. So we don't count, like this one does not get included. The last index does not get included on the right side of the colon for the stopping index. It doesn't get included. Up to but not included, right? Up to but not included. Okay. All right, so we can slice a 3D array as well. So if we take a look at this, we have, again, a situation where we have, let me draw it out again, where we have two matrices. So we have a 2x3, and we have two of them. So we have, inside of here, we have 1, 2, 3, and then we have 4, 5, 6, and that's our first matrice, and then our matrix. And then we have 7, 8, 9, and then 10, 11, 12 as our second matrix. Okay, so that's what our 3D array looks like. And what we're saying is, let's go ahead and take the first matrix. So if we were to build out the slice, we should be taking the first matrix, which would be this guy. That's what this tells us to do, right? This 0 tells us to take that first matrix. And then let's slice the first row That's what this means. So go to the first row, or sorry, index one row, which would be this, index one row, and then every column past the first. So every column past the first index to the end. So we should be slicing out these two guys, which is what we get. We get 5 and 6. Okay. So that's what that, so again, to recap that, this tells us to take the first matrix. This tells us to take the second row and anything past that second row. So here we only have 2 rows. So we're only looking at that second row, but if we had more, it would be all rows past the second row. And then we're looking at the second column and anything past the second column. So in this case, 5 and 6 are in those 2 columns that are past index 1, 5 and 6. Okay. How would you do up to a certain row? You would basically reverse the colon here. So you would do like, if you wanted to go up to index 1, you would just put like, you would do this, right? That goes every row up to that one. Does that make sense? Up to, but not including that. If you want to include that one, then you bump this up to 2, right? So let me make a comment here. This does first matrix, each row past index 1, and then each column past index 1. Okay. So this example we had was a 3D matrix that was like this, right? So it had 2 2x3s inside of it, right? So it had 1, 2, 3, and then 4, 5, 6. And then it had a second matrix that was 7, 8, 9. And then 10, 11, 12. Right, so this is this 3D array that we have. Okay, so with the 3D slicing, what we're saying is we have 3 coordinates we could possibly slice, right? 3 coordinates we could slice. This first coordinate says, let's just grab the first matrix. So the index 0 matrix, which is this guy here. So let's just zoom into this guy. That's what this says. Do we agree on that? That's what the index 0 there means, is let's look at the first matrix. Okay, perfect. Okay. So then within that first matrix, we're going to slice according to these 2, right? So this first one says, let's look at the index 1 row and do everything beyond that to the end. Now, the index 1 row is, let me draw it out, in green is this guy. Do we agree on that? That's the index 1 row. And if we were to go to the end, that's the last row. So in theory, if there were more rows, we would keep going, but that's the last one. That's what that colon says, is go all the way to the end. Do you agree that's the index 1 row? 4, 5, 6. Does that make sense? And we're slicing, the colon means slice to the end, but that is the last row. So that's the only one we would be using. Okay. Now let's look at this last one. This guy says we should be slicing column index 1. Column index 1, and then to the end. To the end. Now, what is column index 1? Column index 1 starts here and goes to the end. So if we were to slice out what we have in this 4, 5, 6 row, where is column index 1? That starts at 5, and it should go all the way to 6. So we should just end up with 5, 6 as the result, which is what we do. We get a 5, 6 as a result. We get that one row, and we get the 5 and 6 out of that row, because that's index 1 to the end of the columns. We could test it out. So let's try it. Let's just insert a 0 to 2 here and see what we get. Yeah, so 5, 6, and 11, 12. Because it's going to do that to both entries. It's going to go to both rows, or sorry, both matrices. So to this one and to this one, we're gonna slice out this and this. Okay. Okay. So don't forget we can use -1 inside of slice. So for instance, what this would say is let's do everything up until the last element. That would be this example here, just a simple example to show you that we could do everything up until the last, which would be -1. And of course, we could use that in a 2D example with like everything but the last column, everything but the last row. We could always slice that way. All right, so we can't forget about negative slices or negative indices. We can always use those whenever we slice. All right, so just to kind of give us a short little quiz here to see if we're following along. Let me ask you guys, what is NumPy and what is it used for? What do you think is the best choice here? Very good. I got a lot of votes for B. B is definitely the right answer. None of the others really make sense for what we're talking about. B is a great choice. Perfect. Good job on that. NumPy is used to manipulate data essentially in these science and engineering applications, especially data science. Okay, what are some of the key attributes of the ND array? What are all the ones that we kind of covered? This one might be tricky, but if you remember them, great. Which ones did we cover? There's some mixed votes for A and B. Let's see what it is. Should be A. So the reason it's A is because there's really no index attribute. We can index into the array by using the brackets to index into it and access elements of the array, but there's really no index attribute that's useful to us. It's more about the dimension, shape, size, data type, item size. Those are definitely important. So A would be the best choice here. That question is a little tricky. All right, which function do you think is used to change the dimension? Which is used to change the dimension of the array? Awesome, you guys are pretty unanimously voting for A. Yes, reshape will reshape it into whatever dimensions we want to, provided that there's enough elements to do that, right? Provided there's enough elements, we can reshape it into that shape. So that's great. Good job. All right. Okay. So let's talk about Pandas. Remember, Pandas is an open source library built on top of NumPy and is used for manipulating data. So it is going to be the thing that we're primarily going to use with our kind of spreadsheet table-like data that we will be working with throughout the course. And it provides, so like NumPy has the NumPy array as the primary data structure that we manipulated previously. Pandas has two really important structures. Basically, it has a what's called a series, which is going to be essentially a fancy array. So it has a series, and then it has a data frame, which is like a fancy matrix. So it's like a collection of series. We're going to talk about both of those and do examples with both of those. But those are the two data types that really make working with structured data efficient. If we could put our data into a data frame, for example, it's almost like having a spreadsheet in Excel that we can do a bunch of operations on. So data frame is kind of like a table. It's kind of like a table or a sheet in like Google Sheets or Excel spreadsheet. That's what a data frame is kind of like. So that's going to be extremely useful for manipulating data, right? Like grouping it, filtering it, doing operations on it, and eventually modeling with it. We'll want to have things inside of a data frame. A data frame will be something we'll use a lot going forward. A series is kind of like a column within so it's basically like a column within a table, or within a sheet. So it's like a single column within there. So a data frame is actually nothing more than just a collection of series, because a table is just a bunch of columns together, right, inside of that sheet. So we'll first take a look when we go through Pandas. We'll first take a look at working with series because we need to know how to manipulate individual columns And then we'll look at the data frame as a whole, which again is going to be that collection of series, collection of columns. So the series and the data frame are going to be our two main data structures that we'll work with. Again, the reason we work with Pandas is it provides us really nice data frame and series objects. It can do a lot of operations on data to help us clean up. It has a lot of really nice like cleaning functions, a lot of transformation functions, a lot of summarization. Like it has group by capabilities, which is really nice. It has a lot of loading and exporting functionalities, which are really nice. So Pandas is really awesome. It's a universally used tool in the industry. People work with Pandas every day. I work with Pandas all the time. A lot of people I know work with Pandas all the time to manipulate data. Okay, so it's a really, really important package in the data science ecosystem. So it has really nice data management and transformations. It's kind of what wrangling means. Has really great aggregations and transformations. Has really awesome tools for reading and writing. As I said, like loading in from a file. That'll be a pretty typical operation for us. Is we'll have like a CSV or an Excel sheet, and we'll actually load that into Pandas so we can do manipulations with it. It has joining and merging capabilities, almost like a table in a relational database. So really nice operations there. It has really nice indexing capability and alignment. So we'll see that as we go along with the series and the data frame. So a lot of nice features, a lot of really nice features that make working with data super convenient and easy. Pandas is really nice. So as I said, it has those two structures. It has the series, which is kind of a one-dimensional array, but the series is like a fancy NumPy array in that it actually has a label with every entry. So instead of just having a positional index, which every array has, right, we can access things by their index. A series actually has a label, which is really nice. So think of a series kind of like a small table where we have basically something like this. We have a label, and then we have our data, and then we have maybe 1, 2, 3, 4, 5, whatever. And then this label can be whatever it is. It can be a string, it could be a number. So the label could just be a simple index like 0, 1, 2, 3, 4, on and on and on. It could be something more fancy than that. It could be like a string label, like category one, category two, and on and on and on. So a series provides us the ability to have an array, but with an additional index, with like a label index that we can use if we need to. So it's a series is really nice in that way. But it is one dimensional, meaning it only has one array, and most of the data we work with is going to be in 2 dimensions. So it's actually going to be with a data frame. So the data frame is a collection of series. So you think of a data frame like this, where it's a series, a series, a series, a series, a series. Every column, each column, each column is a series. But what's nice about a data frame is even though each column is a series, we basically have a unified row label. We have a row label that we will discover is going to be really nice for maybe we want to access certain rows by their label and not just by their index. So maybe some rows are assigned like a string label, a date label, whatever we want it to be. Okay. So our job over the next like our next session, unfortunately, we're basically out of time for today, but our job over the next lesson will be to dive deeper into these two structures. So we're going to learn more about the series and how to work with series, how to manipulate series, load data into a series, all the important functions that come with the series we're going to learn about. and then we'll graduate that information into the two-dimensional version of that, which is going to be the data frame. Okay. So that being said, let's start with the series and then we'll work our way up to extending that into two dimensions. So we're going to start by looking at the series. So in general, as I said, a series is going to have data, which is going to be that one-dimensional array of data, and it's going to have an index. So, and again, that index can be fully customizable. It can be by default, just the standard positional index. So just like we would see in a list or in a NumPy array, it would be 0, 1, 2, 3, just like you see in this little picture right here. This would be kind of the standard like positional index of the series. And then this is your data here. That is the underlying data of the series. What's really nice about Pandas is it actually builds on top of NumPy. So this underlying data is actually stored by Pandas as a NumPy array. And so because of that, series kind of inherit all the nice properties of NumPy arrays in the sense that they can do all the same arithmetic. They can be manipulated in a lot of the same ways. They have a lot of the same attributes, like a shape, and a reshape function, and a transpose, and all these things. So that's really nice about really series and data frames. The underlying data is all built on top of NumPy, which is nice. So you can create a series out of a list. You can create it out of a NumPy array. You can make a series out of a tuple. You can make a series out of a lot of different data. It's just that one-dimensional array that has that special kind of index to it that we could customize. So we're going to see different examples of building a series and manipulating a series. The other thing I should mention is that there's no restriction to the kind of data that the series can hold. So it can hold objects, it can hold strings, it can hold integers, floats, really all of those. And it can even be mixed. So just like in a list, we would see, we can have strings, we can have floats, we can have those kind of things. All right. So let me show you an example. And the first place we'll start is by importing pandas. And this is just like we did with NumPy. Remember, all of our NumPy examples had import NumPy as MP. All of our examples here with Pandas are going to be import Pandas as PD. This is something we're going to get super used to as we go along, is the fact that we see PD. That instantly should tell us we're using Pandas. That's the industry standard. So industry standard alias for Pandas is PD. So if you're reading some code and you come across a PD, that is just short for Pandas, and that's the standard in the industry. So everyone would understand you if you were using PD there. So we import Pandas as PD. Look how easy it is to make a series. We just start with a list. So we just have a regular list of 1, 2, 3, 4, 5, just those 5 numbers. And we create a series by doing pd.series, and we pass in that data as an argument to the pd.series function. This constructs a series, and we store this as a series object. So what's interesting about this is when you first create the series, if you don't specify an index, so if you don't specify the index, Pandas uses the default positional index. So it just assumes that the data is going to be indexed by position. So that's just, this 1 would be at the 0 index, this 2 would be at the 1 index, this 3 would be at the 2 index, and on and on. So it's just the standard, just like we learned how to slice, so we learn how to access elements by their index. That's all we would need to do to access these items of the series. So that's if you don't specify an index. But I want you to see this example here where we use the same data, but now we actually customize the index to be, special labels for every item. So for instance, 1 would be indexed with A, 2 would be indexed with B, 3 would be indexed with C, and so on. So the way we do that is when we create the series, we actually explicitly pass in an index array, which signals that these elements are going to all this data is going to be indexed by this specific index. And then why that's relevant is because when you print out this series, you can access things. Look at how down here we actually access things according to this B index. Or obviously we could pass in a C or a D or an E, and that's how we would access things. Okay. But in the series that does not have that just has the default index, notice that we can access things by this numerical just positional index. So we could access the first thing, we could access the second thing, and then this would access the third thing, which is at index 2. Okay. So and by the way, you can combine these. So you might be wondering, well, we have some data and we have an index. Why don't we just map those two together? And we can. So if we use a dictionary, we can actually combine those two together and say, okay, A should map to 1, B should map to 2, C should map to 3, D should map to 4, and E should map to 5. And we can create a series from this dictionary. So you can actually build a series from a dictionary. And what this will do is it will treat all the keys as the index values, and it will treat all the things that they map to, the values, right, will be the data. That'll just be the data, right? All of these 1, 2, 3, 4, 5 will be the data, and this E, D, C, B, A will be the index. Okay. So when you do this, when you use a dictionary, keys become the index and values become the data. We can use a dictionary. We can just use a regular list. You can also use a NumPy array. It doesn't have to be a list. You can use a regular NumPy array to create a series. So all the code here is just creating a series. Nothing that interesting going on so far, just creating a series. And I want you to see if we were to print out, I'm going to add this in here, just one little cell below this. I'm going to print out the series so you can see it. Let's print the series. You can see that it's going to have, notice how the series prints out with kind of two columns. This is indicating that this is the index, 0, 1, 2, 3, 4, right? It's the positional index of this regular series. And then here's the data, the 1, 2, 3, 4, 5. Okay. So you see both of those. Let's print out this series with index. And let's print that guy out. And you can see now that the index is A, B, C, D, E. That should make sense. This is kind of like an Excel column, isn't it? Because Excel, if you're familiar with those spreadsheets or even in Google Sheets, right? Every row has this index A, B, C. Like you're dealing with cells that are in row A, B, C, D, and on, right? Let's take a look at a series with dictionary. This should be series from dictionary. And we get the same thing, the A, B, C, D, E, 1, 2, 3, 4, 5. What is the difference between dictionary and series? Well, a series is a different object. A series is a Pandas object, and therefore it has certain functions available to it, like finding an average, plotting, finding a mean, or sorry, finding a median. Like it has a lot of built-in functionality as a series that you don't get as a plain dictionary. Does that make sense? Like you get a lot of, we're going to see this in Pandas, you get a lot of functionality if you're a series. You get a bunch of statistical functions that can be easily ran. You can do a bunch of summarization on that data. You can do plotting against that data relatively quickly as a series versus as a plain dictionary. It would be object. Try it out. So try it out. If we did, so let's say we did a string inside of here. So let's make that 3 a string. So we have integers and strings. Let's now print this out. They basically, do you see how they're all objects, which means that Pandas would actually convert everything to a string. Once it sees one string, it's going to treat all of these as a string. So if you see a data type as object, that likely means everything is a string, because string is technically an object. So we can convert that back to an integer, rerun that, it goes back to an integer. Okay. All right, let's see what we get. So I think it's a valid question. What's the difference between a dictionary and a series? Because it's getting at like what's what do we get by having a series that we wouldn't have if we just had the dictionary? And it turns out that we get a lot of different functionality out of the series that we wouldn't otherwise have. So we're going to see some of those functions. The first couple of functions I want you to take a look at are right here, which are the head and tail functions. So what these do is they give you a view or essentially a copy of the first n rows. So whatever value you put in here, you'll get those first few entries. Head goes from the top, so it goes from the beginning of the series and does the first however many rows. So if you don't put a value in there and you just have this, the default is 5. The default is the first 5 entries. Okay, if you don't put anything in there, you could put a value in there like 10 and you'll see the first 10, right? Or you want to see the first 3, you put in a 3. So head gives you that copy of the first 3 elements, and tail gives you, on the reverse end, it gives you kind of that slice. Think of it as like a shorthand for a slice. It gives you a slice of those last 5 guys. So this is almost like this is similar to doing series, and then we were to slice out the like last 5 entries. Think of it like doing something like that. And then this is similar to series, and then we do the first 5 like that. Okay, so head and tail, very interesting functions that actually we will use quite a bit with DataFrames, particularly to just get a quick view of the first 5 rows and last 5 rows with the tail. So if we were to run this, we could print out that. So we could print out the first n rows, and we get the first 5 entries, right? We could actually do the first 2, and that would just give us the top 2, right? From the top. Now we could print out the last 2, let's say. So print last n rows, and this does the last 2, right? All right, so head and tail, pretty straightforward. They give you the first, either from the beginning, first 2, or from the end, the last 2. Series have a shape to them, which makes sense because the underlying data is a NumPy array, which also has a shape. Now let me show you what the shape is. Let's print the dimensions. Print that, and let me comment that out. So as you can see, this series only has 5 elements, and it's basically one-dimensional. So even though it has an index, it is one-dimensional. It doesn't have rows and columns. It basically only has rows, as 5 rows of data. It's just a single column, essentially, right? It doesn't have multiple columns, so we just say it has a shape of 5. It's just one-dimensional data, right? So a series is always 1D, one-dimensional. Okay, it's always one-dimensional. All right. Now let me show you a really awesome function called describe. Now this is a cool function to give you a bunch of the statistics, basically give you a summary, a descriptive summary of your data. So when you have, this is the advantage to having your data in a series, is you can easily run a describe function and see how it's series.describe. What this is going to do is give us a quick descriptive statistical summary of our data. So it's going to print out the mean, max, min, median, and then like various percentiles of the data. So it's going to give us that quick view of all those statistics, which is really nice. So let's see that. So if we print out the stats, we can see what everything that gets produced. So you can see here we get this summary. This is our descriptive summary. We get a count of how many values are in the series. We know that there's only 5 because we created it with only 5. That makes sense. The average is 3. That also makes sense. Just the numbers 1 through 5. So the average is 3. The standard deviation is 1.58. The minimum is 1. 25th percentile is a 2. The median, which is the 50th percentile, is 3. That makes sense. The 75th percentile is 4. Also makes sense. And the maximum is 5. That makes sense, right? It's just 1, 2, 3, 4, 5 is our data. But that's extremely useful, right? To get that quick, you just run one function, you get all this summary of the various stats of that data is pretty useful. And it's actually going to be incredibly useful to do when we have data frames. The describe is going to be something we'll use quite a bit on an entire collection of series in the data frame. Okay. So if we want to get all of the unique values of the series, we can run this unique function, which will give us all the unique values that exist within the series. So if we print this out, this should be the values 1 through 5 because we don't have any duplicates. They're all unique, right? So this should just give us all of those values. Clear that out, and it does, right? So 1, 2, 3, 4, 5. This basically gives us a list or an array essentially of all of the unique values if we run the unique function on the series. That's another advantage, right? If your data is in a series, you can quickly get all the unique values. If it's in a dictionary, that might be harder to do. Might be harder to kind of sort through it and try to deduplicate it. So unique. We can also get the number of unique. So if we just stick an N right in front of that unique, N unique gives us a count. So this should be 5. This should tell us how many unique values there are. We should be able to print this out and see that there are 5 total unique values, right? Just the numbers 1, 2, 3, 4, 5. Fantastic. So we can keep going then. So just like with NumPy arrays, we can do arithmetic with series. So we can add series, we can subtract series. The catch being that it can be tricky to do arithmetic with series when they do not have the same index. Let's see how that plays out. So these series have different indices. Remember, this series was built with the default index with 0, 1, 2, 3, 4, 5. Sorry, 0, 1, 2, 3, 4 as the indices. And this one was built with the indices that have the character indices, right? A, B, C, D, E. So it might be a question of like, what actually happens if we add those series together? Like the data, if we were just looking at the data arrays, those make sense to add together because they're just arrays that are the same shape. So it makes sense to add their elements together, and that should be a very natural thing. The question is, what happens with their indices? So let's see. Let's see what we get. Let's print that out. So it turns out that Pandas doesn't know what to do with that because they don't have the same indices. So this is just a warning that you can add together series that have the same indices, no problem, and the resulting data is just going to have that same index as the first two. But when you add together, these have different indices. So just to give a warning here, we have a warning. These series have different indices. We can't add them together. Okay, we can't really add them. Now we don't get an error, but we basically get an undefined result, right? We don't know how to add things together because and look at what the new index is. It thinks it's adding them two together. We get 0, 1, 2, 3, 4, and then A, B, C, D, E. It's just a mess, right? It's just a mess. It doesn't really make sense to do. So if you're adding series together, or doing arithmetic in general, multiplying, subtracting, all those NumPy arithmetic operations we learned last week, you can do them as long as they share the same index. The index order matters because that dictates the position of elements, right? The relative position of elements is determined by the index. Okay. Now I want to show you something really cool as well, which is the ability to basically apply a function to every element of the series. So if we have a series, we can manipulate every element of it at once by using a special function called apply. So apply does exactly what it sounds like. It applies a function to every single element. So the input to apply is going to be a function. So this is where the input, or I should say the argument to the apply function is a function. And we have a special function here that we have not seen before called a lambda function. So we haven't seen this before. What this is, this notation here actually is declaring a function. Lambda declares a function without having to use def. So it's a shorthand in Python to define a function on one line of code. And what it means is this is defining a function very similar to def, and it's saying we have a function that has one argument, and we take that argument and square it. So that's a function. It's saying take whatever argument is input to this function and square it. So what that means is on this series, we're going to take every element, because those are the arguments to this apply, and we're going to square them. So that's what this means. So this has the effect of squaring each element, because it's star star 2, remember, is the second power. So this will square each element. That's what apply means, is apply some function to every single element. And this is we're defining a function here to say, take every argument and square it. That's what that function is. Now, do we have to do it that way? No. The alternative to doing this is if we quickly came up here and said, let's define a function called square, where we take any x and we return x star star 2. That's a function really easily, right? That's a function that squares the arguments. And so instead of doing this, we could alternatively do the same exact thing, but instead of passing in this lambda, we could pass in our square function there. Okay, which says we should be taking the elements of x and the elements of the array, sorry, the series, and we should be squaring them. This is the same thing. This is the same as above. It's the same thing as doing this. Lambda is just a shorthand for just doing def and returning this argument. This is your argument to the def, and this is what you're doing to that argument. You're squaring it. Does that make sense on the lambda? That this is equivalent to, this is exactly equivalent to this lambda. Exactly equivalent to that lambda is just a shorthand for this function. Roberto, yeah, it's shorthand. So lambda notation is you declare lambda as a keyword, and then you write down your argument. And you can actually have more than one argument. So you could do x, comma, y, comma, z if you have 3 arguments, let's say. In the series, we only have one argument, which is every element. That's the intention, is to apply this function to every element. So there's only ever going to be one argument. So we have one argument, and then we have a colon, and then we have our math to say, what are we going to do with the argument to return? So the colon is like shorthand for returned. Lambda is like shorthand for def. So yeah, it's always def returned. Okay. So the other thing I don't want to get away from either is this notion of apply. This is a really powerful idea. This is a nice shorthand to say, I want to take every single element of this series, and there could be millions of them. There could be millions of these elements. I want to take every single element and apply some function to every single element. And this is the way to do it. So apply is really powerful. We're actually going to use apply quite a bit as we move along and work with DataFrames. Apply will be really useful to apply a function to every column or specific columns that we want to transform. We will use apply. Okay. Let's make sure this works. Let's print out the squared series. Let's do both. Let's do the lambda version first. Let's uncomment that. So see how this, let me comment this out so we don't try to print that out again. Rerun that. Okay, so see how it ended up squaring everything? So there we took the apply and gave it the lambda function and ended up squaring every element all at once. So everything gets squared. And again, like that's we could do it this way. Alternatively, we could run it this way and it should work the same. There it goes. So the same result, whether we use the traditional def function definition or we use a lambda, either way, get the same thing. Okay, cool. So no questions on apply. We will use apply quite a bit whenever we want to make sure to transform all elements of a series. Remember, in the apply, every element of the series is going to be applied to this function. Or I should say this function is going to be applied to every element of the series. So apply will transform everything in that series according to this function. Now, the kind of the more targeted way to replace values is the series dot map. So this is a little less this is basically more targeted than apply, more targeted than apply. It's a replacement of values within the series. So essentially, what we're doing here is we're going to take our series, replace this data with this data here, replace this two that's in our series with this data here, and replace this with this data here. And so you can choose which data values you're replacing in the map. You don't get to choose that with apply. Apply is going to apply that transformation to everything in the series. All of it's going to be mapped with this function, whereas map is going to do a specific replacement. So map can be useful like if you only want to transform certain data values. So if you want to find out where there's a zero or a one or a two and replace those with certain values, you can do this kind of does like a find and replace. You think about it like that, find and replace. So let's see what the result of this is if we print the mapped series. So you can see that 1, 2, and 3 get replaced, but we actually don't have any replacement for 3 and 4. So those get mapped to NaN because we don't have a specific replacement for them, and their original data was integers. So we now have strings, and we had those integers. We don't know how to replace those, so those get overwritten with NaN. So the thing you have to be careful with a map is you want to make sure you basically cover all the cases that you have within your series. So if you have, 1, 2, 3, we know that the other data members are a 4 and a 5. We should probably pick some candidates to replace those with. So if we have 4, we want to map that to 4 probably. And we had a 5, we want to map that to 5. So again, this is a more specific find and replace. So now all of that data has been replaced, and we actually have those replacements that we can now make. Okay, so map will map these data members to this value, and that will happen for every copy of this. So if we had a bunch of ones, they all would be replaced with 1. Every instance of 1 would be replaced with 1, not just like the first one, but every instance. All right. Questions about map. Do we see how it's different than apply? Apply is going to take a function and apply it to everything all at once. We're not picking and choosing what to replace something by, which is what we're doing with map. All right. Very good. A couple more examples. So beyond applying transformations or replacing certain values with something, we can also do things like sorting. So this should make sense to us that we can sort. So by the way, the default sorting is least to greatest. So it's an ascending sort. If we want to turn that off and do a greatest to least, we have to go into here and turn that we have to do ascending to false. Okay, so if we do ascending to false, let me jot that down. Ascending equals false, we'll do greatest to least. So this will sort our data. So we have 1, 2, 3, 4, 5 currently from the beginning to the end of our series. If we do this sort, it's already sorted, but if we do a greatest to least, it should put it now as 5, 4, 3, 2, 1, right? It should now be sorted like that. So let's go ahead and print that out to be sure that it got sorted properly. So print sorted series. And you can see now we have 5, 4, 3, 2, 1. And you can also see the indices now change to where this is now 4, 3, 2, 1, 0 because the data retains its index. So we're sorting the whole series. The index also gets sorted along the way. So that's something to be aware of is when you're sorting the series, you're sorting both the data and the label. That label comes along with it. Or I should say the index, not the label, the index. So if we were to keep this as true, which is the default behavior, it would just be how we had it. It was already sorted, right? 1, 2, 3, 4, 5. So in order to do a greatest to least, we have to put this to false, ascending as false, and that will be the greatest to least sort. Does that make sense? Any questions on the sorting? That's valuable, right? That should be a natural thing we can do is we can sort the series. You can do that in any spreadsheet, right? You can sort a column. So we better be able to do that, right? That should make sense as a basic operation we should have is the ability to sort a series. Okay, very good. Let me move on to a couple of really important things that deal with missing data. So we have a simple function here to check and see if there's any missing values, which is series.isNull. So this will check and see if there's anything missing, meaning that we have a blank value or an NaN value in our data. So we're missing something for that index for some reason. Maybe we loaded in this data from a spreadsheet and we're missing a value. We want to be able to see if we actually are missing anything. Let's see what this returns. So you can see what this does. This goes through and checks every entry and sees if any of them are true or false. If it's true, so this will return true for missing entries. So if there was a true here, that means that slot in the series has a missing value. It has an NaN. It was blank. Essentially, it has an NaN. It doesn't have a valid value there, so it's null. So this will give us a check for every entry, and more importantly than that is maybe we want to know the total of them. So let me show you an additional example. Is we can see the number of missing values, which is if we just tack on a sum. If we just tack on a sum there at the end. So if we take this and total that up as an aggregation, we can get how many missing values there are. So this should be 0. There is no missing data in our sample series, right? It's just 1, 2, 3, 4, 5. There's no missing numbers here. So, but we could confirm that this should be 0. So you see here we get 0 as the number of missing values. There is no, so both of these are valuable. This is valuable to see which slots are missing, and we could have a place to see how many are missing. Can you insert a null? Yeah, you can overwrite. So we could overwrite a value to be null by doing something like series 0 equals none. That would overwrite the first entry to be a null value, none. Does that make sense? This would overwrite the first entry to be null. Yeah, none. The Python equivalent is none. Yeah. By the way, if we do that, look how many are missing now. After we do that, look how many we get missing now. We get one, right? So we overwrote that first item. Now when we do this, we actually get one. That should make some sense to us, right? Yeah, it's because count is usually counting the number of a specific data value, like count how many zeros there are, count how many ones there are, count how many twos there are. In this case, we're getting a total. That's what sum really represents, is how many total nulls do we have? So we're thinking of count a little differently in this context. Like it's the count how many of a certain data type we have. In this case, we're checking is null, which gives us like a Boolean 0 or a 1, and we're totaling that up. So if we have all zeros, the total, if we add a bunch of zeros, we get 0. All those falses are like zeros. So we total all those zeros, we get 0. In this case, when we fill in a null value here, we get 1 missing value as the total, because now there's a true. There's actually a true sitting here, which we could see if we printed that out again. If we printed series.isNull, there's now a true sitting here, which is a 1, basically. Python treats that as 1. So we total that up, we get 1. All right. So you may be asking, well, what do we do if we have a null value? Well, luckily there is a nice function to replace null values with a default value, and that is the function fill NA. So if we're missing something, we can go ahead and just fill it with a specified value. So in this situation, we have a null here. Let's fill it with a 1. Let's go ahead and fill it back in with a 1, because that's what it used to be before I took it out and said it was none. Let's go ahead and fill that NA with a 1, and then let's print the filled series. So now this should have that null value filled in with the 1. And there we go. So we have 1 there, and all the values we have no more null values. So fill NA will fill back in, it will fill in any missing values with a default. Okay, so pretty convenient. If we identify anything missing, we can fill it in, right? We can fill it in with a default, with this fill NA. All right. So what I wanted to show you next is the ability to essentially filter a series. So we can put in conditions to basically filter out different rows or different entries in the series. And I want to show you how to do that very easily, which are just going to use our comparison operators to basically generate some filters for us. So I want you to see the syntax of that. So we have this sample series that we built from this fake data. We have index A, B, C, D, E, and we have that data mapped. We have those values mapped to this data 10, 20, 30, 40, 50. Okay, so some fake data there, and we build our series. So we have a new series sitting here. I want you to see the syntax of how we can generate a filter. So generally, we can build filters by using the comparison operators and the brackets for value selection. So remember, we typically will use brackets to put an index in there. That's typically what we're used to doing, right? We put in a 0, or we put in an A, or we do a slice. We can grab elements that way. So think of doing that, but with a comparison filter now. So this would, like, for instance, this says we want to pick only elements of the series that are going to be bigger than 30. So we have pretend like we were going to pass in an index here. So we have series bracket, because what would typically go here would be something like this, right? That would typically select something from the series. It would select the first item. Or we could slice it to be something like that, right? We could slice. So that's how we select things. But in this case, we're actually going to do a filter, which is a condition to say, I only want to keep items that meet this criteria. That's the filter, okay? So inside the brackets is our filter condition. So it's basically we only keep elements that meet the filter. So let me show you what this should be. If we're filtering out to say, only give me items from the series that are bigger than 30, we should only get this part of the series remaining, right? Everything else should be filtered out because 10, 20, and 30 are not bigger than 30. They're all less than or equal to. So these guys should be left out, and we should only be seeing this as the result of that filter, right? We should only see those guys as the result of the filter. So let's make sure we do. Let's print out this selected greater than 30. So here it is, right? We only, oh, it already did it for us. So it already showed us this. The selected greater than 30 results in only those two parts of the series remaining. So that was an effective filter, right? To only give us the items that are bigger than 30. So that's how we filter. And so all we have to do is if we want to do other kinds of filters, we just have to do other kinds of comparison operators. So for instance, let's pick all the items of our series that are exactly equal to 20. How many of those do we have? We really only have one. Only this guy exactly equals 20, right? So when we do this filter, this should ignore everything else and only give us this item out of the series. So our series is going to be filtered down quite a bit to only this element. And we can see that. So when we come down here, the part that gets printed out there is going to be only that part of the series, the index B and the 20, the data 20. Right? So that is that filter. Not equal to 40. Which items of our series are not equal to 40? That's what this filter really is asking. So we go to our data and look at it. We have a 40 here. Which parts of the series are not equal to 40? Well, it's basically everything else, right? This is not equal to 40. This certainly is, this is, and this is as well. It should be everything but that 40 should be filtered out and returned back to us. So if we take a look at that, what is not equal to 40, we get everything else in the series, 10, 20, 30, 50. So that was an effective filter, exactly what we were hoping for. Okay, so greater than 30, equal to 20, not equal to 40, those are all valid filters. And I want you to see that syntax where this is inside of the bracket. It's basically replacing an index. They say, I want to pick something based on a condition, not based on an index, okay? Based on a condition, okay? So I'm going to show you some other examples of conditions. For instance, we can actually combine conditions using logical shorthands. So this is multiple conditions we're combining. It is greater than 20 but less than 50. So this is greater than 20, and this symbol here we haven't seen yet is the shorthand for and. It's the Boolean and symbol. So this ampersand symbol is shorthand for and. So this means that we're looking to filter out data that is bigger than 20 and less than 50. So multiple conditions combined. Now we could do or. There's a shorthand for or that we could use in here, and that is the pipe. Basically, the pipe symbol is shorthand for the logical or. So we could have a pipe symbol here. Oops, I don't know what happened. Yeah, we could have a pipe symbol here, which would signal that we would be looking at this condition or this condition. So things that are less than 50 or bigger than 20, which would really be everything. So it's kind of a useless condition, but we can have that one. So does that make sense? Those are just shorthands for and or. And so because we can filter on conditions, there's nothing stopping us from filtering on multiple conditions that are logically combined. So greater than 20 and less than 50, well, what should that be? Should really just be these guys here. Those are the only things that are greater than 20 and less than 50. We should just get those two out of it. So if we went down and looked at it, we would get these two guys as the filter, which makes sense. So we can do that. That's a valid way of filtering. You can also, what's really cool is you can also filter based on a specific list. So you could say, I only want to keep values that are inside of a specific list. So this is where we use the is_in function. So this is a function that gives a Boolean true or false if the members of this data are inside of this exact list. So what this means is we should really only be keeping values that are going to be 20, 40, or 60. Only those three numbers should be kept. So if we go back to our data, we only are going to keep these and only these two. There's no 60. So nothing, 60 wouldn't match to anything. So we're really only going to keep the 20 and the 40. So is_in is a special kind of filter that only retains values that are actually in this collection. So if we did this by list, we only get those two, only the 20 and the 40 remain. You can do string filters. So for instance, if we had our data was all strings, we could filter based on the string starting with a B. So that's actually a very specific condition, right? So we want to filter all strings that only begin with B. So in this case, that would just be the banana, should be the only one that is returned, the only entry that's returned. Everything else starts with A, C, D, or E. So that's possible. Okay. So what's really important to know is that loc allows us to pass in basically the labeled index. So our index that we have, which is either the default one or the one we provided when we created it. In this case, we created a series that had a index with A, B, C, D, and E. So loc will allow us to select multiple of those indices, almost like a slice. So loc allows us to use our index. So we use our series index to select data. So we're selecting A, we're selecting C, and we're selecting E. So we pass those into a list inside of the loc function, and we can pass in as many as we want. We can pass in just a single value. It doesn't need to be inside of a list, but loc is pretty typical for selecting multiple elements using the index. So that's the key thing to remember about loc. It uses the index of the series to select items, and you pass in typically a list of those indices that you want to pick. So we're picking the elements at A, element at C, and the element at E. So go back to our data. That should be 10, 30, and 50. So if we go back and look, that should be at those three guys, right? A, C, and E, 10, 30, and 50. Okay, so loc uses our indices. And now, how is that different than iloc? So iloc always uses position. So this always uses position regardless of index. So even if you have a really nice index that you've provided, like a date, or in this case, A, B, C, D, E, we can ignore those and just use their position within the series, which is what iloc does. It just uses the numerical position of the elements. So for instance, if we want to pick the very first item, we know is at index A, but in terms of its position is really just position 0 within the series, right? Position 0 is the very first item, even though it has an index A. In this case, we're picking the positions 1 all the way up to 4. We're doing a slice. We can do that. We can slice based on position. So that's okay with iloc. So remember, iloc is different than loc. Loc uses the index, whatever index we have defined, which is, it can be special, right? It can be dates, it can be strings, it can be objects. That index can be whatever we define it to be. iLoc will always use numerical positions, always. So you would never put in, like, this would be invalid to do this. This would give us an error. We can only use this with loc because that is the index of the series. But the positions are just the data positions within the series array. So we have just a natural ordering that always exists of our data within the series, and we can use that with iLoc. Okay, so they're very similar. They're both used for selecting data, but they use different indices. Loc uses the defined index of the series, and iLoc uses the numerical position of the elements. Okay, so we see, by the way, this is 1 all the way up to 4. So what is at position 1 would be this guy, even though it's at index B, even though it's at index B. And what is position 4? Well, this is 0, 1, 2, 3, fourth, the fourth element of our data. So that would be all the way up to 50, but not actually including 50. That's the slice. So it should be 10, 20, 30. What is 4? It's a position. It's just this would represent the fourth element in the data, which is this is the 0th element, this is the first element, this is the second, third, and this is the fourth, right? Numerical position. That's what iLoc uses. Now, what data do you, if you were to ignore this index for a minute, this is the index, and just think about this data's positioning from left to right, what index would we say, or what position would we say is the 10 at? What position is the 10 in the array? If we were to just think of it as a list, let's say, what position is that? Right, it's position 0. And what position is 20? It's at position 1, right? And so 30 should be at what should be 30? 2, perfect. 40 should be 3, and 50 should be 4. So what I was saying with those examples is iLoc uses these positions while loc uses the index. Does that make sense now? When you think of it this way? iLoc uses those positions of the data, the relative positions of them, to select things. So when we say 1 to 4, that's this slice, right? That's this slice of the data. Not including the 4. So it's really this slice. Okay. So what I wanted to show you guys is that was the end of this notebook, but there is some extra practice. I encourage you guys to try this out on your own. So this is your own practice here at the end. Try this out on your own. So this 4.01 notebook, try this out when you get a chance to do some extra practice accessing and manipulating this data. Okay. So you have some example arrays here. You'll build some series and go through and do some selecting of some data using the different methodologies we just showed with loc and iLoc, and picking different indices and things like that. So this will be some extra practice for you. What I want to do now is go over to talk about the data frame. So we've talked about series so far. We have some different functions on a series. Most of these are going to carry over exactly into the data frame in the 2-dimensional aspect. So everything we've been doing, mostly been dealing with 1-dimensional data, but we are going to deal with 2-dimensional data. Let's go over to 4.02 now and talk about the data frame. Okay. So if you have a moment, pull up the 4.02 notebook. We're going to go over to that and talk about the data frame now, which is going to extend everything we just learned over into the 2-dimensional data with rows and columns now, which is going to be the data frame. You guys have this notebook? And go over to the 4.02. So let's remind ourselves what a data frame is. So a data frame is now going to be our 2-dimensional extension of the series, where we are going to have a tabular data structure, meaning it's going to look more like a table. We're going to have rows and columns to deal with now. And what's going to be really interesting is we'll actually have multiple indices to worry about because we have multiple dimensions. So imagine if we had these two series of apples and oranges. So we had a series called apples. It has this data 3201, and it has just a natural positional index of 0, 1, 2, 3. So nothing that interesting. We have another series over here called oranges that has data that looks like 0, 3, 7, 2. It also has the same index of 0, 1, 2, 3. That's fine. That's just a default index. Now, what we can do is concatenate these into a single data structure called a data frame, where now these two series actually form columns in this table structure. So now we have more of a table, which is a data frame that contains one row index. So this is called the row index here. So it has a row index, which is row 0, row 1, row 2, row 3. So we can think about the data at a row level. So we can say, okay, this is one row. This is one row. It's very much like a spreadsheet, right? This is one row. This is one row. We have that. And then we have data at the column level. So we have these, what are known as the column index that we have here. So the column index just allows us to select columns based on those names. So we can always go into this table and grab the apples column. We can grab the oranges column. We could grab the apples and oranges columns together and pull back multiple columns. We have that flexibility with a data frame, just like you would in a spreadsheet. You can pick data at a column level as well. So you always have that flexibility in a data frame to select rows, to select columns, to select rows and columns. So that's something we're going to learn how to do, is select data based on where it is, what row it's in, what column it's in, select sections of a data frame, or rows and columns. What will be the merge title? So that's up to us as a variable. The title of the data frame is not that important. It's more when we add these two columns together, we get a single data frame with two columns, and we have a row index and a column index. Oops, this is the row index. But the name is whatever we want to call it. We can label it whatever we want as a variable. Like we could say this is our fruits data frame. We just call it that. Fruits data frame, which has apples and oranges as columns. And it has 4 rows, right? It has 4 rows of data and it has 2 columns. Basically, the shape of this is a 4-row, 2-column matrix, right? Think about this as a NumPy array. That's what that is, right? 4 rows and 2 columns. Okay. So one thing to point out about this so I told you guys it has a row index and a column index. So those will be really useful for when we want to select data from the data frame. But the other thing is there's no restriction on the data types in the data frame. So the data types of one column can be completely different than the data types of the next column. So like this column could be all strings. This column could be all floats. That's totally fine. There's no restriction there of what the columns can be. They can be mixed data types. That's totally fine. There's no restrictions on the data types. Oh, that's just random data. It's just random. It doesn't represent anything meaningful. It's just random. We just wanted some values to be in there. Yeah, they can be different for each row. Yeah, they can certainly be like they generally could be if, let's say I had like this data type was a string, so this column was a string, this column was a float, then I'm going to have like within this row this is going to be a float, but this is going to be a string. So yeah, the rows can be different. If you have mixed data types, the rows are going to be different. So the most meaningful example I can give you is most spreadsheets can be loaded into a data frame structure. So if you take any like CSV or Excel sheet, they can be loaded into a data frame, and then we can do all of our analysis on that data frame. That's typically what we're going to do with the data that is inside of a comma separated value file, a CSV file. We'll load that into a data frame. We're going to practice doing that quite a bit. Okay. All right. So before we get to those examples, let's talk about how we can create some example data frames using our code. So here we are going to import Pandas as PD. And one of the most common ways creating a data frame is from a dictionary. That's one of the most common ways of creating a data frame is from a dictionary. Now, why from a dictionary? It's because these keys in the dictionary are actually going to be our column names. These are going to be our columns. The keys are going to be our columns, and then the data within those columns are going to be inside of this list. Okay, inside of each of these lists. So I'll show us that data frame in a moment, but this is pretty common. So the keys become the column indices, and the data within the columns are the values, which are the lists. So those lists become the data within the columns. So the name has these three strings, the age has these three ages, and the salaries have these three integers. So let's go ahead and see that dictionary. So it actually looks like this: name, age, and salary. It looks like this. This is our data. It has 3 rows. That's not surprising because it has every column has 3 entries. So it ends up being 3 rows. And here's the name column has Alice, Bob, and Charlie. The age column has those ages that were in that list. And the salary column has those 3 there. So using a dictionary is one way of building a data frame. It's a very common way. So we can do that. The other way is to use mixed type lists. So basically where you define every row. So creating a data frame from lists is possible, where we have a list for each row. So we have the first row, we have the second row, we have the third row, and we actually manually supply what the column names should be. So this is all the row level data, and this is the column name. So we can actually build a data frame off of that using pd.dataframe. We pass in our row data, and we say, here's what our column should be labeled. Here's the column indices. So these are the column indices. We say, here's what our column should be. Here's our row data, and that builds the same data frame. Builds the same exact data frame as we had before, just doing it not in a dictionary, but in a list of lists, essentially, right? All of our rows are utilized here as like this. But this does build the same exact data frame. All right, same thing. We can use NumPy arrays. Now this is a NumPy array. This is the 2D array of our rows, right? So here's the first row, here's the second row, here's the third row, and we can give it our column indices as well. So again, the NumPy array data is our rows of the data frame. So this data formulates our rows, and we're passing that in to build our data frame. So this should be the same exact data frame that we have from before, just using NumPy arrays to build it. Okay. All right, let me give you a more practical example that will be realistic to a lot of the use cases we will see over the course of the program when we're loading in data. And this is one that's used all over the industry. People use it all the time. I use this one nearly every day, is reading data from a file. So if you want to read a CSV file, you use the pd.readCSV function. So read CSV, and all you have to do is pass in the file path. So now this path looks a little wonky because I am inside of Colab and I had to mount this file within my drive. so this data is in my Google Drive on Colab, but generally that like if you're in VS Code, this would be a path to the data that is somewhere on your computer. So this is just a file path to this CSV file. Okay. And by the way, you guys should have this data. If you go into your, let me show you where it is. So if you go into your LMS, let me log in. Do you guys have access to the data sets? It should be from your reference materials. It should be in this data sets here. Okay, this data sets. So go to this data sets and the reference materials, and that's where I'm getting this house price CSV from. So if you download that and extract it onto your machine, that's where you can get that. That's where you can get that file from. So house prices. By the way, if you have it in your Google Drive, you have to run this code. You have to run this code first to be able to access files that are stored on your drive in Google. So you want to run that first, and that makes your data accessible within your. So this is if you're running in Colab. If you're running in Colab, you want to run that in a cell so you can. This makes your data accessible. Let me write that down. This makes your Google Drive data in Colab. Okay, so you have to run that, and then once you run that, then you can access data that's within your drive. So if you go to this like folder icon, you can see you can browse your drive within this folder icon. This is likely going to fail for me because I didn't mount the drive yet. Yep, so I can't find my drive files, but I just run this permit. There is, but only for the folder you have open. It's just the like file explorer on the left. Roberto, it's just the file explorer on the left, but only if you have it only in the folder you have open. So what I would recommend if you're working in VS Code is to I would recommend to put that data set in the same folder as where your notebook is so it can discover that file pretty easily. Does that make sense? Like put that data set file. So there's two files in this notebook that you're going to want access to, which is the house prices and the iris Excel. So put those in the same location as this notebook and it should work. So let me actually put a comment here. So you should be doing pd.read CSV, and then it should be file path to CSV, wherever that is. So I think the easiest thing to do is put it at the same location as where the notebook is saved. Because if it's in the same place, then that should just be pd.read CSV, and then it should be house price .csv. Should just be that. Loads the whole file. Yeah, loads all the data in memory. I don't have import drive command on the. Yeah, this is for Google. This is for Colab. This is only for Colab. You need this to access data on your Google Drive. The two files are the house prices CSV and the iris Excel XLSX. Do you have those two? House prices CSV and iris XLSX Excel sheet. So you can build a data frame from here. Now, when you load all this data and you print it out, it's actually quite a big file. It has about 5,000 rows. So it's not going to show you all of that data, but we're going to have some functions we can do that can easily get us some summaries of this data, which will be nice. Okay, so we'll have that coming up shortly. but there are 5,000 rows. So, or sorry, about 4,600 rows. So it's a, decent amount of data there, 4,600 rows. And the iris data also has 460 rows and 18 columns. 4,600 rows, I should say. Sorry. All right. Were you guys able to run this? Were you able to read the CSV using Pandas? Were you able to run this? Not able to. Make sure that the path you have the. Oh, that's fine. The output's getting truncated. That's fine. That's expected. It's not going to show you all 4,600 rows. That's expected. Yes. Are you running in Colab, Mario? You are? Okay. You have to give permissions. So there should be like a pop-up when you run this code. When you run this, there should be a pop-up to give permissions from your Google account for this notebook to access your files. So make sure that that pop-up actually shows up and you click and you validate it. You should see a pop-up when you run this. Okay. Worst case, by the way, what you could do if your drive isn't mounting, a backup is to go. Do you see this file? Do you see this files on the left? And this is for everyone running Colab. If you're unable to get the drive to mount, what you could do is you could just upload the file into the workspace. So if you go to this files, you can upload. You can hit this upload button to upload data. So you can see this upload here from if you click on this and then you click on this, you can upload the file manually into this workspace, into the notebook workspace. So you could do that too. If you have the file on your computer, just upload it. That works too, without having to mount your whole drive. So just click on this upload, and then you can upload the file. So I just uploaded the house price CSV, so now I have it available in the session. And then I could just like that. What should it look like? It should look like this. You don't have to do Google Drive. You can do it this way too. Do you see the way I just showed where you can upload it into the session, into the notebook session? You can do that. You can keep the file on your local and then just upload it to your notebook using this files upload. Roberto, do you see this? Like all of this data displaying? That's how you know it worked. If you rerun the cell, that means it worked. It should display the same thing. If you scroll back up, people posted it, but it's in your LMS. It's in the datasets here. See this datasets link? It's this one. Download the datasets, and we're doing the house price and the Excel and the Iris XLX. Okay, so were people able to run this and get you should see this output that has a bunch of so this is printing out the contents of the CSV. That's right, Roberto. Yep, that's right. Okay. So you guys should be able to see this. Now, this is loading. Let me just take a step back and say this is loading the data into a data frame. So now this is the contents of the CSV are now in a data frame. So we can do data frame operations to that data, which is going to be really useful. We can manipulate it. We can do summaries. We can do group bys. We can do filtering. We can do all kinds of stuff to this data frame now that we've loaded all that data into the data frame. So read CSV, we are going to use a lot during the program. We're going to use a lot to load in data from a file, to load in data from like a spreadsheet style file into a data frame and then manipulate that data frame. Okay. And there's a read Excel, Pandas actually supports a lot of different read functions. So it has read JSON, read Parquet, read arrow. It has all kinds of different file types that it supports. Okay, so not just CSV and Excel, even though those are very common, we can read all kinds of different files in Pandas to load them into a data frame, as long as they're supported. Okay. All right, so we practice loading in the data, but now what we want to do is practice accessing data from that data frame. Now that we've seen we can load data in, how do we actually access data and then start to manipulate it, summarize it, do all those things we were doing with series? We want to extend into the data frame. So let's get some practice there. Let's scroll down and build an example data frame with some fake columns here. So we have column underscore name, column 1, column 2, another column. We're going to practice accessing data from this. And then eventually we're going to come back to this data frame with all that data we just loaded from the house prices or the iris and practice working with that. But for the moment, let's work with this fake data frame built from this. So we do pd.dataframe that builds it out of this dictionary. And here's our column data that we have mapped to these different column names. So if we want to access a column, it's super easy to do. We just pass in that column name here inside of the brackets. So we do df, which is the name of our data frame, and we just have column name here. That's going to access all of the data within a column. By the way, what do you guys think is the data type of an entire column? We just studied it. What do you think an entire column is inside of a data frame? It's a particular type of object. You're right, it's an object, but what type of object? It's a pandas object, not a string. We just learned about it. We just were manipulating it. So a column is a series. Okay, a column is an entire series. Yep, a column is a series. So when we access this column, it's as if we're accessing an entire series. Okay, so if we print out that column, we get this. This looks like a series, doesn't it? It looks the same because that's what it is. It's a series. We're grabbing that entire column, which is 5, 15, and 8. So to access a single column, we just use the braces and we pass in that column index name and we pull back all the data from that column, which is really a series. So remember, a single column is a series, is a pandas series. So we're actually accessing that series when we do column name. By the way, if we were to try and access an invalid name, we will get an error. So let's say we did some column. Now this doesn't exist. So this will give me an error. So if I try to do this and that doesn't exist, this will give me an error. And you can see what kind of error. I get a key error that this does not exist. Basically, I don't know how to access that column because it doesn't exist. Right? So this is, we would not want to do this. We would want to use the proper column name, and that should work just fine. Okay. All right, now how about this guy when we pull back multiple columns? So we can use a list and select multiple columns at once. Now, what is a collection of series? We are studying it right now. What is a pandas collection of series? So when we pull back multiple columns, this should be multiple series, which is a data frame. So you guys are absolutely right. When we access multiple columns, gives us a data frame. So this is actually going to be kind of a miniature data frame. It's only going to be these two columns because we're accessing these two guys, which are these two columns worth of data. That's kind of like a mini data frame that's part of the whole data frame, right? Selected columns there. So let's look at that. When we access multiple columns, we get these two guys, which is a which is a data frame. Okay, we get column 1, column 2, and we see the data when we have 3 different rows from the data frame. So we definitely can access as many columns as we want by passing in a list into that data frame bracket, and it will allow us to access multiple columns. Now, we can't forget about loc and iloc. So, for instance, iloc will allow us to select particular rows based on the index. So iloc of 0 is based on the position. So this is saying, let's grab the data that is at row 0. So again, this is using the positional index 0. Regardless of what the actual index is, the user-defined index, and data frames can have user-defined index. The rows can actually be a custom index as well, because we know a series can have a custom index. So iloc doesn't really care about our custom index. It's going to use the positional index to grab that entire row. It's grabbing the first row. So df.iloc is grabbing this entire row, which has values of 5, 10, and 100, and 25. If you look at it, that makes sense. That should be this row here. That's the row, that first row. We can do filters just like we did with series. We did filters. We can do so we can do conditional filters here where now how do we do that? It's exactly how we would have done with the series, right? So we do a bracket to signal that I want to access something, and here we give a filter. So what this filter does is this will filter rows of the data frame that meet the condition. Okay, so any row where this condition is occurring, in other words, this column name, it has a value greater than 10, we will keep. So we go to that, column name bigger than 10, which ones are bigger than 10? It looks like only this guy is bigger than 10. So we really should only be keeping this row here. Should be the only row that gets kept, because that is the one that corresponds to where this column has a value greater than 10. Okay, do we see how that filter works? We're really checking, so we go back to the syntax. We're checking where a particular column is greater than 10. Only those rows do we keep where this condition is met. So what we should do is go and double check this. So the filtered rows, we only are keeping that one row. So we just filter that one row because that's the only place where this guy is bigger than 10. So that's very powerful. We do this very big kind of filter operation on the data frame. So you have to think of the filter operations we did on the series, we're extending it into 2 dimensions. We only keep the rows where this condition is met. Okay, only keep the rows where that condition is valid. Okay, it's because overall we access data by using df and then the bracket, right? So that should be generally accessing data. We saw that with the series too, right? It's a series and we have bracket. We saw that with lists. Usually it's a list and then a bracket and we pass in an index. So we generally have the first df with the bracket to signal we're accessing something. Okay, just generally we're accessing something. Now, the reason we have df twice is because inside of here is a filter condition. And the condition says, I want to look at this column. So the reason we have the data frame twice is you see that we're accessing that column, which is df bracket the column. This accesses this column and says, I want to check where this column is bigger than 10. All the rows where this column is bigger than 10. That's why we see df twice. We see it once on the outside to signal that I want to access something from this data frame. What do I want to access? Only the rows where this condition is being met. Only the rows where that condition is true. All right, I have one more thing I want to talk to you about on the filtering, and then we'll take another little bit of a longer break. So we've been going for a couple hours now. So once we filter like this, we're basically picking all the rows that we want out of the original data frame, right? Because that's what this does. It selects rows based on meeting this condition. But there's nothing stopping us from accessing a particular column after we do that filter. So that's what this, I'm going to scroll down to the bottom of this cell and go to this example, and I'll come back and talk about IAD, and loc in a minute. But do you guys see how we are accessing, this is the filter again, same exact filter. This is bringing back, so let me copy this and make a comment here that this part of it gives us the df rows that meet the condition. And then we access a particular column of these rows. So that's what this does. Do we agree on that? So this is saying I've already filtered my data frame to be filtered to this set of rows, but it's still all columns. So if I were to draw this, right, if I were to draw this, we've basically filtered it out to this selection of rows. Just imagine that, right? We've filtered it down to this selection of rows. But what this thing does is says, let's zoom in on this column, right? Let's zoom in on that column. That's what that does. So we are allowed to do that in the syntax. Once we filter, we can select a column from the filtered result. We can basically chain those together, which is what that's doing. That code is doing. Okay. All right. So let me just summarize the things that we've done in this cell. Let me move that. So all we did was we created a data frame with some example data. We didn't even use that data yet. We'll come back to it. But we're just using this example data from this dictionary, and we were just practicing some different things, like accessing a single column. All you have to do is put the brackets and then the column string, which corresponds to whatever column you're selecting. That is going to retrieve the series of data, in this case, like the column, right? 5, 15, 8. So it's doing that. You can select multiple columns if you pass those names inside of a list. So column 1 and column 2. This is actually going to give us a data frame result, right? Because now we have multiple series being pulled back. Multiple series equals a data frame. Okay, multiple series equals a data frame. So we have a data frame result that is giving us only these 2 columns out of the 4 columns that exist. We can use iloc to grab a row based on the position, the positional index of that row. Like this is the first row. We can do the second row. We could do the third row, the fourth row, etc. So that's just the first row. We did a filter. So this is just a basic filter. We were just talking about this where this is the condition. And so this is saying, let's grab all of the rows out of this data frame where this condition is being met. Okay, all of the rows where that condition is being met. All right. Then, yeah, different from a slice. Different. This is a filter, different than a slice. This is because this is conditional, right? A slice is more positional based. It's not conditional. This only selects data that meets this condition. This is conditional. And then what we said is based on this condition, we can actually select another column right after that, which kind of changes together. Yes, Roberto, it's like a bidirectional. Yep. Okay. So while you try that, let's continue talking about on this set of examples here. We had the at. We had just gotten to the at. Now, the at is like the equivalent of loc for accessing a single entry in the data frame. So this is the equivalent of df.loc for a single value. So at will use the index. So at uses the index, uses the row index and the column index for accessing. So the row index in this data frame is just the default. It's just the positional, just happens to be that way. Does it have to? No, it could be dates, it could be strings, it could be anything. In this case, we didn't specify any special row index. We do have column indices, right, which are these names. So we can use those, but there's no special row index with this dictionary when we create this. So it just has the default row index. So when we use at, we can say, I want the value at the first row, which is row 0, the second row, which is row 1, the third row, fourth row, fifth row, and those are all going to be this positional index because that is the true index of this data frame, the row index. However, we also have the column index, so we can access things based on that. So column name, we're grabbing the element in the column name column, but the first row here. So this should fetch us this 5 because we want to be within this column, but the first row. So this at should return to us the a 5. So if you go down to single cell by label, this should give us 5, which is what it does. So sometimes you can use at. Again, this you only ever use it if you want to access a single item, which is kind of rare. You're not usually going to be grabbing just a single item in the data frame. Usually you're going to be grabbing multiple rows, multiple columns. But there is the at function for passing in a row index and a column index to access a single item. Yes, but that's true, Ramiro. But I would call it the row index and column index. In this data frame, the row index is 0 because it has the default index, right? It has the default index for the data frame, which is 0, 1, 2, 3. It's this. This is the row index, right? This is the row index. And then this is the column index. Column index. Okay. All right. So with at, we have the equivalent of loc, but for accessing a single item. We also have I at, which is this is the equivalent of iloc. So this is the equivalent of iloc for accessing a single element. And so this one we use. So this one uses the positional index for row and column. So we do not use the name for the column. We only use its positional index as far as which column are we in going from left to right. Are we in the first column? Are we in the second column? Are we in the third? This would signal that we are in the second column because that is the column that is at index 1. So if you use the positions with I at, or iloc, for example, we would be like, this is column position 0. This is column position 1, column position 2, 3, regardless of the actual column index, right? It has a position within the data frame going left to right. Every column has a position. So I at uses this column position. It also uses the row position regardless of what this is. It just happens to be the same because the data frame uses the default row index. But so 0, 1, if we did I at and then we did 0, 1, would be the first row, second column, right? First row, second column. So that should be this guy. So we look into our data that we have, which is this data frame right here. it should be first row, second column, it should be 15. So we want to make sure that we get 15. So if we run that single cell by position, don't know why it's saying, where did we do? Sorry, row 0, column 1. So row 0, column, oh, sorry, that would be this. Yep, it would be 10. Oh, so it just took the value. It actually it ignored the column string and just it evaluated it. Okay. That's what I figured. It wouldn't honor the formula. It would just take the value as a result. Makes sense. Thanks for trying that. That makes sense to me. Is it possible to assign a label to a column and what? Call it a label? Yeah, you can call it a label. I think people, yeah, so going back up to this, people sometimes call these the label instead of the index. Like this column name, they usually, yeah, you can use the word column label or you can use the word column index. Either one works. I think people would know what you mean by column label. If that's what you're asking, yeah, you can do that. So yeah, you can use either of these. They're pretty much equivalent. Okay. All right. Finally, we have df loc. So if you guys remember, loc uses we've kind of already talked about this, but loc uses the indices, right? So it uses the row index and the column index. In this case, we're selecting the first row, but all of this column named column name. So here we are selecting the first row, but all of column name column. We're picking all of those values. So we should be getting first row, but the whatever is in the column name entry. And so that would be if we go back to, we should be in the first row, but only getting this 5 essentially, which is the value in that column name. So loc will use the indices just like at would. So at uses the indices. Loc also uses the indices. Basically, loc we would use though when we want to select. So we use loc just like we did when series, right? We use loc to select multiple values. You can even slice the rows. So for instance, we can grab the first 2 rows and slice it that way. And that would pull back multiple values for this data selected with loc. So it's actually going to grab all of those rows 0 and 1 and the data belonging to column column name. So you can even put it, so you can use loc to grab multiple entries. So you can have a slice in there, which is pretty interesting. So here's a slice, 0 and 1 rows. Okay. All right, let me get to some exciting summary functions that we will cover next. So I want to go through some basic data frame functions now that we've seen how to access data. Let's look at some other convenient functions. And some of them are going to be really familiar from series. They're going to be the exact same, like head and tail and sort and is null. Those are all going to be the same that we have, except now it's going to be in multiple dimensions. So let's take a look at some of those examples, but some of them are going to be pretty unique, but some of them are going to be basic multi-dimensional extensions of the functions we've already seen for series. So let me walk you through some of the functions that we are going to do some examples with. The first couple we've already seen, which are head and tail. So just like in series, we have a head and tail function which shows us the first few rows of the data frame. If you don't put anything in the head and tail argument, like if you leave this blank, it will just do by default the first five or the last five rows for head and tail. Now, why is that helpful? It's actually really helpful often when we load in a data frame. The first thing we typically do is run a head or a tail so we can sanity check what we just loaded without having to print out the entire data frame. Printing out the entire data frame is usually inefficient, and we don't like it's going to get truncated anyway. So a very standard thing to do is to just print out the head or just print out the tail so we can get that view of the first five or last five rows to sanity check what we just loaded in. So that's a very common thing to do. We're going to see examples of that, and we're going to use head and tail quite a bit as we move along. And as we load in data, that'll be usually the first thing we do is head or tail, just to take a look at the data we just loaded in. Yes, it's going to include the header. Let me show you an example. So if we go back to the data we loaded earlier, so the house prices, let's print out the head. So df.head. It shows you the header, but it just shows you the first five rows. See how it's just the first five rows, but we can see all of the contents of the data pretty nicely and succinctly. So it's a very useful thing to do, right? When you load in this data, this is very useful to do to sanity check what did we just load? What does it look like? df.head, we can get a sanity check of what the data looks like after we, load it in. And we could do tail. So that will give us the last five in the data set, right? That'll give us the last five. So you can see there's 4,600 rows. This gives us the last five of them. Sanity check that too. Usually we look at the first five. Okay. So head and tail. Now, you were asking Roberto about a summary earlier. Here is a couple of really nice summary functions, which are going to be two that we'll use quite a bit. One is called the info, which gives us an information summary of the data frame, including all of the columns that exist, all of the data types, and if there's any data missing from those. So the df.info function, which you see used right here, is an incredibly useful function to give us a summary of what is there. Okay, it gives us a summary of what exists. So let me show you what that looks like on the example I just did. So on that house price data set, we looked at df.head. Let's do df.info and print out the information summary. So if you take a look at this summary, what it looks like is we have a total number of columns. We have a total number of rows. So 4,600 entries, that's 4,600 rows. We have a listing of all of those columns and how many non-null values they have. So you can quickly eyeball and see which columns are missing data because we're expecting to have 4,600 entries in every column. Those are the rows. And this tells us how many were not null. So 4,600, that's a good number. That means we have full amount of data not missing. Right? That's pretty good. Not only that, but we get the data type. So what this would tell me is anytime I see object, I'm thinking of that as a string. So the date is just a string of the date. The price is a float, bedrooms is a float, bathrooms is a float, square footage in the living room is an integer, square footage of the lot is an integer, floors is a float, waterfront is an integer, view, all of these things. You could see exactly what year that it was built as an integer, year that it was renovated. So you could see what all of these columns are about these houses. It's all different attributes of the houses. These are all strings, so they're related to like street, city, zip, country. They're all address related things. are all, strings. That's not surprising. So you can see that we have a bunch of float columns, a bunch of integer columns, about 5 string columns, and this is how much memory our data frame takes up. That's a pretty good summary, I would say. Is this the summary you were looking for earlier? Oh, yeah, that's a pretty good summary of all the columns and their data types and not null. This is a great summary. Yeah, so this is df.info. df.info gives us that information summary about this data frame. What is non-null? Non-null means not missing, like not null values, not missing, right? Meaning it's like not empty. Okay. So we have info, incredibly useful. Now, do you guys remember this? We had this for the series, was the describe. Now, this gives us a summary of the statistics. And now if we take that describe, remember, it was operating on every series, but what is every column of our data frame? Let me ask you guys, what is every column of our data frame? What kind of data type is it? There we go. Yes, it's a series. So should we be able to do describe to every column? Because remember, describe was a function on a series, right? We've already seen that. Describe gave us a summary, a statistical summary of our series. So it should be natural to extend describe to the whole data frame. That should be pretty natural. And and we will. So basically what describe will do, will take that same exact describe that we did on a series and it'll do it across every column. Every column that is, the catch is, it's only going to do it to columns that are numerical data types. So it's not going to do this to strings, okay? Because it doesn't make sense to compute like an average or a median or a percentile. Right? It doesn't make sense to do that to object columns. So it's only going to do this to numerical types. So it's going to do that summary for every numerical column, every numerical column. So numerical meaning it's some type of integer or float. It's going to compute the min, max, average, median, percentiles, standard deviation. All of those are going to get computed. So that's a great summary. That's a really great summary to get a sense of what our min and max, like our range is, what our average is. That's a great summary as well. So let's run that on the housing prices. So we go back up. We just did info. Let me do df.describe. So this should be computing those averages. So this is going to be computing those values across all of those numerical columns here. So for the bedrooms, the minimum is 0, kind of wacky, 0 bedroom, and the max is 9. So there's a 9-bedroom house in there. The minimum bathrooms is 0. I'm gonna guess that's likely because it was missing, so it just filled in a 0 in the spreadsheet. But the maximum bathrooms is 8, and the average bathrooms is about 2, little over 2. The average bedrooms is about 3. I think that makes sense. It's pretty reasonable. Just sanity checking that. And then we see that the average price is sitting here about 55,000, or sorry, 551,000, I think is what that is. Because remember, I mean, it's not missing, but it was filled in with a 0 ahead of time. So there technically is a value there. It's just meaningless, basically. But there is a value there. It's kind of like defaulted. Yeah. So you're right. Like 0 bathrooms would make no sense. So that data is likely probably not good, probably not very great data, but it's not missing. There is a value there. It just happens to be 0. It was probably like whoever was recording that data didn't have a number of bedrooms and bathrooms, so they just put 0. Does that make sense? Like if you were filling it out from a survey or something, they just probably just put 0 as a default. They didn't know what it was. Just put 0. How can you remove scientific notation? You can display it, I think, as a normal value. So I think if you grab, let's try this. I'm actually not, yeah. So if we do, if we do, yeah, that should truncate it. There we go. Yeah, the round function. So we can round our entire describe, I think. Yeah, that'll round it to 2. Okay, I thought there was maybe an argument that would do that by default, but there's not. Okay, so round works. Okay, so if you set that at the pandas level, which will default that for everything. I like the round though, because we can be a little more selective on when we do it instead of just doing it by default to everything. But thanks for, yeah, I agree that that should work, setting it at the pandas level. Okay. What do we think about describe? Does it seem useful to you guys? Does it seem useful to have a nice summary view of the statistics? Like you get a mean, you get a min, you get a max, you get remember the 50th percentile is the median, right? You get the median, standard deviation. So about the average house price in this data set is about 551,000. Now there's a max that's way out there, looks to be like 26 million. I mean, that seems like an outlier. I'm gonna guess it's this 9 bedroom, 8 bathroom one that has 13,000 square feet, but seems like seems like an outlier potentially. But maybe we'll study that later on when we get into identifying outliers and such, which we will. But that seems like yeah. And the square footage of the lot. I mean, this seems like a lot of land. So that's, we'll have to see if that's an outlier or not. Okay. All right. So let's go back to our function. So we had describe. Now, the shape we know we can get. So that's just an attribute. This isn't even a function. This is just if we ever want to see how many rows and columns we have, we can do dot shape. So we go back to our data. We can do, so we had the statistical summary. We can do df dot shape to see how many rows and columns we have. So we have 4,600 rows and 18 columns. That we know that's what we had. So not surprising there. We can always do dot shape to see what we have. Now, what's interesting is we can also do dot columns to get a list of all of the columns that we have. So that's another useful one if you want to quickly see, if you want an exact list of all of your columns. So df dot columns. This gives us a list of all of our columns, so we can quickly see which ones we have, and we have a list of those guys. So df.columns gives you the kind of listing of all the columns that are in your data frame. All right, loc and iloc, we've already talked about. Those gives us the ability to access data. So we have, those are the same from series. We just did some examples with those, so I won't spend too much time on them. I want to get to a couple of interesting ones. Any idea why I'm not getting my house price? Head or tail? Data load is complete. Are you running it like what did you load it into? What did you name the file when you did read CSV? What did you name it? Okay, so you should be doing df csv.head. Does that work? You can either run it in the cell or you can try printing it. Either one should work. If it's not working for you, you could try restarting your session. If you're in Colab, you could try restarting your session and rerun it. Maybe that'll work. Okay, it works. All right, great. Yep, should work. Okay, so we can sort, we're going to do some examples with sorting down below, but what we can do now, what's interesting about a data frame is when we sort it, now we have columns at stake. So sorting is a little more complicated. We have to decide, how do we want to sort this data frame? Which column do we want to sort the rows according to? So that's where sorting the data frame has the ability to sort by one or more columns. So here you pick which columns you want to sort by. we're going to do some examples with this, but you can basically sort by one or more. So you can say, hey, I want to use the square footage and sort everything from greatest to least square footage, which will shift all the rows around according to that square footage column. You could sort by the number of bedrooms, number of bathrooms, right? We can pick which columns we want to sort by. So that's the only thing is like when we're sorting a series, we just sort the data. It's only one dimensional, right? So we just sort it. But when we have a data frame, we have to be more selective and pick which column we want to sort by. So that's the only thing that we have to be careful about. So we'll do some examples with that. Now we have some another interesting function here that we're not going to get to today, but we'll cover this in our later lesson 8 or 9, or sorry, 9 or 10 when we get into working with our data. But data frames support group by operations, which is basically like if you're familiar with SQL, doing a grouping of the data according to a certain column, and then we can do aggregations based on that group. So we will learn about this later, but data frames support grouping according to certain columns, which is really useful. So suppose we want to group by number of bedrooms. So we want to take all of the houses that have a certain number of bedrooms. So all the 2-bedroom houses, all the 3-bedroom houses, all the 4-bedroom houses. We want to group by those and figure out what their average price is. We could do that. We could group according to the bedrooms and then do like a mean on the price. Those kind of slicing and dicing we will be able to do later. We're not going to get into it today because it's a little more advanced, but we're going to have a whole lesson dedicated to doing this in the future. So we'll come back to group by later on. But that's a really, really useful, as you can imagine, right? Grouping by columns really useful. So we'll get into that later. Now, one function we've already seen, and it will show up here again, is the apply. So we have that basically the same to where we will be applying a function usually to a column to transform that column. So usually we will apply to a column or maybe multiple columns in order to transform them. So maybe we want to take a column and multiply everything by 10, or take a column and square everything or divide it by 5, or whatever the case is. We can use df.apply to apply a function to a particular column, just like we were talking about with series, because what is a column? It is a series. So it should make sense that we can apply a function to that series. And so we will be able to do that. We're going to see some examples here of using apply to transform an entire column of a data frame according to a function, right? So remember, the argument to the apply is a function. So we're passing in, hey, what function do I want to transform this entire column according to? Do I want to square everything? Do I want to cube everything, take the square root of everything, take the logarithm of everything? And really, when you're looking at the column level, that would be every row, right? Every entry within that column we're going to transform. So we will do that in some examples coming up. So we're going to see apply. Now, something we're going to see later on that that will be also in the same basic lessons that we're going to learn about group by is going to be the merge or concat. Now, this will be able to take multiple data frames and merge them together. That's incredibly useful. You can imagine like loading in data frames from multiple files, and those will create multiple data frames, and we want to bring them together in some way. So merge them, like join them together like you would kind of like a database table join. We'll be able to do that, or just actually concatenate them. Just maybe they represent the same column, so we just stack all the rows on top of each other in a concatenation. So the ability to merge or concatenate data frames, we'll learn about that later. I don't think we'll do any examples today of those, but we'll, again, whole lesson dedicated to grouping, a whole lesson dedicated to merging, concatenating. So we'll certainly cover that later on. Okay. All right, so a couple more. Now what's really nice, and we're going to learn in the next lesson on how to do this alternatively with Matplotlib and Seaborn and some of the plotting libraries, is DataFrames have built-in plotting that uses Matplotlib as kind of the backend to do it. But you can actually directly from a data frame plot columns, which are really useful if you want to quickly visualize something about that data frame. So if you want to actually see what is a bar graph of all the, or a histogram of all the housing prices, we could do that really quickly just with the data frame. We don't need to use any additional plotting libraries. So that's usually for quick plotting. We're going to see some examples of this coming up of how we can do this within this notebook. We'll see some examples of doing this, but we'll also in our next lesson, in lesson 5, we'll talk more about plotting. Lesson 5 will be all dedicated to doing plotting with the more sophisticated libraries that are dedicated to plotting. But just for doing something quick, the data frame actually supports plotting directly out of the box. We can do something like df.plot and directly plot attributes of it, rows and columns of it, which can be pretty useful. All right, finally, data frames have the ability to drop rows or columns. So if for some reason we need to delete rows or columns, we can definitely do that. A pretty typical use case for that is maybe we load in a data frame from a CSV, like a file, and there's some columns we just don't need. Maybe there's a user ID, or there's some type of useless like extra column that's snuck in there that we don't actually need. We can go ahead and drop it. You can drop multiple columns, you can drop multiple rows. We will see some examples of this as we go along, but pretty typical use case is dropping columns. And usually what you do is you just pass in the column argument here of which column do you want to drop. So it's like, okay, I have a user ID column. I don't really care about it. I'm gonna drop that, but doing df.drop and then go ahead and pass in that column index to go ahead and drop it. Okay. So we'll see an example of that coming up shortly. Okay. All right. So let's go ahead and take a look at some examples. So we're going to have some fake data here in our data frame. So we're going to build out the data frame we kind of had earlier, very similar one. We put that in the data frame, pd.dataframe, build the data frame here. Oh, you had a question on the merge. Left and right, no, those are the two data frames. So this would be merged together. So this would be df1 and this would be df2. We have two separate data frames and we're merging them together. The on is usually a label of a column that they share. Like if they share a primary key column, then that would be like a join. Yeah, Roberta, that's like a SQL join. Yeah. This would be an inner join between these two tables. And we have a join key here that would be a column. This would be a column that we want to join on. We'll learn about that later. Yeah, we're going to have a lesson dedicated to doing that. Okay. All right, so if we were to go back to this example, now head and tail, no surprises there. We can print out the head and the tail. This gets us the first 2 rows. This is the last row. So first 2 rows should be these guys. And then the last row would be this guy. So we can take a look at that. First 2 rows, again, here's those. Last row, this is this. I don't think there's that much surprise with head or tail. I think we're pretty comfortable with that. Info we've already seen before. So the info about this one is that it has these 4 columns here. It's not missing any values. It only has 3 rows. It's not missing any data there. It's a pretty small data frame, only 220 bytes. Makes sense because we don't have that much data stored in there, just some integers. It's not that big of a data frame. Only has 3 rows. And the shape of it, so we can print out the shape. It is a 3x4 data frame. It has 3 rows and 4 columns. We know that. It makes sense, right? Not that surprising there. But some of these things we will see, like now let's sort it. We could actually sort some of this. Let's sort this data frame. Let's do some additional code here and sort it. So let's go ahead and do print, and then let's do df.sort values. Let's go ahead and sort according to, this is where we pass in the column that we want to sort by. So let's go ahead and sort according to this. Oops, I'm in the wrong section. Let me sort, I want to sort this one. Let's sort according to column. Which column should we sort according to? Maybe this one, which is unsorted. Let's sort it from least to greatest. So column name. Let's use column name as the column we want to sort according to. Let's see what this does. Oops, this might need to be, sorry, this might need to be a list. Oh, I didn't run this yet. That's why. Okay, there we go. So it ends up sorted. So see how that now shifts around this guy to be sorted. Now all of the rows are sorted according to this column. So we went ahead and sorted that, which will you see how originally it started as 5, 15, and 8. Now it's been sorted from least to greatest, which is the default. But of course, we could change that to be ascending equals to false, and it should now do greatest to least. So 15, 8, 5. So that's the primary sorting that's done. And so that's an example of sorting. We could also, so this is an example of sorting. And then we'll do an example of dropping. So let's go ahead and do df.drop. Let's go ahead and drop the column. Let's drop column 1. Let's say we deemed that guy to be pretty useless. We're going to go ahead and drop that one. So we can go ahead and drop that column. Now, one argument here I forgot to mention is that if we don't, the default is to not do this permanently. In other words, if I run this, it's not permanently going to be dropped. We're just going to get a copy of the data frame as if it was dropped. So we're not going to get so I could save this result as df with and save that as this. And what that will do is it will pretend that we had dropped this column from this data frame and store that result in this new data frame, which is a copy of the original. If we don't want to do that and we actually want to permanently drop, then we can set this argument called in place, and we set that to true. Now, what that will do is it will permanently drop that so that this data frame no longer will have this column 1. So we can do that, and it will no longer have column 1. Oops, I may need to have this inside of a list. Oh, I think I need to do columns equals. There we go. So now if I go ahead and do df, it no longer has that column, right? It no longer has that column in there. So this is saying I want to drop this column and I want to do it permanently. So therefore I go back and print out the df. It no longer has that column in there. It's been deleted. So I've like permanently removed that. But if I don't do in place, let me show you. If I don't do in place, let's rerun this. I want you to see the difference. If I set this to false, which is what the if I set this to false, which is what the default is, then and then I do that, and then I print out. If I go back and look at the DF, it still has column one in it, so it's not permanently deleted. I just get this copy when I do this, and I can certainly store that DF with drop, and then I can display this, so DF with drop. And now this guy does not have column one, but if I go back and look at DF, it still has that column. So you have to make that choice when you do these drop operations. Do you permanently want to alter that original, or do you just want a copy with that dropped column? It's really up to you, but either so if you want to permanently alter the data frame, you set in place equals to true. It will permanently drop it. Does that make sense to us? In place equals true, we'll permanently drop it. All right. All right, before we move on to statistical operations, let's take one more final break since we've been going for a while now. Let's take one more final break and we'll come back and wrap up today with doing some statistical operations in Pandas. So we'll learn about doing mean, median, mode, all those good functions on our data frames. We've already done the describe, but I want to show you how we can do individual statistics if we want to just calculate the mean, just calculate the median, the max, the min. We'll do those. So, okay. So I had scrolled down to here. I was just saying we can always do describe. That gives us all of the statistics on a data frame all at once. But if we want to do individual ones, we can come down here and do dot mean, dot median, dot standard deviation, dot max, dot min. And this will do those individual functions across each column. But we can actually do them on individual columns if we want. So all we'd have to do is access those individually. So let me show you that. So for example, if we just selected, let me go down here. If we just select a particular column, so we do numeric column one, let's say, and we can do dot max, we can easily get the maximum of that column, and it turns out to be 15. Do we see that? Like if we select a column, we can easily do these aggregation functions or these statistical functions. We can do mean, for example, to get the average value of that column, which is 9.333. We have that. We can do the median, which is 8.0. So this is how you can do it of a single column. If you want to just zoom in on one column and get a statistic of it, let's do the min. We can do the lowest value in that column is a 5, for instance. Okay, so pretty simple. We can actually total everything as well. So we could do dot sum, which will total up everything in a column. We can do count, which will count how many values are in that column, and there's really only 3. So those are just the total number of values. So we have a bunch of different statistical operations available to us. Standard deviation. Okay, so we can do all those. Remember, if we just do dot mean, this is going to compute the average for each column. This is going to compute the average for each column. Okay, so that's why when you print out this mean, you actually see it for each column: 9.3, 20, 200. Same thing with the median. This is going to do the average for each. This is the average for each. Sorry, this is the median for each column, and you can see that here. These are all the medians. These are just doing individual functions. So the describe does all of them. It prints them out all. Like maybe we don't want to do all of them and we want to zoom in on a particular column, we can do that with something like this. Like we can zoom in on a particular column and compute the max. We can basically, it's just convenience. Do we want to do all of them at once in the describe, or we want to zoom in on one and grab a particular statistic if we need that, right? There's really no difference in the values that get computed. It's just how much of it do we want? Do we want all of them? Do we want a little bit of them? That's up to us. I want to show you some additional things. Now, we haven't learned about this. We'll learn about it later, is exactly how to compute this correlation. But Pandas supports taking a data frame and doing a correlation matrix, which is a way to determine if certain columns are related to each other linearly. So if there is a linear relationship between columns, we will see that. And so the way we do that is we do dot core, which computes the correlation matrix between columns. So the way you read this is, for instance, a column with itself is going to be on the diagonal, and those are all going to be a one, meaning that of course of course a column is correlated to itself. That makes sense. Like of course, they always have a relationship to itself. That makes sense. But what this is signaling is that it looks like column two has a relationship with column three that's perfect, a perfect linear relationship. Again, we're going to learn about that later on, what that exactly means numerically. But just calling it out now that DataFrames support doing a correlation matrix. And it's not surprising to see column two related to column three. I mean, look at this relationship here. Column three is literally a multiple of column two. You just multiply by 10, you get exactly column three out of column two. So it's not shocking that you get a perfect correlation there between column two and column three. But again, we haven't learned the formula of that. I'm not concerned about us knowing that yet. We're going to learn about that later on, but just showing you that data frames support a correlation calculation, which is really critical for model building and finding out what columns are related to each other, which will, again, that'll be really helpful for prepping our data for modeling, finding out correlations and removing correlations. In the real world, when we see this, we're likely going to remove this column altogether, probably drop that, because it doesn't do us any good if one column is a perfect multiple of another. It's not really useful to us from a modeling perspective. They tell us the same data. One is just scaled up than the other, but they tell us the same exact kind of trend and the same data. So we would prefer to just get rid of that extra column that we don't need. So we'll do that later on. How did you round off 2 decimals? It was round. So you use the round function. So it was round, and then you pass in the 2. So round, and then round, and then comma 2. It was like that. Okay. Now, an extremely useful function that is last in this notebook, but certainly not least, is the value counts function, which is an extremely useful one to count the number of occurrences of unique values in a categorical column. So what that means is there are certain columns that represent categorical data. So think about it like in the house prices, there are the houses are captured in different cities. So the cities are kind of categorical, right? They belong to a certain number of a certain number of unique cities that exist in the data. So categorical data is basically data that has discrete values, right? It belongs to a certain number of unique, limited number of possibilities. It's not a real number data. It's not like a float or an integer. It is usually a string that represents some type of category. So for instance, imagine we had a column in this data called category, and it only had 3 different possibilities. It was either A, B, or C. What would be a natural question is that, we would want to know what is the most frequently occurring category, or how often do those occur? Like how many A's do we have? How many B's do we have? How many C's do we have? That might be a natural question to ask. And the way we can get that is with the value counts function. So on a category, we can compute the value counts, which will, or sorry, on a column of categorical data, we can compute the value counts function, which will return to us a series that tells us how many values belong to each unique category. So this is incredibly useful for two reasons. One, if we have a bunch of data, it tells us what the unique categories are, in this case, A, B, and C. That might be useful to know in and of itself. Here are the unique members of this column, A, B, and C. And here are their frequencies. We have A shows up 4 times, B shows up 3 times, and C shows up 3 times. That may be useful to know. So value count is an extremely helpful function for determining what are the counts of the unique categorical values in a column. So we're going to use that quite a bit as we go along. Again, for data that looks like this, that has discrete categories, and we want to count how many of those are there, and that gives us an idea of how that data is distributed. There's 4 A's, 3 B's, 3 C's, pretty even distribution of the categories. And you can also turn this into a percentage. So value counts gives you the raw counts, but you can pass in a normalize argument to set, if you set this to true, this will display as a percentage. So 40% of the data is A, 30% of the data is B, and 30% of the data is C. So these are now proportions as percentages. So you can do raw counts, which is the default. This is set to false, but if you turn it to true, it gives you that gives you the percentage. So normalize equals to true gives the proportion of each unique category. You can multiply. So you can multiply by 100. That's all you got to do. Just multiply by 100. Oh, to do that, you got to do more work to do that, Roberto. You got to so for instance, you got to save this so you got to save this as a series. So this, and then we have to go in and modify each. We have to turn it into a string and modify it. Like we'd have to add in a percentage. So we turn this into a string and concatenate it with a percentage. We could do it. It's just we'd probably want to write a function to do it. I don't think it comes out of the box to do that. Yeah, we have to. Not that it's difficult to do, but we would require that, writing our own function to do that. How do you get to see the different function arguments? Usually in if you're in Colab, just hover over it. Just click on it and hover over it. That's all I do. Click on it once and hover over it. You can see what the arguments are. And you can even scroll down in this doc string. All right. So there's some more practice. So, between now and Wednesday's session, I would encourage you guys to practice this assisted practice that's inside of 4.01. So at the very end of 4.01, try that out, which is working with some series. And then 4.02, try some of this practice with the data frame. Okay, and this works with the house price data. It asks you to grab different statistics of some different columns, compute the correlation, and then do the value counts on the neighborhood, building type, house style. So it asks you to do just a little bit more practice. So give that a try. Definitely encourage you guys to give this practice a try with the housing price data set. Okay. And let me know, reach out on Slack if there's any questions about you have or any issues you run into trying to work on that practice. Okay. We'll get to that later, Brent. It's just extra practice. It's really just like extra kind of homework practice for you guys. I will share that out once we get to enough progress to work on it. It's designed to be practice for you guys to work on once you've done enough in the course. We haven't quite covered enough to work on it yet, so we'll when once we cover enough to work on that practice, I'll share that out with you guys, Brent. I'll describe that more to you. We just haven't covered enough to get to that, so stay tuned on those. They're just extra practice. Do you mind if I do that at the end of class in a few minutes? I'll share out the notebooks. Not that it takes a long time, but I just need to go back in and do that once we're done. Okay. Let's spend the last little bit of time we have going over to 4.03. Do you guys have this notebook? Do you guys have this notebook, the 4.03? We're going to wrap up by just doing just talking a little bit about working with dates inside of Pandas. All right, so this is the 4.03 notebook. So you have a moment, you want to pull this one up. This is the one we had finished last time. We had just gotten to the beginning of it. This is where we left off on. And we had skipped down to this portion of it where I had mentioned that we have the ability to convert dates that come from our data as a form of a string. We have that ability to convert those dates over to a datetime object, which is really advantageous in Pandas to do because we can extract a lot of information from that object and manipulate that object a lot better as a datetime object rather than if it was just a regular string. It's not that useful. So this was an example of doing that. I just wanted to recap that. Here we have a single column, which is the date column. And so if we were to do df.info at this stage, which is what I put there in the code to kind of do like a before and after. If we currently look at that info, it tells us that the date is an object type, which is Pandas's way of saying that's really a string. And we know it's a string because we are hard coding the data as a string, right? So it's being read in as a date string. But one simple line of code we have here to overwrite that date column and set it equal to a conversion, which is to take your existing string date column and pass it into this toDatetime function. What that's going to do is Pandas is going to convert those strings over to what are called datetime objects. And you can tell it's a datetime object because when you look at the info after doing that, you can see that now we go from a generic string over to datetime 64 object, which 64 just represents the precision. It's down to like, it can go down to the nanosecond of time. Yeah, Tim, it guesses. So there is an argument here in the toDatetime. There is an argument here to supply like a format string to say like here's the expected format of these. Here's the expected format of. So see how there's an argument called format, which would be something like this. We can do format equals, and we can pass in a string to say like, okay, we should have years, months, days, something like that. So if we know ahead of time what it is, we can pass that in. But Pandas will take its best guess based on what the string looks like. So in this case, it is like this, right? It's years. Years are first, then months, then days. So it is like this. But Pandas will guess at that and take its best guess based on the underlying string. But yes, you can change the format here that is expected when you're converting the strings into the datetime objects using this format argument of the toDatetime. Does that make sense? So you can override it, but Pandas does a pretty decent job of guessing what it is, which is the default behavior. If you don't specify kind of a specific format, it will try to guess what it is based on the string. Okay, so why bother doing that? Well, it's because once we have it as a datetime object, which it now is, we can extract various pieces of information about that date. So, for example, we in order to access attributes about the date, we use the DT property, which is short for the datetime property. So we're accessing the date time attribute and we're accessing the day of the week. So, or sorry, the day of the month. So this would give us like the numerical day. In this case, we know from the string it should be 1 and it should be 2 and it should be 3, but we're actually going to generate that into a new column. This is going to take every date and extract its day of the month. So this extracts the day of the month from the date object, from the datetime object. Okay, that's what this dot day does, is it extracts the day of the month. So, and we should end up with a column that has 1, 2, and 3 oh, I'm sorry, not those. Should be 1, 15, and 20. Those are the days of the week. So to get the format right. Similarly, we can extract the month of the year. So this is going to be the first month of the year. This is going to be the second month of the year. It's going to be the third month of the year. And that's going to be the integer month. So this will extract the integer month of the year. So first, second, third, fourth, all the way to 12. And then this will extract the integer year. So we know these are all 2023. So every one of these should be 2023. But of course, if we had data that had different years, we can extract that year directly from this date object. And so in a way, you can think of this toDateTime function as kind of like parsing the date. It kind of parses the date for us so that we can extract pieces of information out of that date that we may need to know. We may need to know specifically what is the day of the month, what is the month, or what is the year. You may care about only those pieces of the data. So if we take a look at it, you can see that these turn into integers because these new columns have the extracted information from these dates. What's great though is even when we have datetime objects and we go ahead and print or we display the datetime object, it still displays like a normal formatted date, which is nice. Like it doesn't display as a generic object. It actually displays as same thing kind of as a string, but we know it's a datetime object, and that's what allows us to extract these bits of information out of those dates. Okay, so that's pretty useful. Now, these are not the only pieces of information we can extract. We're actually going to do some more examples with it, but those are pretty useful just to be able to extract the day, month, and year from the string. Okay. All right. So let us continue then. We also can extract other things from the datetime objects. So we have an example right below where we actually, instead of converting strings over to datetime objects, we are going to basically build a date range. So Pandas supports building a custom range of dates if you want to build. So this will create a custom range of date time objects. So what this means is we want to build a range that starts on this and has 5 days essentially. So the default is how many days do you want to separate from the start? So think of this almost like a slice of dates. We want to start on the first and have 5 days worth of data. So when we first look at our data frame, it starts on the first and goes all the way up to the fifth because that is 5 total days. So if we change this to 10, that would be 10 days starting from the first. We could do 100 days starting from the first. So think of this as number of days that we want starting from this exact date. This builds a range of datetime objects using this syntax. Okay. So what's nice is we don't need to convert anything here to strings. They already, because we're building a custom date range, it already is going to be a datetime object. And because of that, we can extract something like the day of the week. So this is an integer. So we extract the integer day of the week. And something I should say about that is Monday is 0, Sunday is 6. Okay, so it starts on a Monday as a 0 and then goes Monday, and then Tuesday is 1, Wednesday is 2, Thursday is 3, Friday is 4, Saturday is 5, and Sunday is 6. So this just gives us the integer day of the week. Why might we care about that? Because that might be useful data to know, is what day of the week is a particular date. We can always extract that if we know the datetime object. We can extract the day of the week, which is, not immediately known. If you take a look at this date, like January 1st, we don't know what day of the week that is necessarily, but Pandas can compute what day of the week that should be by just extracting that from the datetime object. It can extract that. Okay. Now here's an example where we can use that day of the week to create a new column. So we're going to create a new column called is weekend, and we're checking here if we can, if we divide by 5, if we get a remainder of, if it goes into, if the weekday, if we divide by 5, if we get 1, that means that it must be a 5 or a 6, right? That's what this means. But the alternative is to do something like df date, and then we could just do .dt.weekday is greater than or equal to 5. That would probably be the that'll be the same thing, because the only 2 days that are going to be a weekend is a 5 and a 6. So if it's 5, it's a Saturday. If it's 6, it's a Sunday. So I think we could just do that. I think that would make more sense, is to just check this condition if this is a true or false. That would be the same. That should give us the same result as this. So this is a way of doing it, is checking the integer division by 5. If we get a quotient of 1, that means 5 will divide at least once into that day, which means it must be a Saturday or a Sunday, right? If 5 goes into that day fully at least once. That's right, JD. Yeah, it's a quotient. It's a internal Pandas date object. Yeah, it's a special Pandas date object. Oh, I'm sorry, I missed your question, Roberto. Are periods always days, or they can be weeks? No, they can be different. In the date range, you can change the frequency to be like a string. So the frequency can be like a day, it can be a week, it can be a month, it can be a year. Does that make sense? It's a character. The default is day, which is D. So this means 5 days starting from this day. That's what this would, if that's what you read with this. But we could change it to be months. So it'd be 5 months starting on this date. So it's this frequency parameter, which changes, like you can change it to weeks. So 5 weeks starting on this day. I think you can even do quarters. So like 5 quarters starting on that day. You can do Q frequency, but the default is day, 5 days. You can do time. You can also do hours. So you can do like hours, which is H, or minutes, which is M. So you can do those kind of frequencies as well. Actually, I think it's lowercase m for minutes. Uppercase M is months. Execute? You mean execute the cell? Yeah, we can. I mean, yeah, we can run this. So you see how we did every month. It goes to the end of the month. So see how it goes to the end of the month for those 5 months. So monthly starting on this date. So 1 month from that then is 1 month from then is this, 1 month from then is this, 1 month from then is this, 1 month from there is this. And then just as another example, we could change it over to weeks, which should be changing this frequency to W, and running that. So you can see you get weekly values starting on the 1st. And notice that the weekday is always the same, because that makes sense. It's just 1 week from that day. It's always going to be on the same weekday. For doing hours and minutes, yeah, that's true. So our date doesn't start that way. So it should start like something like this. That's true. Our date should be something like this in order to use hours and minutes. But we're just working at like a daily level as a simple example. Biweekly, I think you could do, you could customize it. I think there may be a parameter here to do starting, ending, frequency. I think there is like maybe a B is biweekly. I think it might. Yeah, I think it might have. I think it might have biweekly. Have to look that up though. All right. Let me ask you guys though, does it make sense how we're creating this is weekend column? Does that make sense how we're creating this is weekend column, which is coming from the day of the week? And initially, like you can either do it this way, or you can do the integer division by 5 and check and see if that's one. The quotient is 1. Okay. Oh, it's biweekly. Yeah, it is two W. Makes sense. Every other week. Yeah, biweekly. Let me stick with the daily for now. All right. Okay. So what I want to show you next is the ability to add and subtract periods of time from an existing date. So one of the advantages to having things in a datetime object. So here's an example where we convert the existing dates over to a datetime object. And remember, if they're already a datetime object, it's not really going to matter if we do the conversion. It's not going to produce an error, but it's not really going to do anything. It's already a datetime object. But supposing we were to convert those over, this is now guaranteed to be a datetime object. One of the things we could do is subtract or add, which does some type of shift of periods of time. And the way you do that is you use a Pandas time delta object. So we use time delta objects to do date arithmetic. So basically shifting of dates. So for example, this is going to take our current dates and subtract 1 day. So time delta gives you an object representation of a period of time. So this is shifting our dates back by 1 day. And how do I know it's 1 day? It's because the argument in the time delta corresponds to those frequencies. Basically, like how much time am I talking about? Is it 1 day? Is it 1 week? Is it 1 month? Is it 1 quarter? Is it bi-weekly? So is it 2 weeks? How much time am I shifting off of these dates? So what this does is this is going to take every single date and subtract 1 day. That's all that means. The time delta is kind of a representation of 1 day being subtracted from the date. Now, do we have to subtract? No, we can also add to shift forward. So this is going to be, the first one is a shifting backwards. This is now a shifting forwards of our dates by 1 day. So this adds a period of 1 day to every date. Now, why is that useful? Sometimes when we're manipulating our data, we may want to shift the dates around to do some type of manipulation to the data. So we may need to shift our dates forward by a week. We may need to shift backwards by a week, or by a day, or by an hour, or by a minute. So if we ever need to do any of that plus or minus of a time period, we're going to use a time delta object to do that shifting forward or backward. So you can see what the result of doing this is. We have our existing dates from our date column, and the previous date goes back 1 day. So you can see what the new dates are for that column. They're automatically computed for you. That's the really nice thing about datetime objects. It's taking our existing dates, subtracting 1 day. So we get a new date object, which represents that shift back by 1 day. So we have 12/31. Here we're taking this, we're shifting it back by 1 day, which lands us on the first. Here we're on the third, shifting back 1 day. It's going to give us a second, and so on and so on and so on. So that time delta really represents like how much time do we want to shift by. Same with going forward. You can see what the next date is. If we take the existing date and we shift forward by 1 day, we get the second. If we're on the second and we shift forward by a day, we get the third, and on and on and on. And so, when we're at the end of the month and we shift forward by a day, Pandas will handle going to the next month and shifting forward into, like, if we're on January 31st and we shift forward 1 day, it will go to February 1st of the next month. right? And you can even see this, like when we shifted back one day, it actually went to the previous year. So it did a good job of recognizing, okay, we're on January 1st, we're on New Year's, want to shift back one day, so we need to go back to 12/31 of the previous year. So it's doing that math for you as long as you shift by a time delta. It will do the math for you of what the new date should be. Okay. So here's an example where we have a couple more time delta examples. This creates a frequency. This creates a date range that starts at January 1st, but has 10 hours of time. So it's going to generate 10 hourly intervals starting on the 1st, which assumes that it's at 000 of the 1st, goes forward 1 hour 10 times. That's the date range. And we can shift forward that time by 3 days, or however, we can shift forward by hours. Like if we replace this with hours equals 3, we can shift everything forward by 3 hours. So time deltas can be, you can just pass in different arguments here to represent different periods of time, like weeks, months, hours, years, quarters, those kind of things. So here's an example where we take all of those existing dates and we actually shift them forward by kind of an arbitrary amount here, which is shifting forward by 2 weeks, 3 days, and 12 hours. So you can see the starting date is the first. The starting date is the first, and then we shift forward by 2 weeks and 3 days and 12 hours. So we go 2 weeks is 14 plus another 3 plus another 12 hours. So that brings you into the 18th at 12. And this was the first hour. This shifts forward to the 18th at 1300, on and on and on. Okay, good. Okay. So hopefully we're comfortable with time delta. How many iterations it takes? We only have to do, so we are adding to the entire column all at once. So it doesn't do any iteration. It just does it in one execution. So really just one execution to add all the time delta to all of those dates. Because we had 5 rows, right? We had 5 initial dates. So we started out with 5 dates. This is taking the entire date column, which has 5 entries, and adding this amount of time to it. Does that make sense? Like we had a column that had 5 entries, 5 dates. We produced that up here. We produced that. Actually, I realized I didn't run this. So if I rerun this, this should be the proper, yeah, there we go. It should print these does that make, so sorry, now it has the proper number because we had 10 periods. This data is based off of running this cell first. That should be proper now. What is range 1020? So range, do you remember what range means? Range is a list. So a list of values that start at 10, go to 20, but doesn't include 20. And it increments by 1. So this is just a list of numbers, 10 to 20. And this is a list of numbers 0 to 9. Does that make sense? That's the range function in Python, which creates a range of numbers with a starting, you just give it a starting and a stopping point. If you only have one thing, this is the same as having a starting point of 0. It's not being used in this yet. It's just here as additional data columns. These are just additional data columns that are in the data frame. It's not really being used with the dates. It's not really being used with the dates yet in this example. It's just mimicking if we had extra columns of data. Yeah, well, because there's 10 rows, but yeah, if that's what you mean, yes, there's 10 rows, so it'll do 10 shifting of dates by this amount. Okay. Now, I want to show you something really important with time series data that's actually going to show up quite a bit when we get into doing more analysis and doing some plotting of time data that is indexed by time. And the thing we're going to take a look at is something called resampling time series data. So what this means is that the dates can be at whatever interval that they are. So I can have dates that are at the day level, month level, year level. I could have hourly dates. I could have time that's at the seconds, and I can have a bunch of different rows that represent data at the second level, day level, whatever it is, right? So resampling is the process of aggregating those times to be at different intervals than what I start with. So let's say I have data that is at the hourly level. So I have a record of like a temperature. Let's say I have a record of a temperature that is, and then I have the date, I have it recorded at every hour. So I have it on 01, 01, 01 on that day, but I have it at 0, 0, 0, 0, 0, 0, 1, or sorry, 0000. So I have it at the very beginning of the day, and I have the temperature as let's say 40 degrees Fahrenheit. So I have 40 degrees, let's say. Okay, and then I have another recording at the next hour. So I have a data point that is at the same day, so 01, 01, 01, but then I have it at the next hour, which would be 01, 0000. So let's say I had a record here, and it's now 41 degrees, let's say. Okay, so and on and on and on. So I have a bunch of data that's at the hourly level. What we can do is we can actually resample this to get an aggregation at a different level. So let's say like I don't really care about what the temperature is every hour. I care what the temperature is across this entire day. So I only care about it across what is it on average across this whole day. So I could boil down all of these dates into a single record for that day. So I could just have an entry for 0101, 2001, let's say, and I have now an aggregated temperature here of it's like 53.7, let's say. So now, and then I go and so then I have a bunch of data that's at the hourly level for the second, but I can aggregate that down to an average for that day, which is maybe 54.2. So something like that. So this process is called resample or resampling, which changes the frequency, basically aggregates the data at a different frequency than what it is recorded at. So let me give you an example of that. Let's say I had a bunch of values that are recorded for each day, and I wanted to get an aggregation. Let's say I wanted to get an aggregation in our data frame. So you see how I have a bunch of different values that are at an hourly level currently for this data frame. What I'm going to do is pick all of my numerical columns. That's I forgot to mention this. Let me come back to this in a moment. This picks all of our numerical columns. So basically exclude any strings, exclude any objects. Let's just pick all of our integers or float columns that we have. And what we're going to do is we're going to resample those at a daily frequency. So I'm basically going to roll all that data up into an aggregate. And which aggregation am I going to choose? You can put that at the end. So you can take a maximum, you could take an average, you could take a median, you could take a sum. Any of those Pandas functions that we've seen that do a statistical operation, we can do a count, we could do a total, which is what we're doing here, the sum. We can do a mean, we can do a max, we can do a min. But this is what this is doing is aggregating that data at the day level. So notice that we take all of this data, which has 10 different entries for these columns. Let's print out our data frame so far. So our data frame has existing dates, it has these existing values, and it has these time delta shifted dates. But what we're going to do is basically aggregate all of this data to be resampled at the day level So it's going to produce a single data point for this day. Does that make sense what it's doing? We're producing a single data point for the day. And we have to say, how are we doing that? How are we aggregating? Well, we're really taking a total. We're taking a sum. So we're actually going to sum all of these guys that correspond to that day. We're going to sum all of these guys that correspond to that day and get a total for that day. But, we don't have to use a sum. We could do a min or a max or an average. So we can, of course, replace this with mean. We could replace it with the maximum across that day. We could replace it with the minimum across that day. But here we're using the total across that day. And how do I know it's resampled at the day level? It is because this is the frequency of our sampling. So we are producing a data point at the day level, knowing that we already have values at an hourly level. We're aggregating them to the day level, and we're aggregating them via this function, the sum. So see how our other two columns produce totals of 45 and 145. Yeah, you can. So yes, what you would do is you have to do it in two steps. You basically would generate the resample data frame, which is just this, and then you can do an apply. So actually that might be worth taking a look at, is then you kind of do like an apply, and then you can do a lambda or an apply your function here. Does that make sense? Like you can do an apply to basically apply your function to the resampled rows that you get, to like the aggregated rows. Yeah, you can apply a function to it. But the pretty typical thing is to do some type of aggregation to it, like a statistical function. In this case, we're doing sum to get the total for each day. Something I should mention is that doing resample assumes that the dates are actually the index of the data frame. So that's a big assumption. So you can only resample if the dates are the index of the data frame. So one of the things that we do first is we actually set the index to be the date column. Now that's important because if you take a look at the DF at that stage, once you resample it, if we were to print the DF before we do the resampling, oh, because I already ran this one, so I have to redo it. Let me redo it. Sorry. Rerun this. Rerun this. Rerun this. Okay, so if you take a look at our dates or our data frame, so what we did is we set the index to be the date. So remember, if we don't do that, the default index is, see how when I printed it out before, the default index is the positional index of the rows. That's the default behavior when you create a data frame, right? It just gives us the index as 0, 1, 2, 3. That's the default. But we can overwrite that by doing this set index function, and we purposely want to permanently, that's what the in place equals true does, right? Permanently reset the index to be the date column. So now when we print out this data frame, you can see that the index is actually the date now. That is the index. There's no positional index anymore. The date is actually our index. And once the date is the index, then we can do resample. So resample assumes your data has the index as some type of date time object. So it's not going to work if you just have if you have the default positional index. Resample won't work. Yeah, Roberto, let me explain that. Well, I'll explain that in a second. Do we see what I'm saying by resetting the index? Where this is a way to set the index on a data frame to something that we like, an existing column. Just saying, okay, set the index to the date column. That's what I want the new index to be, and I want to do that permanently, which is why I have the in place equals true here. So let me write that down as a comment. We permanently in place equals true set the index to be the date column. Permanently do that so that resample will work. If in place equals false, then remember it doesn't do it permanently. It gives you a temporary copy of the result. So you would have to do something like df temp is this, and then we would resample df temp, because this will, like, if this is false, then it doesn't permanently affect the underlying data frame. It only gives us like a view of the result. So that's why usually, yeah, we don't need to do this. If we just put in place is true, that will permanently alter it. And then we could just operate directly on the regular data frame. Yeah, you could set the index back. So once you're done doing that, you can reset the index. Let me show you how to do that. So you can reset the index to the default by using this, which is you can do df.reset index, and then you want to do in place equals true. So you want to do in place equals true. Does that make sense? This will reset the index to be the default. It'll just reset it back to the default. That's how you set it back to the number. Okay, let me go back and explain because it's a good question. What does this mean? So the select D types is a way in Pandas. So select D types is a way to select data. So one way to select data is to use the brackets, right? And we can put in filters in the brackets. We can have many different conditions in there that will pick out the rows that we want to return when we're selecting data. But select D types will select rows, or it will select data from the data frame according to what we include or exclude. So include, if we have an include argument, that means I want to return all data that is numerical in type. That's what select D types does. So this will return all data that is a numerical data type. So what does numerical mean? Think of int or float, right? Some type of numerical data type. So the reason we do that is because resample is not going to be able to aggregate things that are strings or other types of objects, right? Does that make sense? Like it's not going to make sense to aggregate a bunch of data at the hourly level down to a day when we have something that's like a zip code or something like an address. It's like, how do I take the average of an address? Can't really do that. So what this does is it filters the data to only include numerical values, right? Only include numerical values when we do this operation. So this is like a select D types is like a filter. It's like a shorthand. It's like a shorthand. Filters to only columns with numerical data types. Okay. So see how the main takeaway to this is we go from data that looks like this at an hourly level to a single value for the day. We go down to a single value for the day for those numerical results. Now that is extremely powerful. Like that resampling operation is extremely powerful to be able to aggregate time-based data at different frequencies. Really useful, right? For summarizing, for generating reports like quarterly reports or like yearly summaries. Like it's extremely useful function. All right. So what we're going to do next is talk about working with categorical data, which is going to be those kind of strings or data that naturally belongs to discrete categories. We kind of alluded to that yesterday, but I'm going to talk about it a little more in depth now. So we're going to move away from dates and talk about categorical data coming up next. All right, so let's talk about categorical data. So categorical data is, data that belongs to usually a distinct number of categories or discrete number of possible values that it can be. So for example, we may have data that is usually, this would be like in the form of a string, and there's only a certain number of possible strings that that data can be. So like, for instance, what if we had a column that had values that were like this, where the entries in that column were only things like low, medium, high, and those are the only three values we saw. That is definitely a good example of a categorical column or categorical data. So because in that setup we only have three discrete possibilities, the data points are only going to be these three possible categories, which are low, medium, and high. So Pandas does support allowing you to convert objects into categorical data, into a categorical data type. And the reason you may want to do that is to have a sense of ordering or be able to sort based on those categories. So, for instance, we can take the values that are like low, medium, high, and we can generate a categorical data from that, which is going to be basically a series which has a categorical data type. So this goes from a string, and the data is now going to be categorical. We can tell it what categories exist. So in this case, only low, medium, and high exist. And we can say that there is a natural ordering, and the ordering follows the order that's inside of the categories list. So low is first, then medium, and then high. And it goes from least to greatest. So low is the least value, medium is the next, high is the highest categorical value. So all of our data now can be converted into a categorical series, which can be useful for sorting it, because now instead of sorting it alphabetically, which we may not want, because if we were to sort this, it would just be treated alphabetically as strings. Now, if we were to sort this, it's going to be sorted according to these rankings of the category, low, medium, high. So putting things in a categorical type often has a benefit of allowing us to then have some natural order amongst the categories, which can help us whenever we are doing analysis or sorting that data, or grouping that data and slicing and dicing it. Okay, so let me run this. So the what I want you to see is now the categorical variable is now it now is data that looks like this, and has three categories ordered from low, medium to high. So it goes from regular, the data starts out as just a list of strings, and it turns into basically a series that then has categorical data. So pretty useful. What we can do with categories as well is we can count how many unique values there are from each category. Now we saw this, I think on Monday I showed us this, but showing you guys this again is you can take categorical data like we have here, or you can take data that's just regular strings. It actually doesn't matter if it's in categorical format or not. We can take data that's just regular strings, and we can compute the value counts on that column, which generates the number of occurrences of each unique discrete category. So in this case, we have data that only belongs to A, B, and C, but we can see C only shows up once, which is what this count is. B shows up twice, which is here and here. So you can see what that count is. And then A shows up the most, which is 3 times. You can see that's what that count is. Remember, you can pass in a normalize equals true argument here to create percentages. So half the data, this is signaling that half the data is category A, which makes sense. There's 6 entries and 3 of them are A. And then 1/3 of them are B, because 2 out of the 6 are B, and then 1 out of the 6 is C. So you can produce percentages. The default behavior is just to give you the total count of how many are each category. Now, this is extremely useful. Like when we get into modeling, this is going to be extremely useful, because often we're going to care about our data from the perspective of like, how many examples do I have, things that are like pictures that are cancer or not cancer. And maybe it's we run this value counts function on it on the cancer column, and we see that most of the data is actually not cancer, which would be a pretty typical scenario. And then some of it, like some percentage of it is, but we can see that the majority of it is not. So this is a good way to kind of figure out what those relative amounts are between the members of the categories. So this looks like, there's mostly it's A, but there's a few examples of B and one example of C in this data. So value count is an extremely useful function on a column. Usually you run this on one column to kind of see what the categories are. So not only does it give you the counts, but it also will give you the unique categories within that column. Here we have an A, B, and C. We know that because we can see it. But if you imagine you loaded in this huge spreadsheet, you may not know all the discrete values that are in a column. You may not know that right away, but if you run value counts, you can actually get those. And not only that, you can get a frequency of how often those show up in that column. So pretty useful. Yeah, so normalize equals false is the default behavior. That's just going to give you the raw count of each category. So this tells us that there's 3 A's, there's 2 B's, and there's 1 C. So normalize is false. Normalize equals false is the default. So you don't even really need to put it in there. It's the default. And this means that we get raw counts each category. So if we set it to true, we get percentages. So if we set it to true, we get percentages. So see how it changes to where A is now 50% of the data. So this means that of this column, 50% of the entries are A. 33% of them are B, which makes sense because 2 out of the 6 are B. And then 0.1677, that's the ratio of C. So there we have 1 out of the 6 examples are C. No, Tim, value counts is really a function on a series. So you should only be doing it on a single column because remember, what is a column? It is a series. So really should only be doing it on a single column at a time. Certainly you can do it on more than one column, but you're only accessing a column at a time and then doing it. Yeah, it's because it's a function on a series of categorical data. And that's the use case anyway, is typically the use case is to zoom in on one particular column or maybe a couple and do the value counts on those, the columns of interest. All right. So value counts, we'll see again. We're going to use this quite a bit here and there as we progress. This will be a really useful one when we get into modeling. Okay, really useful function for us as we will see later down the road. Let's talk about another really useful thing for modeling, which is to convert data from categorical into numerical. Now, this is an extremely, I really want us to understand this because this is something that is going to be extremely useful as we get into modeling, is machine learning models are going to not really be able to make use of these categories as they are, because it's not going to know how to work with strings out of the box, right? So because they're mathematical models, they're going to struggle to make sense of, well, what is an A string? What is a B? What is a C? What is a D? It's not really going to know what those are. So what we want to do is convert those into a numerical collection of data. And the way that we do that is we actually generate new columns which indicate the presence of that category or the absence of that category. Let me give you an example. So if we have this original data here, so let's just say we had a column called data and it took on these values like we see here. We have an A, we have a B, we have an A, we have a C, we have a B, we have an A. Okay, let's say we had that. Now, what we are going to do to convert this to numerical is generate some new columns that indicate the presence of each one of those discrete categories. So for instance, we're going to create a new column. that is basically going to be do basically do we have data underscore A? Do we have that value? Do we have data underscore B? Do we have B? Data underscore C? Do we have C? Now, in this first row, do we have A? Do we have the presence of A? And we take a look at it and we see that, yes, this entry is A. So I should have a 1 here and a 0 here and a 0 here because I don't have a B, I don't have a C, but I do have A. So this is going to indicate the presence of A. And this is going to indicate the presence of B, as you can imagine. And likewise, this is going to indicate the presence of, of C. So in this first entry, I have A in our data. That's the first entry in our data. So I have presence of A. So I marked down a 1 for that column and a 0 for presence of B and a 0 for presence of C. Let me ask you guys, what do you think presence of A column is going to be for this next entry? So if I look at this entry, what's going to be the presence of A? It's going to be 0. Yes, perfect. You guys are right on top of that. This is going to be 0. Now, what is going to be presence of B? And how about presence of C? Perfect. So presence of C would be 0. Perfect. So now, does this process make sense? How we are converting? So look at what we're doing. We're converting our categorical data into numerical data because now this is all integers, which is great from a model perspective. That's fantastic. I actually have numerical data I can work with. So that's fantastic. Now, what was the cost of doing that? I have 3 new columns. It's not for free. There's a cost to doing that. And you are going to always have that scenario where when you are converting your data over from categorical to numerical, you are going to get as many columns as you have discrete categories for your data. So this data here only has 3 possibilities. So I need to make 3 new columns that represent the presence of those 3 categories. Does that make sense? The presence of those 3 categories. So I have 3 new columns. This is incredibly important to understand because we are going to do this procedure all the time. By the way, this procedure has a very special name in machine learning, which is called, it's this name called one-hot encoding. So one-hot encoding is the name of this process of turning categorical data into numerical data. That's called encoding, one-hot encoding. Why is it called one-hot encoding? Because you're using 1s and 0s to indicate the presence or absence of categorical data. Okay, one-hot encoding is this process, turning categorical data into numerical data. That's what we're doing. That's just the terminology. one hot is like hot is like that. It indicates presence. Like it's there. You can feel it. It's hot. It's presence. That's all it means. Okay, so let me walk through that again because it's really important that we walk through this and understand it. So this data example has a column called category. Okay, it has a column called category, which only has 3 discrete values. It can only be A, B, or C. And you can see the data here. The first entry is A, second entry is B, third entry is A, fourth entry is C, fifth entry is B, and last entry is A. That's what I have here with this data, right? I have that data there listed in a column. So for any time we have categorical data listed in a column and we're going to do modeling with it, we want to do one-hot encoding. We have to do one-hot encoding the model will not be able to make use of the string. We have to do one-hot encoding. So we have to turn this into numerical data. So the trick to doing that is to generate 3 new columns. These columns represent the presence, those unique categories. So we have a column for presence of A, we have a column for presence of B, and we have a column for presence of C. Let me pause there. Does that make sense so far of the setup? So in order to convert our data to numerical, I'm saying let's create 3 new columns which indicate whether or not we have one of those categories, A, B, or C. The presence of A, presence of B, presence of C. That's all I'm saying is we're going to set up 3 new columns to represent this one column of data. We're going to generate 3 new columns called presence of A, presence of B, presence of C. And the way we're going to fill out those columns is we're going to look at our data. We're going to look at our data and we're going to say, what is the value of that data? It's an A. So therefore, presence of A should have a 1 because that means, yes, we have presence of A in that first entry, in that first row. Presence of B, no. We actually have absence of B. So we should have a 0 there. There is no presence of B. There's 0 presence of B. And there's no presence of C. So that also should be 0. So we have converted A into a 3 different columns, presence of A, presence of B, presence of C, where there's a 1 in the presence of A spot and a 0 in the other 2 spots, okay? And we go down to our next entry. We look at B and we say, okay, how about B? It does not have presence of A, so that should be 0. It does have presence of B, so that should have a 1. And it does not have presence of C, so that should be a 0. So we have 0, then we have 1, and then we have 0 for that second row. No, if you have, so you're thinking correctly that if we have 10 discrete categories, we have to generate 10 new columns. It's going to be 10 new columns that we have to create to indicate presence of those 10 categories. Yes, they have to be 10 new. And we're going to have a Pandas function that's going to do that for us. So if you're asking, is there a shortcut? Pandas will do it for us. Yeah, Pandas will do this for us. I'll show us the function. Luckily, Pandas does this for us. We don't have to do it manually. I'm just trying to show you the procedure of one-hot encoding and what it does so we understand it. Okay. Should it be a categorical variable or any data? So technically you can one-hot encode any data. Now, do you think it makes sense to one-hot encode numerical data? Do you think it makes sense to do that? Like, would we want to do presence of 2.3, presence of 3.5, presence of 4.7? Like, would we want to do that if we have a lot of, because what's the issue with floating point numbers? Okay. Yeah, I saw a question. 1 or 0 are constant with these numbers, no matter how many yeah. And does it make sense that only one of them is going to be a 1, and because you're only going to have presence of one of them in every row, and then every other one has to be 0. So you're only ever going to have a 1 once, and then every other entry has to be 0. That's what it has to be, because you're only going to have presence in one place. You're only going to have presence of one of these categories, and then every other entry is going to be 0. Is there a limit? And basically until you run out of memory, that's the only limit. So technically Pandas doesn't enforce a limit. Basically you can, if your data frame grows too big, like if you have too many unique values and your data frame grows too big, you are injecting too many new columns, that's when you would hit the limit, like the memory limit of the data frame of your machine. But like technically there's no limit. Okay. So let me do 2 things. Let me give you a real world example. Okay. Let me give you a real world example, and then let me show you the Pandas function that will do this for us, the one-hot encoding. Okay. So I'm going to give you a real world example first. So in the real world, there are a lot of categorical features that are, or I should say variables that are going to be useful for predicting something. So for example, there's a lot of things that are discrete when it comes to recommendations. So think about something like Netflix. The genre of a movie is a discrete categorical variable, isn't it? So a movie is going to be something like horror, comedy, adventure, action, thriller, right? It's going to be one of those strings. So if we were to build a model off of that to do a recommendation, which is what they do, they generate recommendation models to recommend movies to you. The models are not going to understand those strings, but they are going to understand the numbers, which we can do the presence features like in the one hot encoding. So a realistic example is to take like a movie genre that could be a unique category like comedy, action, romance, whatever it is, and convert that over to a one hot encoded column so that a model can use that for recommendation. So movie genre, and then we could have genre. We could have a new column that's genre comedy, genre action, and then genre romance. And then we have, but these are like our presence. These are like our presence features, right? I keep saying the word feature, which I haven't taught you guys what feature means yet. But let's say column. These are presence columns. So genre comedy, there's going to be a 1 here, 0 here, 0 here. Action, there's going to be a 0 here, 1 here, 0 here. And romance, 0 here, 0 here, 1 here. So now a model is going to be able to work with these numbers. So a model is going to like a recommendation system is going to like that data a lot more than it likes this. It's not going to like strings. And we're going to see that when we get into machine learning. When we actually build our own recommendation systems, we'll see why. The numbers are so much more useful to the model than strings. So that's a real world example. And that's not just for recommendations, it's for a lot of different predictive models. A lot of predictive models care more about the numerical data rather than strings. So it's in our best interest to convert any categorical data into numerical data prior to building a model. It's really important to do that. So we haven't learned that yet. We haven't learned how to model or do anything like that yet, but we will. Give us some time, we will. Can Pandas use drive space as memory? What do you mean by? Okay. Before I show you the Pandas example of converting things into the one hot encoding. Okay. Okay, so the way that we can do this in Pandas automatically to do the one hot encoding is a function called get dummies. So in Pandas, there's a function called pd.getDummies, and all we have to do, all we have to do is pass in this column of your numerical data. And actually, what getDummies can do, getDummies is a very flexible function. You can pass in more than one column at a time. So you can pass in multiple categorical columns and it will convert all of them into their one hot encodings, which is pretty useful. But in this case, we only have one column. So we're just going to pass in this category column. Now, you can optionally, you don't have to do this, but you can specify a prefix, which is the prefix is for the new generated column name. So that the prefix is the new generated column name during the encoding. So when we do the encoding, we could name this whatever we want. We can name it presence. We can name it. Typically, the default behavior is just to name it the column. So the prefix is just the column name. In this case, it is category. So, for example, this means that our new columns are going to be category prefix and then the whatever the category value is. So category A, category B, etc. So whatever the discrete options are for that column. we can have the prefix. Now, one other important part of this is by default, the get dummies is going to use Booleans. It's going to use true or false to indicate the presence or absence. But we want to use numbers like 1 or 0. So the way that you do that is you change the D type to be an integer. So we want it to be integer result, which will change the true or false into 1 or 0. So we want to purposely end up with numerical data, right? We want to take our categories and end up with numerical data. So when we run this, you can see what we get. We get now this should make some sense to us, this result, because what we're getting here is the first entry is an A, so we get presence of A, 0 presence of B, 0 presence of C. That makes sense for the first entry. If you go to the next entry, it's a B, so we should have a 1 here in the category B column, which indicates presence of B. And so then the next entry is A, we get presence of A. That makes sense. The next one is a C, so we get presence of C there. The next one is a B, we get presence of B. The next one is an A, we get presence of A. So get dummies does the one hot encoding for us, and the only thing we generally want to remember is to put in this data type of integer in here, which will ensure that the results end up as 1s and 0s, which is what we want. We want to convert those strings into numerical values. How it is used. I was kind of describing how it's used. I mean, so let me ask you this, like from a mathematical perspective, if we're building a model, how does a model that does mathematical equations, how does a mathematical equation know what to do with a string? This is the fundamental issue of why we have to do this, is it's not going to know what inherently to do with a string. It doesn't know what to do with B. It doesn't know what to do with A. It doesn't know what to do with C. It doesn't know what to do with B, right? There's no way to really incorporate that as a number into a model. It's not really a way currently. Now, do we think that we can incorporate 1s and 0s? Yes, we should be able to incorporate 1s and 0s. So it's to our benefit to turn this data into this data. This is the same data. It's the same data. It's just represented differently, but it's the same data, right? It really represents the same data, just in a different format. One is one hot encoded and one is the original categories. Models are not going to be able to use this format. Models are not going to be able to work with that. Models can't work with these strings. But it's not like now they can't work with the strings, but it's not like we should ignore it. It's still useful information to know that, okay, this data is category A, this next row is category B, this next row is category A. Let me give you an example. In the house prices data set, do you remember how we had data that was number of bedrooms, number of bathrooms, and square footage? Those were all numerical. There were pretty useful categorical columns as well. So there were things like the neighborhood or things like the zip code, things like the address that are important categorical features as well that give some meaning to the house, like what state it's in. The state is a discrete categorical feature that may be really useful to tell what the average, like the price is going to change based on the state. So that is a useful variable to know, but we can't use the state as a string, but we can use presence or absence as 1s and 0s. So that's where it's going to be used, is in our modeling. We haven't learned modeling yet, but this is where this is going to be an incredibly useful Pandas function. Get dummies, right? Get dummies is going to be an incredibly useful Pandas function to do one hot encoding. Okay. All right. So as an alternative, something that we can also do that is going to be useful when we are doing modeling and we want to, instead of doing presence or absence, maybe we want to assign each unique category with a numerical label that increments. So for instance, we could have a mapping here that says, well, A should be assigned to 0, B should be assigned to a label of 1, and C should be assigned a label of 2, let's say. So we can encode this way, which will also change over those strings into numbers by assigning a label to every unique category. So we're going to do is assign A to 0, assign B to 1, assign C to 2, and on and on and on. Like if we had a D, we would assign that to 3. If we had an E, we would assign that to 4, and on and on and on. So we can do this, and then it instantly maps our data to a new column that would be like 0, 1, 0. It's exactly this data here that you see, right? All of those values get mapped into their labels. And so this is called label encoding versus one-hot encoding. This is just a slightly different way of doing it. When we do modeling, we'll always do one-hot encoding. Label encoding is useful when we want to assign a label to a category for the thing that we are trying to predict, but not for the input variables. The input variables, we usually will always do one-hot encoding. But for the independent variable that we are trying to predict, if it happens to be a category, I'll give you an example. So for like, let's say we were trying to predict fraud, and we had we had fraud, we had a column called label, and it was either a string that was fraud, not fraud, fraud, not fraud, and on and on and on. So there's only two possibilities. We could label encode this to have a new label that would be like fraud is a 1 and not fraud is a 0. Fraud is a 1, not fraud is a 0, and on and on and on. So label encoding is useful for the thing that we're trying to predict. We can assign a label to it that is numerical because, again, a model is going to struggle to predict a string. A model is not going to be able to predict a string, but it can predict a number. It can generate a number. So it makes a lot more sense to convert the thing we are trying to predict over to a number versus keeping it as a string, like fraud or not fraud, or cancer, not cancer, cat versus dog. We could assign a label of 0 or a 1, or maybe if there were 10 categories of animals, like cat, dog, leopard, panther, cheetah, wolf, we could assign like 0, 1, 2, 3, 4, 5. Like we could assign a bunch of numbers to those for the thing we're trying to predict. Okay. So one-hot encoding will be used for modeling for our basically our variables that go into the model, and label encoding will be used to convert the what we are trying to predict, right? The actual outcome label over to something numerical, so the model can have an example of how to predict that, like what number should it result in. Okay, let me show you how you can get the labels. It's actually not that hard to do. There's actually multiple ways to do it. We're going to see a different way to do it down the road that involves the Scikit-learn package. But for right now, we're going to just use Pandas. So the way we can get the label encoding is we can first convert our data to a categorical type. We've actually already seen this using the pd.categorical is an alternative to convert to categorical. But once we convert to categorical, we access the categorical attributes by so we access .cat to dot cat to get the categorical attributes, such as the label encoding, which is from the codes. Codes gives us the mapping encoding values. So dot codes gives us the unique label encodings that we have for those different categories. So for instance, as I was telling you earlier, A gets mapped to 0, which we extract from these codes. A gets mapped to 0, B gets mapped to 1, A we already know is 0, C gets mapped to 2, B gets mapped to 1, and A gets mapped to 0. So in essence, we have converted our categorical data again into something numerical. It's just this is a different strategy than doing one hot encoding. It's doing what we call label encoding, which is going to be done for a different purpose. Usually, it's done for model outputs. One hot encoding is done usually for model inputs as data going into a model. And label encoding is usually done for data that would be the output of a model. Again, we haven't learned about modeling, but hopefully that is reasonable why those would be different, why we need a different strategy to convert from string to numerical, depending on if we're dealing with inputs or outputs. All right. So there is some extra practice here that, again, I will leave to you guys. Feel free to do this between now and next Monday. This is just extra practice for you to work through doing some converting of existing columns in the. This is, by the way, this is for the housing price data set. So you're going to be doing some practice with the house price data set to analyze the year built and year remodeled ad to convert those to datetime format and extract things like the year, month, or day because these are dates. Calculate the difference between when the house was built and when it was remodeled. So you can subtract those dates, calculate the difference, which will give you a time delta object. Count the number of categories in the categorical features. So some of that data, if you remember, is going to be categorical. So those are going to be things like the zip code, the state, the address. So sometimes we want to know how many of those houses are from Massachusetts, how many are from New York, how many are from California. We should be able to do value counts to determine those numbers. And then we also, I would encourage using something like the states to do the pd.get dummies to get some practice with building one hot encodings of the data. So I'd recommend picking one of the categorical features or categorical variables and doing the get dummies with it. Yeah, the house price is CSV. That's what this wants you to practice with. This is with the house price CSV. Housing data set, which is the house price CSV. Yeah. Yeah. So definitely practice with that one. All right.
So this is going to be our last notebook in Pandas, so inside of lesson 4. But as I said earlier, by no means will it be like the last time that we work on Pandas. We will be working on it quite a bit as we continue because most of the time, anything we do is really going to be working with Pandas in general. So this definitely won't be the last time we work with it. But I wanted to wrap up with some additional topics in Pandas. One is going to be working with text data. There may be sometimes a need to work with strings, like some of our columns could be strings and we need to manipulate those strings. So I wanted to basically describe how we might do that and see some examples. I also wanted to show us like different methodologies for iteration over all of the rows inside of a data frame and kind of caution us to those methodologies and what the proper way to basically apply a function is to every single entry in a column. As you can imagine, that's going to use our apply function, but there are other ways to kind of iterate through every single row if for some reason we needed to do that. It would be very rare. I'll point that out, the kind of the syntax that we would need. I wanted to briefly describe sorting. We've kind of already done that, so I won't spend too much time on it, but we can definitely sort a data frame according to different columns. We can use those as kind of our sorting columns. And then just briefly talk about how you can plot things with pandas, knowing that, we have additional plotting libraries that we're going to learn about in lesson 5 coming up that will take care of plotting for us. But Pandas actually does have built-in plotting support to quickly do plotting without having to go to those other libraries and explicitly build out plots. Like if you just want a really quick one, like if you want to plot a column and figure out what the trend of that column is, you can easily do that within Pandas without having to use another plotting library. So it does support built-in plotting. I'll show us that. But let's start with text data. So if we have strings, kind of just like with series, we can access string attributes by using the .str attribute of that column. So this data is all string data. So we can access the str, which gives us access, kind of like how dates are the .dt. They give us access to things like day of the week and month, day, year, those kind of things. If we do str, we can do different operations on the string and access different attributes of the strings. So for instance, we can uppercase everything, we can lowercase everything, we can get how many characters there are in that string. So for instance, like the hello string has 5 characters, so its length is 5. World has 5 characters, its length is 5, and on and on and on. You can do different operations. So this finds the length. And notice that we are getting that from the str attribute and then doing different operations on it. So if you're ever working with strings, you're likely going to find yourself using the str attribute and then doing functions on that to kind of operate on that whole column. As I said, you can lowercase everything. So here we're creating a new column called lowercase, which takes the existing column of data we have and lowercases it. So it removes all those uppercases and lowercases everything. You can see there. We could uppercase everything back, which would do upper. So you can see how that uppercases every single character, but we can also lowercase every single character, which is what we had before. So pretty straightforward. Like working with strings isn't something we'll do that often. Most of the times when we're doing data science and modeling and we have strings, we normally won't work with it too much. We'll actually just convert it over to one-hot encoding to use it with models. So it'd be very rare that we have to do operations like this, but just pointing them out to you that we can operate on strings if we need to. Okay. So another one is like we can check and see if strings contain any other substring. So this can be like checking if this data is within this existing string. So the only one that would return true on, this is something that's going to return a true or a false, is going to be that last one. So data science definitely contains data as a substring of that full string. So it returns true. So you can check and see if certain strings contain certain elements, which would be like certain characters. Like we could see if it contains an O, if it contains an L, if it contains a P. So we could do things like that. So we could check and see if things contain the P. Of course, Python is the only one that does, so it returns true in that example. Okay, pretty straightforward, I think. Any questions on these kind of things working with strings? There's more functions. I'm not showing you all of them, mainly because again, it's going to be very rare that we would ever really need to work with strings. Usually we're just going to convert them over to one-hot encoding because the strings are usually going to represent some type of categorical variable for us when it's in our data. Identify space? I think so. Well, we can check that out. So I have a single white space here, and data science contains a space. So yeah, the substring of just a single space character. Space is a valid character, like white space. It is a character, so this is the one that has space. Okay. So what I wanted to get to next was something more important, which is going to be how we operate on collections of rows at a time from the data frame. And data frames actually support a couple of objects that allow us to iterate through the entire data frame if we need to. However, we should be really cautious if we find ourselves looping over the all of the rows using something like a for loop. It's generally discouraged because it's very slow as an operation. So it's very rare that we should ever find ourselves having to do a for loop where we work our way through every individual row. For one thing, most of the data that we work with will have lots of rows, so that will be incredibly inefficient, looping through every single row. And we generally don't need to do that when we have something like apply, or we can do direct operations on columns that will do a calculation to every single row all at once. There's not really a need to loop over every single row. If you find yourself doing that, you're likely doing something wrong, and you should rethink what you're doing, just because it's going to be incredibly slow to do that. But Python does support a couple of functions on the data frame that give you an access to every single row in the data frame, and you can see what they are here: iter rows and iter tuples. I'm going to show you an example of those, but it'd be very rare that we would ever need to use these. So let me show you an example of what I mean by this. So notice that we have a data frame built out here with two different columns and only three rows. So we have column one and column two. So really we have data that looks like column one, which is column one, which has data that looks like one, two, three. And then we have column two, which has data that looks like A, B, C. So very simple data frame. Now, what this code here is going to do, this df.iterRows, it's going to give us the ability to access the index and the row as a tuple. So essentially what it's going to do is loop over the entire data frame, all rows, one row at a time, and give us access to the entire row. Not only that, but the index, which is index zero, this is index one, this is index two, and it gives us that in a tuple. So the first time through the data frame, you can see what the index is. It's zero. We actually print that out, print out the index, and we also print out the value at column one of the row and the value at column two of the row of the current row in the iteration, right? So on the first loop, on the first pass through the data frame, we are on the first row. So we have index zero and we have a one and an A as the two values from column one and column two. That makes sense. That's what this is. Then we go to the next iteration, which goes to the next row, and that gives us index. We are now on index row index one, and we have column one's value is now two, and column two's value is now B. So we can have access to those elements of the row by doing something like this. Okay. And then on that final iteration through, we are on row index two, and the data that's in column one is a three. The data that's in column two is C. So you can see that here. Okay, so iter rows gives us the ability to access the entire row at once, and then we can access particular items of that row based on the column name, just as we would like in a data frame where we put the bracket and put the column name. So we can access that elements of the row in that way. I should caution you that this is very slow. So, unless there's a very specific reason why we need to loop through every single row, we generally shouldn't be doing this. You could argue like one of the reasons we might want to do this is to manipulate this row element, or this row element or whatever. Like maybe we want to add them together or multiply or do some operation. And there's going to be different ways to do that that are much faster and do not involve an explicit loop over the data frame. I'm going to show us those. So it's generally going to be discouraged to do a loop like this. If you find yourself doing it, try to not do it. Try to think of a different way to do your operations. You really shouldn't be looping over every single row. It's generally discouraged. Okay, but there's the code to do it. All right, so let me give you an alternative. So like if for some reason we wanted to go through every single row and multiply everything by 2, well, we have a way to do that that does not involve looping through every row. That's going to be much faster, which is using the apply function. So we've already seen this with a series. Remember, what is a column? A column is just a series. So of course we can do apply to any column in the data frame, and that will allow us to manipulate that column and multiply every element by 2, square it, take the logarithm, whatever we want. This is a lambda function that we are applying to every entry in this column that will take the entry, which is what this argument is, x, and multiply it by 2. That's what this lambda is doing, is saying take your value and multiply it by 2. So when we apply that to this existing column, we are going to get a new column that has every element multiplied by 2. So we have a 20, we have a 40, and we have a 60. So pretty straightforward, but if you ever want to generate a new column with a mathematical function of an old column, generally you're going to want to use apply. Now, could you do this with the for loop? You could. You could iterate through each row and take the value that's at the existing column and multiply it by 2. That's going to be slow. That's going to be slower than if we just did apply and did an apply function to this entire column, which Pandas has an optimization to do apply. It does it so much faster than manual kind of iteration through every row. So again, like if you want to do an operation to every element in a column, use apply. You pass in that function to apply, and that will apply that function to every row of that column. Okay, so we've seen this before. So nothing that new, but just showing you again, and applying a function is going to be faster than if we looped through here. So like what we could do, let me show you the alternative. So the slower alternative is to do something like for index row and df.iter rows. If we did a row and we generated a new column equals row, and we access the existing column, and we took that and multiplied it by 2. Now that will do the same thing. It will take whatever is in the existing column, multiply it by 2, and set that as the new column element. But this is going to be, there's no reason to really do it this way. It's going to be slower. It's less readable than if we just did apply and took this existing column and applied this function to it. This will be faster. Pandas has optimizations for doing apply. This will be slower. Don't generally want to do this. All right. And then let me show you another alternative notation. So if you're doing something really simple, and you don't need a complex function here, like multiplying by 2, I would argue is really simple. You don't need anything that fancy. Like something simple could be like adding 2 columns together, or multiplying 2 columns together, or dividing 2 columns, or subtracting 2 columns. Those basic arithmetics between columns, or even with a column and a constant, like multiplying everything by 2. You can do what is called a vectorized operation, where you actually take that whole column and you do arithmetic with it to another column. And Pandas will optimize this. Pandas optimizes this operation to be really fast. Now, why does it optimize it? It's because it uses NumPy under the hood, and it turns out to be an incredibly fast operation that would be so much faster than looping through every row and adding this row element with this row element. Like we could do that and get the same result, but it would be so much slower than if we did it this way. So taking the entire column of A, adding it to the entire column of B, we don't need to loop to do that. We can just directly do it. We can just directly do that arithmetic between the columns, and that will give us the new result, which adds those together. So that is called doing a vectorized operation because we think of the whole column as a vector, think of the whole other column as a vector, and we're adding two vectors, which is a really simple, it's like adding two NumPy arrays. It's a really simple operation. Okay, so you can do a lot of vectorized operations. You can do, another example would be instead of apply, we can actually do new result, or let me actually call this double result would be df, take an existing column, so let's call it column A, and multiply that by 2. Okay, or multiply it by 3, whatever your favorite constant is. And that will generate a new column that takes the column A and multiplies it by 3. Okay, so 3, 6, and 9. So this is an example. We could use apply for this, which would be like df column A dot apply and then lambda x times 3. Like we could do that, but the doing it this way is actually going to be faster. And so when you have something really simple, we can just directly operate on the column most of the time and avoid doing apply, avoid doing for loop for sure. We never want to do that. It's going to be incredibly slow. How would you average a set of columns? So that would be using the built-in mean function. So you pick a set of, like, you pass in a list of column A, column B, and then you do like np dot mean. You could do it that way. Does that make sense? Like you pass that into the average, like a NumPy average, or you could do it that way, or the alternative would be to do dot mean like that. You could do it like that. So we can't forget our statistical functions, right, that we have on our data frames. Could we do this by looping through every row? Sure, but it's going to be so much slower and inefficient. I would never recommend doing that. Okay. All right. So, just like with now we mentioned this example here to say you can also iterate over a series, just in the same way. So as an alternative to iter rows, you can loop over an individual column. You can loop over an individual column because remember, every column is a series. So you can grab the what are called the items, which gives you the index of that series. It's basically the index of that row and the corresponding data point in that column. So you can iterate over an individual column instead of all rows, which is a little bit better, but still there's very rarely a need to do that. Very rarely a need to ever do that. Yeah, so that's a good question. Is there any specific condition where only looping is useful, even if it makes the program bulky? So I would say only where you're doing something that is so complicated that cannot be put in an apply, that you need access to only specific, like you're doing a transformation that involves elements of the row, like maybe you're concatenating strings, doing some transformation, then doing like math with it. You're doing something so complex that you actually have to loop through every row, and it can't be encapsulated in a simple lambda. That'd be the only scenario I could see. Just something really complex. Yeah, just something so complex that you can't get away with doing it in a lambda, and you really have to do it. Or sorry, you can't get away with doing it in an apply, and you have to iterate through every row in order to apply that operation because you're doing something really custom. That's the only scenario. But again, like that's going to be something so complex, which would be very rare that you would do something that complex that you couldn't do in just an apply. Okay. All right. Any questions so far about iteration or doing operations kind of on the at the column level? Hopefully, so your options. So just to recap this actually, your options when you're working with columns is your first choice. If it's something simple like doing arithmetic or multiplication by a constant or applying a simple function like an exponential or a logarithm, you can actually just do that directly to the column like this. So if you can do that, that's actually going to be the fastest and most efficient way is to just directly operate on the column. If you can do that and your operations are really simple, you can get away with doing that. That should be your first choice is directly operate on the column. If you need to apply a more specific function, you can use dot apply. That should probably be your second choice, is to think about if I have a custom function, can I apply it to every entry in this column? That is going to be maybe you need to do that because you have a custom function you want to apply, and it's not so simple to just operate that on the entire column like a basic arithmetic here. So that would be your next choice is apply. Last resort, last resort, something so complex that you can't use apply and you can't use direct arithmetic would be looping through every row. That would be last resort, iterating through every row, and then utilizing those row elements to do some custom operations with. Okay, that should probably be the last resort. Okay. Let's go on to sorting. So let's talk about sorting the data frames. We've kind of already practiced this a little bit, so I won't spend too much time on it. But we do have the ability to sort data frames, which of course will rearrange it according to a column or maybe a collection of columns, and it can be, either greatest to least or least to greatest kind of sort. So you can see in this picture, like in this example, we are sorting based on the height column, which will rearrange it from least to greatest and kind of shuffle those rows according to the sorting. And so let's take a look at that with this example. In this case, we are going to take this data and sort it according to the age column. So one of the things we need if we're going to sort is to specify what column do you want to use to do your sorting, and that you can pass that in the by argument. So we are sorting by the age in ascending order. So ascending order because the ascending argument is going to be false by default, which indicates that we are sorting according to the age sorry, ascending is true generally, which means it will be a least to greatest sort by default. So ascending equals true is the default behavior. So if we don't pass anything in there, that will be what we get. We get a least to greatest. So you can see this gets rearranged where the age is now least to greatest. This is like in a spreadsheet, right? You take a spreadsheet and you go into a column and you sort your spreadsheet according to that column. It's kind of the same thing. Taking our data frame, sorting it according to this column. If we want to do descending, so if we want to do descending, we could do df sorted equals df dot sort values, and then we can do the same exact syntax where we pass in our column, except now we do ascending equals false. So this will now do the greatest to least sort. So it reverses that. Okay, so ascending false does a greatest to least sort. Okay, pretty straightforward, I think. Nothing, terribly interesting going on there. Oh, the other thing I forgot to mention is if you do sort values, it will not do it permanently to that data frame unless you do the in place argument. So if you want to permanently sort the original DF, you need to use in place equals true arg. So what that means is you would do something like df dot sort values. You could use the by age column, but in this case, we would do in place equals to true. And this will permanently sort this data frame so that going forward, its values will be permanently sorted. Notice that we didn't do that. We just did sort values, which return, it's just like all those other things that return a copy of the data frame that has been sorted, and we store that into this df sorted variable that we can work with going forward. So when we do this, this original data frame is not permanently altered underneath, right? It's not permanently sorted until we do in place. So if we do in place equals true, then going forward, this DF will be permanently sorted. Okay, so just like a lot of it's true of so many data frame operations. They're not going to be permanently altered until we do in place equals true. It's just how it is. Okay. All right. So the other thing is you can sort according to multiple columns. So all you have to do is in the by argument, just pass in a list, and it's going to go in order of the list. So what that means is it's first going to arrange the data frame according to this first column, which is the age, and then it's going to secondarily sort according to this if it can, right? So the age is the primary sorting because it is first, and then the salary would be kind of like the secondary sorting for any like tiebreakers, for instance. Like if the age was tied, then we would sort according to the salary from least to greatest. However, you can change the greatest to least or least to greatest as your primary or secondary sorting. You can actually change that in the ascending argument. You can pass in a list. So what that means is the age here should go from least to greatest because that is ascending true, but the salary would be kind of reverse sorted. So the salary should go from greatest to least if there was any tiebreaker of the age, right? So if any ages were tied, we would then sort according to salary, but that would be actually a greatest to least sort. So whatever is greatest would be first. Does that make sense? Like multiple columns can be used for sorting. Think of this as just here's your primary sorting, here's your secondary. You can have as many as you want. You can actually have as many as the number of columns that you have. You can sort according to those. Okay, pretty straightforward then. Let's see. You can also sort according to the index. So this is useful when your index is something interesting other than the default index. So this will kind of reverse the data frame because the index is of course 0, 1, 2 by default. And if we do an ascending sort false, this will kind of like reverse it in effect, right? Because now the it's now a greatest to least index sort. So the index 2 would be first, index 1, then index 0 is last. So you can also sort according to the index. This is useful when you have things like time. Like if your index is a date, you could sort according to like earliest to latest in terms of the dates. That may be useful. So when your index is something interesting, you can sort according to your index, which is pretty useful. So notice the syntax is a bit different. It is sort index rather than sort values. So sort values is used for any column you want to use to sort with. Whereas sort index is, of course, just going to use the index. So when your index is something interesting, that can be helpful. Like if your index is a collection of dates, you can sort that, which will go like earliest to latest. Okay. And we've already seen an example of sorting a series, so I won't really spend any time on this. We know we can sort a series. We've already seen that. The reason we're calling that out again here is because, again, what is every column? Every column is a series, so we can go into an individual column and sort it if we need to. And that may be useful to extract the values out of a particular column and sort it so that we can manipulate it if we need to. So we can always take a column and sort values just as we can an entire data frame. So no surprises there. All right. For large data sets, do you know if our data set or Pandas is faster overall? It depends on what you're doing to it. What did you have in mind? Like, if you're doing basic arithmetic, like if you're doing operations like this, like multiplication or addition of columns, I actually think Pandas is going to be faster because Pandas is backed by NumPy, which is pretty fast for doing those kind of things. I think Pandas is going to be faster for doing like basic vectorized operations, but anything beyond that, it could be slower. Yeah, I think for doing basic vectorized operations, I think it's going to be faster. I think you get in trouble with Pandas when you get outside of that. At that scale, yeah, it's going to be. I mean, there's other. By the way, there's other things that can work with data that's that big, right? There's other frameworks that can work with large data. Something like a Spark or something would probably be more ideal. Not that we'll cover that in this program, but yeah, generally for dealing with data at that scale, we probably would move outside of Pandas altogether anyway and be working with some other big data framework. Okay. All right, so let me finish up Pandas by telling you guys a little bit about some plotting. So if you have a data frame, you can actually quickly plot the column data by just doing df.plot. So a very simple function which will generate the plot. Now, we haven't learned about Matplotlib. That's going to be in our lesson 5, which we're going to get to next. But suffice to say that df.plot uses Matplotlib in the background. Pandas will use that, but we don't have to explicitly go into Matplotlib and build an entire plot to quickly generate one off of a data frame. So df.plot will build a simple line graph of each column. So it's plotting A and B at, where we have the x-axis is just the basically the row index. So I should mention that here. The x-axis is the row index. So that goes from 0 to 4. And then the y-axis is the data. Y-axis are the column values. Right, so it's plotting. If you take a look at it, it's plotting 1, 2, 3, 4, 5, and then 5, 4, 3, 2, 1, which are these two lines here. And you can see they even get labeled A and B. Something we're gonna learn about how to make plots. So I'm not too concerned right now about like how do we get this legend here? How do we make these different colors? We're gonna learn about that in a few minutes. But again, Pandas has the ability where we don't really need to do anything that fancy. We could just quickly plot a data frame if we need to do that. If we need to quickly plot it and we don't want to spend time setting up an entire plot, we could just do df.plot. One thing that I'm going to talk about in a little bit is this plt.show. So this code is the equivalent of print. This is basically the equivalent to print when working with graphs. So it's yeah, why not write that? It's because this is Matplotlib's way of doing the print function to say, okay, I'm ready to display the graph. It's like it basically is like a display function that comes from Matplotlib. So I'm gonna show us why in lesson 5. So hold on to that thought. I'm gonna show us why this is important in lesson 5 when we actually talk about Matplotlib. We haven't covered it yet, so I don't want to go too down that road. But it's in the next lesson. It's going to be in lesson 5. Yeah, this PLT part is Matplotlib, but this is not. This is just the dataframe.plot, which is what I want us to focus on. This part is from Matplotlib, which is basically the print statement of Matplotlib to like display the graph. So it's nothing that interesting other than saying, okay, I'm ready to show the graph. So go, it's like print. It's like print your graph that you have available from df.plot. df.plot generates the plot. So this code generates the plot in the background. And then we don't actually display it until we do plt.show, which will print it out. So this like renders the plot data and gets it all ready to be printed. And then plt.show is kind of like our print function that will actually then display it. So this code kind of generates the plot. This actually prints it out. So we're going to see if that doesn't make sense now, that's okay. We're going to see plenty of examples of plt.show coming up of why we want this to be here. Right. So Pandas isn't responsible for displaying the graph. No, it's responsible for building the graph with this basic DataFrame.plot function will generate the plot, but it's not responsible for displaying anything. That doesn't happen until we run this code. And Roberto, I would encourage you to try this. Like in your VS Code, try running this, try creating this and leaving out this and see if it actually prints it out. Okay. So this won't do anything until we do plt.show to actually render and display the graph. Okay. So I wanted to show you a couple other types. Again, not going to focus too heavily on this because we're going to get into building our own plots in Matplotlib coming up in lesson 5, which is going to be next. But we can do a bar graph as well. So we do df.plot and we pass in a bar parameter. This will create a bar graph that looks like this. So it takes our indices 0, 1, 2, 3, 4, and it generates a bar graph of the values in our data. So we have A in the data, which column A has values 1, 2, 3, 4, 5. Column B has values 5, 4, 3, 2, 1. So we display kind of a bar graph of that data here. And the only thing we really had to do is do df.plot and then change this over to bar. The default is just a line graph. So if we don't put any type in there, so like what we just did with bar, it's just going to build a line plot by default. Okay, it's just going to build a line graph by default. Okay, and it turns out that there's other types. I'm not going to get into them really because we're going to explore those in Matplotlib in 5.01. But there are other types that pandas can do out of the box. I will say that it's rare that we would actually use this as our plotting methodology. Generally, we will build the plots directly in Matplotlib code, which is what we're going to learn how to do next. Okay, that's what we're going to learn. But it's just to show you that Pandas does support doing like really quick plots on data frames if we need to. Like if we want to get a quick view without having to go into Matplotlib and write some Matplotlib code, we can actually quickly plot some characteristics of the data frame if we want to. Okay. All right, so there's some more practice here for you guys to try out. Mainly the interesting thing is working. Now there is another data set that is included for you guys. I want to see what the name of it is. I'm forgetting the name. Give me one moment. Let me make sure I have it. It's for lesson 4. I think it's still the house prices CSV. I still think it's the house prices CSV that this practice is meant to work with. So if you want to give that a try, I think it's looking at specific like precipitation or temperature. Um, I think, but there's some extra practice here. You guys can give it a try. All right. So what we're gonna do is move to lesson 5. Which is gonna be pretty exciting. We're gonna move into data visualization. So we're really gonna get into some specifics of how we build graphs, which is really powerful. Like that's gonna help us tell some stories about our data, build some graphs, build some different visualizations that may be pretty helpful for not only ourselves but stakeholders, right? Maybe they want to see some interesting trends or interesting visualizations of the data. we will see how to do that inside of Python, inside of these various plotting libraries. We're going to learn about like Matplotlib, like Seaborn, like Plotly, and turns out there's actually many others that are out there. We're gonna start with Matplotlib. That is the foundation. It's kind of like NumPy. Matplotlib is very much like a NumPy where Pandas is built off of NumPy. A lot of plotting libraries are built off of Matplotlib. So Seaborn uses Matplotlib and kind of builds off of it. Plotly does as well. So many of them do. It's worth our while to start with Matplotlib as the fundamental foundational plotting library and then kind of build off of that with learning about Seaborn, learning about Plotly. So we're going to start with Matplotlib and then kind of grow from there. But so we will cover this. We're going to go over to the 5.01 notebook. So if you guys want to open that one up, we will start there. Before we dive into that, we will take our final break here. So let's take one more break. Let's take a 5-minute break, and then we will come back and finish up strong with visualization, getting into lesson 5. Okay, so let's take a 5-minute break. Let's be back around 10:40. All right.
We're talking about data visualization. So really exciting stuff. We're moving. So far, just to recap, we've covered Pandas and NumPy, which are two really helpful libraries for manipulating data. And we will come back to that and do a lot with manipulating data as we move along in the course. So those things we won't forget, like we'll still be able to manipulate data as we go along. But what we want to do now is start to pivot into doing things with data, like telling a story through visualization. And so over the course of the next couple of notebooks, really this 5.01 is going to do everything around Matplotlib. And then 5.02 is going to do everything beyond Matplotlib. So things like Seaborn and Plotly, some more advanced plotting that we will see. But we want to get a really solid foundation of plotting. It's going to serve us well as we go forward and have to do more and more visualization of our data for multiple reasons. One, really to understand it better ourselves, which can help when we're modeling, but then to tell that external story to stakeholders or people who may want to know more about the data and see trends, and pictures usually help tell that story. So visualization is going to be really important, and we're going to spend the rest of today on it, and really our next session on Monday next week on it. So that's kind of the agenda. And so there's many ways to do data visualization that are beyond just working in Python. So you guys may be familiar with like BI tools to do data visualization and things like Tableau, and you can even build graphs directly in Excel. Those still exist, and we're not saying like those should be definitely replaced. It's just when we're working in Python and we're building models and we're doing a lot of things with our code, we still want that ability to use our code to create visualizations. That's still a really powerful idea. And we can get insights, we can find out trends, we can find out patterns, all of these things. And the pictures that we generate from our code can help tell that story, help us communicate that story of what we're seeing in the data. Okay. So 3 libraries we're going to cover: Matplotlib, Seaborn, and Plotly. Matplotlib is the foundation. Everything else is built off of that when it comes to visualization. So that's where we'll start. And Matplotlib gets its inspiration from MATLAB. So if you ever worked with the tool MATLAB, the plotting that's in Matplotlib is actually very familiar to, or very similar, I should say, to the plotting that's done in MATLAB. That's kind of where it gets its name from, as far as a plotting library inspired by MATLAB, Matplotlib. Matplotlib is great in terms of building out a bunch of different plots, and we're going to see examples of those, things like histograms, pie charts, scatter plots, bar graphs, even more advanced things like tree maps. We're going to see examples of all of these. So they can help, Matplotlib can help us build out those in a very systematic and programmatic way with our code. Okay. The first place we're going to start is by seeing how Matplotlib kind of works with the mechanics of it, with a basic graph, such as a line graph. So this is a basic graph that connects points in line segments. So usually we would use a graph like this for showing trends over time or over iterations or over an index that's growing. We can kind of see how something is trending by connecting all of our data points in a line. So that is called a basic line graph. We are going to see how Matplotlib works, and I'll give you a high-level overview of it right now before we dive into the code. Essentially, what you'll see with Matplotlib is always the same setup, which is you have your core plotting function, which will come from the PLT, the Matplotlib library. That is aliased to PLT. So anytime you're reading code, the industry standard is to alias Matplotlib's PyPlot module, the Python plotting module, as PLT. So this is the industry standard. Alias is PLT. So anytime you're looking at other people's code and you see PLT, you should instantly be thinking, okay, this person's building a Matplotlib plot. Or they're using Matplotlib for something. So that is pretty industry standard, just as like NumPy is industry standard alias to MP, Pandas industry standard alias to PD, lots of different standards that we will learn as we learn more packages. But the thing that we will always see is basically our core plotting function. So we will always have our core plotting function first. Core plotting function first. And then we will always have code after that that manipulates the figure. So we have Matplotlib code after the core plotting code to manipulate the rendered graph. So what that means is we will generally have code, and don't worry, I'm going to come back and explain what this is doing. I'm going to explain all these arguments to us. But what I want you to see right now is the separation of the code from the core plot building aspect to the figure building aspect, which is what these things do. So what these things do is do various manipulations to the rendered graph. So this will add an x-axis label. This will add a y-axis label to the graph. This will add a title to the figure. This will add a legend, and this will basically print the plot, which is always last. So when you see this is basically, I'm done formatting, print the graph. It's basically what that signals to the reader of this code. I'm done doing any formatting. Go ahead and print the graph. Yes, Roberto, the formatting. Yes. So all of this stuff is AKA formatting. Formatting the graph. So Matplotlib supports adding different labels, adding different titles, adding a legend, which it generates automatically based on your inputs and what you label things. So it will generate a legend, and what I want you to see is where those things show up. So we have an x-axis label and a y-axis label. You can see that those show up here. So we get our x-axis label and our y-axis label that show up there on the rendered graph, the displayed graph. We get an overall title that always displays at the top. So this is that plt.title. This shows up here. And then we have the legend, which will automatically be put somewhere within the graph. Matplotlib will actually automate where that goes, depending on where it thinks it makes sense to put it, like based on the spacing. Generally, it favors putting it in a corner. So sometimes it'll show up in this corner. Sometimes it'll show up in the upper right corner. This is a little too crowded up here. It's close to the actual graph, so it will kind of block that spot from being used. And this is a bit too crowded up in this corner, so this gets blocked. So the only two spots the legend can really be are like here and here. So Matplotlib just will randomly decide, okay, it should go here. Now, you can customize that. You can put it where you want it to go if you put in some exact coordinates and you manipulate that. But generally, we won't do that. We'll just do plt.legend and let Matplotlib optimize where it should go within the graph. Okay. So plt.legend adds the legend. These things add those formatting elements to the graph. But what I want you to see is those really come after the core plot. So that's going to be the pattern for all of our Matplotlib examples. Basically, we will first have the core plot, and then we will do the formatting after it. And then at the very end, we do plt.show to print out the graph or basically display it. So display the graph. Display the graph. Okay. Okay, so I owe you talking about this, which I will next, the core plotting code, but does it make sense, the organization of plot and then format? Plot and then format, plot and then format. We will see that over and over again for the rest of these examples. We will see that setup, plot and then format. So all of these PLT functions do some type of formatting to the rendered graph. Okay. Now let's talk about the core plotting function. So most of these plotting functions are actually going to behave the same, where you use PLT and then you pass in the type of plot as the function. So you do PLT dot, let me make this in a comment, should be PLT dot type of plot. And then it will usually look like this, where you have your x-axis data, y-axis data, and then you have optional args come after that. So nearly every plotting function looks like this, where the x-axis data goes first, y-axis data goes second, and then optional args will go third. So in this situation, we have a NumPy array of points between 0 and 10, which we produce 100 of those linearly spaced between 0 and 10. That's what the linspace does. This creates, let me make a comment, this creates 100 points equally spaced between 0 and 10. And then what this does is it takes the sign of those. So this takes the trig function sign of x, where the x are these input points here. Okay, so it'll take the sign of that array and produce an array of all these sign values of these angles between 0 to 10. Okay, now, so in the plot, the plt.plot is the code for a basic line graph. So plt.plot creates a basic line graph. So that is the most basic kind of graph we can have, where we basically connect the dots of all of our y values, and that it generates a line in between all of those points. So plt.plot signals that we're doing a basic line graph. As you can imagine, like when we do later examples, we'll see plt.py or plt.bar or plt.histogram. Those will be our different graph types. But if we just do regular plot, that is a basic line graph. 10 is included. That's the confusing thing with a linspace. So linspace includes the 10. Yeah, linspace includes, because linspace is designed to be like, if you define a range, it basically wants you to do everything in that range and then have 100 total points that are equally spaced, including the end. Yeah, so linspace does include the end of the range. Yeah. And this will build 100 points in there between 0 to 10. Okay. Okay, so we have plt.plot. Now we have our x-axis data, we have our y-axis data. It turns out that Matplotlib is very flexible with the kind of data we pass in. It can be a list, it can be a NumPy array, like in this case, it's a NumPy array. It can be a series, which is very common too, to pass in like a column, which is a series of data. So let me make that comment, is that we can have lists, NumPy arrays, we can have series are all very common inputs here. Really, most of the time we'll probably be dealing with series because we're often going to be plotting data that comes from a data frame, and those columns are series, right? So, but it is flexible. It can be a NumPy array, which is what we have here with NumPy arrays. So after that, after your x-axis and y-axis data, you really have a bunch of optional arguments in here that do some styling on the actual plot. So for instance, we can make a color, we can have a string that represents the color. Now, this string can be very fancy. It can be a hexadecimal string that represents like a custom color if you want to do that. But Pandas has some support for just regular colors out of the box, like blue, green, orange, yellow. So we can change this line to be like we could change it to be green, and we can generate the plot and it will look different. So here it's now green. We could change it to be orange. So, and then it will be, we could change it to be red. There's some pretty standard colors there we could change it to. But as I said, like the color could actually be, you can come up with a hexadecimal code for a color and pass that in, and it will render that hexadecimal code for the color. So feel free, you can customize that. Let me just turn it back to blue. You can provide a label. So the label is used with the legend. So this is what the legend will use. Like if you have multiple lines, it will know that the blue one is labeled sine wave. So in the legend, you can see how it says sine wave here. So this is what shows up in the legend. Label is used with the legend. So we are tagging this as essentially the sine wave graph. We can customize the style and width of the actual plot. So we can bump this up to make it thicker. It's just an integer. So 2, 3, 4, 5, it just increases that width level. We can also change the line style to be like double dashed or single, just a regular line. There's actually, you can use like asterisk to make it like stars that are flowing. You can make it triangles. You can make it circles, which are like, so just a regular, like the default is just a regular line style. Okay, just a regular line style. And so that will generate as just a normal line that's connected there. But we could change that. Like if we wanted to have it be more of a dashed line, we could use the double dash there. This means we're generating 100 points in the array. So this array is going to have 100 total points that are between 0 to 10, evenly spaced. That's what this lin space means, evenly spaced 100. So if you were to draw this, it would be like we start at 0, we end at 10, and we generate 100 evenly spaced points between there. So this array should have 100 total points in it, 100 total values, right, in the array. Okay, so that's about it. Like now, Matplotlib has some pretty extensive documentation as well for what kind of arguments you could pass in here. But most of these guys are affecting the actual plot itself. And then we can have formatting at the figure level, which is what these guys do here. So these format the overall kind of figure, and these arguments inside of here affect the individual plot of this line. Okay, so hopefully that makes sense, that we're separating the two, and we're building this line graph because it is plt.plot. We're going to see some other like plt.histogram, plt.bar, plt.boxplot. So we'll see some other kinds of plots coming up, but this is the most basic that we can have as a line graph. Okay. If that's the case, let's go on to another important kind of plot, which is going to be the scatter plot. So now the scatter plot is really useful in the sense that it helps us plot two different variables against each other as coordinates. So it is a plot that will have data on the x-axis and data on the y-axis. And then we use the x data and the y data, and we think of that as like a coordinate, and we go ahead and plot that somewhere on this grid. So we have like x comma y, that could be a point that looks like this. So that means that there's some value of x and some value of y that drives that point. And the reason that's so important is if we go ahead and plot all of our values, we can do that over and over and over for these two variables, let's say, and we can start to identify if there is a trend. So we can see, like, do all the values tend to trend in the same direction? Do they tend to trend in this direction? Are they pretty flat? Are they pretty scattered all over and there's no obvious trend? That's useful information to know. So the scatter plot will just take points and kind of scatter them on the graph. And then from there, we can kind of observe if there's any trends to it. So that's very helpful. So generally, this kind of plot is going to be used with two different variables, one on the x-axis, one on the y-axis. So think of it as two different columns. Like maybe we plot the square footage against the number of bedrooms, or the price against the number of bedrooms, and see if there's any trend there. The scatter plot is really useful. How do you use the scatter plot? So that's a great question. So usually you use the scatter plot for two reasons. One is to identify any relationships amongst variables. So if we have like a feature like square footage and then another like number of bedrooms, we could plot those to each other and see if there's a correlation. So if there's like a strong kind of linear trend amongst them, what that would tell me is I likely should get rid of one of those variables because they are trending in the same direction, or maybe they always trend in the opposite direction. In which case, like, there's a strong relationship there. I don't want to include both in the model. The model is not going to like dependencies between variables. It's just not. That's not a good thing to include. And so the plot can help us visualize if there's a dependency. Like if I were to draw the scatter plot between two variables, x and y, and I see a plot like this would tell me there's a strong linear relationship between these two variables. Does that make sense? And like if there is, I probably want to get rid of one of those variables because it's redundant information, right? If I know information about one of them, I automatically know the information about the other because they're always going to trend in the same direction. So I will favor dropping one of those because we don't want that redundant information. We don't want those dependencies in our model. It's actually going to degrade our modeling effort if we have those dependencies in there. Okay, so that's one way we can use it. The other way is we can actually make a plot of our independent variable, which is the independent variable is the thing. These are things that we are going to use as predictors, so as inputs to our model, and then the dependent variable, which is the thing we're trying to predict, right? So let's say we're trying to predict the price, and we take a look at the square footage. We can see if there's a relationship there. We could probably guess there's going to be, like, the higher the square footage, the higher the price. We could see that on a scatter plot. And what this would tell me is, okay, this is likely a very good predictor of this price. We should include it in our model because it has a strong relationship from an input and output perspective, right? So that's another way we can use the visualization, is to help us identify which independent variables have an influence on the dependent variable if there's a relationship there. Do those make sense? Those two use cases? So we're determining relationships between variables. We don't want there to be dependencies between variables. That's actually a bad thing. All right, so let me continue then, and let's talk about the scatter plot and take a look at the code. It turns out that it's not too bad of the code in the sense that it's going to be very similar to the plt.plot, where again, I'm going to go into detail on this part of it, but what I want you to see is the overall organization of the code. We have our core, this is our core plotting code here again, core plotting code here. And then we have our formatting code that comes after it. So figure formatting code that comes after the initial after this initial core plotting. So this builds the graph. This will build elements on the figure. So here we have the y-axis, and then we have the x-axis label. You can see those are things we are adding to the graph here with the plt.x label and plt.y label. And we do a plt.title, which will generate this guy here at the very top of the plot. So that is there again. We have a plt.legend, which is the legend here isn't that useful to us because we're just plotting our points everywhere. So do we really need a legend? Maybe not, but there it is, just for completeness. And then of course at the very end, this is signaling let's display the graph. We are done with any of our formatting. Let's display the graph. Okay. All right. So let me go back up to the actual plot and the data. So what's really interesting about this is we first generate a variable called x, which has 100 random points. Okay, so this will give us 100 random points that are uniformly drawn between 0 to 1. So these are 100 random points between 0 and 1. Okay, so this will build 100 random data points between 0 and 1. What I want you to see is we purposely take 2 times whatever points we had in X, and we add a little bit of noise to it. So we purposely take 2 times X, and add randomness between 0 to 1. Okay. So if we're doing 2 times x and adding a little randomness, do we expect to see a linear relationship between these somewhat? Like, would we expect that? Do we think? Do we expect to see a trend between x and y is what I'm asking. Like a clear trend if we're literally generating y by doubling x. We're basically taking, to generate y, we're doubling x and adding a small amount of noise to it. That's all we're doing, adding a small amount of randomness to it, because these are going to be values between 0 to 1, fractions, right? Fractions between 0 to 1. We're doubling everything in x and adding a small amount of noise to it. So yeah, I would expect there to be somewhat of a relationship between these two, to the extent that, there is some randomness here, so it's not going to be perfect, but it's pretty close. This is literally 2 times x plus some noise. Okay. So if we do our plt.scatter, we're going to put our x data and our y data there as the first 2 arguments. That's very standard. This means that on the x-axis, I'm going to be plotting the x data. On the y-axis, I'll be plotting the y data, and those will form our xy coordinates that will be plot in the scatter plot. We're going to make everything green. Again, that's customizable. We could make everything blue, everything red, everything orange. Pick your favorite color, and we can make those whatever we want. Pretty standard is to make it a single dot. So the O is the standard marker. This is what the marker is. The marker is what every point will be displayed as. So in this case, it will be like a circle, just an O that is filled in with the orange color, whatever color we have. But we could pick different things, like we could pick an asterisk again, or different shapes are eligible there. So just look up the syntax in the Matplotlib. documentation if you want to see what possibilities there are. But O is the default, which is just a circle, just a small circle to be filled in there for every point. We have a label here. Again, this is what the label just is what will be displayed with the legend for this data. Okay, this is just what goes in the legend. Okay, let's run this. So we have all of our points. Let's actually, I'm gonna make this blue just because it's easier on the eyes for me. Okay, so random data. So we kind of see the trend now. There's some randomness to it, so it's not perfect, but there is a little bit of a trend here, kind of like this, which we'd expect, right? But it's not perfect because there is some randomness added in there, and we start out with fractions between 0 and 1. We multiply them by 2, so not perfect, but there is a little bit of a trend from left to right, which kind of makes sense that would exist because we're literally, producing the values by multiplying by 2, adding a little bit of noise. But that's the scatter plot. Pretty easy to build, just plt.scatter. Again, I want you to see the core components of Matplotlib at play here. Here is our core plot, which is being generated from plt.scatter this time. Before we had plt.plot, which is a basic line graph. Here we do plt.scatter to build the scatter plot. Of course, we have our formatting stuff here, but we're passing our data into this, which is the important part. Pass your data into that core plotting code in order to make a visualization of it. Okay, so let's go to the bar graph. So in the bar graph, generally what we have are values for different categories. So for instance, we have a category A here, which has a value of 25, category B, which has a value of 40, and category C, which is going to have a value of 15. So what we can do is do as you might have guessed, plt.bar will be our core plotting code, which will generate a bar graph using the x-axis categories. So those are the strings there, category A, category B, category C, and the corresponding values list. So here is an example where we're not even using NumPy arrays, we're just using a basic list to pass in data, and Matplotlib is very flexible. It can use lists, it can use NumPy arrays, it can use series. All of those can be valid input data to this PLT core plotting function. We can change what colors of our bars are. We could change them to blue, orange, green, whatever we want. So these are just the colors of the filled in bars. We could change what the edges of the bars, their color, like we can make them white, we can make them black, whatever we want. And then here's our usual label for the legend. We have our usual formatting here. We put an x-axis label, categories, we put our y-axis label, values, and we do a title on the graph. We add a legend and we display the plot. So by this point, pretty standard stuff that we've seen from our core plotting code and our formatting that we have for the graph. Let's run that. So you can see here, this just builds a basic bar graph here where we have category A has a value of 25, category B has a value of 40, category C has a value of 15. So where this graph might be useful is something like the value counts. If we wanted to see how many discrete values there, how many occurrences of those discrete categories there are in a variable, we could do the bar graph of the value counts to get this visual comparison of how many there are per category. That might be useful to do. So that's a good application of the bar graph, is to use it in conjunction with the value counts data to get a visualization of how much difference is there between category A to category B to category C in terms of how many values there are inside of a column for a categorical column. Okay.
So take a moment to pull this one up. This was the 5.01 notebook, and we were a little bit down into the notebook on where we left off was on the box plot example. So I'm going to go back through that entirely to start today. But prior to that, we had some different examples from Matplotlib that dealt with doing different plots, like a bar graph, a scatter, which is the plt.scatter. You guys remember that? And we had just a regular plt.plot, which is a line graph. We have data on the X and Y axis. The typical format of this plotting code is that we usually have our main plot that comes first, and then some formatting through PLT that comes after that. And then usually at the very end is kind of the print statement, plt.show. If you guys remember, that was kind of our format. This kind of stuff with PLT adds on formatting to the figure. So it adds things like labels, titles, legends. It adds different stuff that shows up here on the figure. What's actually producing the graph is this line of code here, right? The plt.plot or plt dot something, which is, some type of plot type. So in the scatter plot, it was plt.scatter. And then we had our formatting code here, and or plt.bar was another example. And we had just gotten to plt.boxplot last time, and I was kind of describing what this kind of graph shows, which I think is an interesting graph. If you've never seen a box and whisker graph, this is a way to plot data that is, maybe from different groups. So we have, like, in this scenario, we have three different arrays, three different NumPy arrays, and we label them as group one, group two, and group three. But the box plot, what's really interesting is that it shows you kind of the spread of that data and how distributed it is. It's one way of viewing that information. I'll show you why. Just to recap it, is with a box plot, the reason why it's called a box and whisker plot is you always get a kind of a central box that's drawn around the median. So this, where this notch is, by the way, the notch is kind of an aesthetic. It's optional to have the notch. You can turn it off. I think by default it's off, but we turn it on here so you could set that to false, which is the default, and it would just do a rectangular box. But the notch kind of highlights where the median is, which is nice. And so that's going to be this line in the box here. That's the median of the data is right here at this notch. So the median of that group, median of that group, median of that group. That's where that notch is. Now, what the box represents is the 25th and 75th percentiles. So down here at this line is 25% of the data falls below that, and then 75% of the data falls below the top of the box. So this box, its kind of height of that box is actually a significant value. It represents a range, and we'll actually define this later on when we get into statistics. It's a special range that represents this kind of middle 50% of the data from the 25th up to the 75th percentile. So represents that kind of middle 50%. And depending on the height of this box, it kind of tells you how spread out the data is, right? Because if it's really compact, that means that most of the data is kind of centered on that median. And a scenario where that's happening is this box here. This is pretty compact, where the box height is pretty short, right? The box height is much shorter compared to this one, and this one's even more short compared to this one. What that means is there's just a wider range centered around that median where the data is. So there's more spread, it's more variation there, away from that central kind of median point. So a box plot's really good at showing that box so you can kind of quickly get a sense of how things are distributed around the median. Is it pretty compact? Is it pretty spread out? Okay, so that's the box. The whiskers are these lines here that go all the way up to the top and all the way down to the bottom with a bar. And what that represents is the max and the min. So this is the max of the data, and this is the min all the way down here. And so that can also give you a good sense of how spread out the max and min are away from each other. So obviously, if those whiskers are really tall, that means that the maximum is occurring pretty far away from where most of the data is. Same thing with the min. So if that bottom whisker is pretty tall, that means that the minimum is occurring pretty far away from where that box is. The box representing kind of the middle 50% of the data. So obviously there's going to be points that fall in between. So there are data points that are somewhere in here. They're just not plotted. In the whiskers, you just see the max and the min. Okay. So the box plot is a really useful plot just to get a quick sense of how things are distributed, get a quick sense of where the median is. Just from looking at this graph, I can already tell that, for instance, like this median is slightly higher than this one. Um, which so it's and then it's looks like it's slightly lower. This one is slightly lower than this one. So this one looks like it has the highest median, but this one looks like it has the highest maximum and the lowest minimum out of all the groups. So it has quite a bit of spread to it, whereas this one all the way on the left is pretty compact. Even its max and min aren't that far away. It's still pretty compact compared to the other two. So you can get that kind of picture of the data just by looking at the box plot and kind of analyzing the box plot. Okay. So just to recap that, with a box plot, you always have a median, which is going to be a line in the box where that median is. You have a box which has a height determined by the 75th percentile, 25th percentile. And then you have your max and your min whiskers that go from the top and the bottom. And you interpret the height of this box as kind of a way to determine how spread out the data is around that median. If it's pretty compact, then that means that most of the data is centered around the median value. But if it's pretty wide, or I should say the box is pretty tall, that means the data is spread out pretty decently away from the median. It's not all compact, just values that are right around the median. It's more spread out than that. Okay. So scrolling down, we're going to take a look at some more graphs. The next type of graph we're going to take a look at briefly is the spider chart, also known as the radar chart. And this is a way to display multivariable data. So think multiple columns, for instance, with three or more variables represented kind of starting from the center and going out in different directions, kind of like a hexagon or kind of like a spider web almost. So I'll show you what the graph looks like. It kind of looks like this, where you can have different points that represent the value of different categories. And you can see that they're kind of connected here in this like spider web type of graph. So this would be like category A has a value of 2, category B has a value of 8, category C has a value of looks like 5, and then all the way over here, category D looks like it has a value close to 10. Okay, so you can kind of see that's what the graph looks like. Any use case for this one? Yeah, it's when you have when you want to compare categories, like categorical values. So let's say we had like different average ages or average like prices per zip code or per demographic group or something. We could kind of do a comparison of those groups on a spider graph like this. So if you have a value, you want to compare the groups, you can actually do that in many different graphs, right? You could do a bar graph. That would be another way to do comparison. You can do so the same kind of thing you would do with the bar graph, you can kind of do in this spider graph. Okay. Now this spider graph is a little more complicated to build, mainly because it uses basically a special type of plot, which is we're going to see in a moment, called the polar plot, which this thing plots. So this plots polar angles and radius values. So it makes now the reason to do that is to make the web. It basically makes those circles by passing in different angles and different radius values. It generates these like concentric circles that look like a spider web. So plt.polar kind of builds that spider web, and this fills in this puts in kind of labels at the different points that are spaced out at different angle values. So this theta grids builds out the lines from the center that go out to the edges, and then puts a label on each one of those lines. So the theta grids is what builds out this line so it's the purpose of it is to put a line at different angles. So all of these angles here, we have a line that's goes from the center out to the edge of the circle, and we label that with a different with each one of these categories. Okay, so that's what the theta grids does. So the data in this case is just angles between 0 and 360 degrees, which is 2 pi radians. Do we need to know that? Not necessarily, but we build out just evenly spaced angles based on the number of categories that we have. So that would be pretty standard stuff there. And so this is not that special. This is a pretty standard setup for just having n number of categories, however many there are, evenly spaced out in this circle web. And we do the theta grids to create those lines from the center out to the edge. The thing that produces our points is this data. So we pass in the angles, we pass in our data. The angles makes the circle. The data makes these points that are plotted at different values on the circles, and those are generated from random integers. So we pick a number between 1 and 10 for basically one for each category, and we just plot those. So if you run this multiple times, you may get different values because this is randomly generating an integer. So random. So we plot these here on this graph. And the thing is we mark each one of them with a circle. That's could be changed. So you could use an asterisk. You could use I think you can use a square. But like circle is just a standard point. I think that's the default. Okay. So that's the radar graph. Again, would you use this one maybe in the same situations you would use a bar graph when you have different categories and they have a single value that you want to compare each category against? It may make sense to use this graph. I think you can get away with using multiple kinds of graphs, maybe even like a pie chart, or even like a bar graph to have similar information. But this one is available. The only thing we would really have to change to this is just our data. Most of this other stuff is going to stay the same, like the number of the angles would likely stay the same for each graph. Just you want evenly spaced angles between 0 to 2 pi, which is 360 degrees. Okay. I wanted to show us the area plot. So this is going to be a plot that will allow us to graph the area between two lines, which can help us with representing like cumulative sums or something, or just filling in the area between two plots, if we really want to like call out that region between two graphs. So the way we would do that is we would use this plt dot fill between. So just which is what the name suggests, right? The name of it really suggests fill between. And then what you notice is we're actually supplying two collections of y-axis values. And there's really no reason it has to be two. We could actually do more than two, but in this situation, we are going to draw two graphs and kind of fill in the area between those two. So imagine building a graph where you had one line here and then another line here, we would fill in this area between them like this. So, uh, and all we're doing here is generating one collection of data that's equal to X, and then another collection of data that's the square, the squared exponent, right, of whatever X is. And then we plot those and fill between those two graphs. So one other thing to notice is we're still following our usual Matplotlib setup, right? Where we do a PLT dot something, and then we come back and do PLT X label, Y label, title, PLT legend, PLT show. All of that still is the same. It's just we're doing different kinds of graphs here in all of our examples. Okay. So you can even see that here, PLT legend, PLT show, all that's still the same. Here's where we're filling in that area. So you can see that one of these graphs is just X, which is this guy. This guy X is here, and then X squared is this guy, and we're filling in all that area in between. Okay. Pretty straightforward. The area between them is the fill between. So if you ever need to use that, which may be useful to highlight like a region between two graphs. Yeah, it's because Matplotlib expects you to have. I know these are equal, so you're actually right that what we could do is actually just do this. We could do that and that would work, but we do need to have the x-axis data needs to be first. So the x-axis data is this linearly 100 points between 0 and 5. So we have 100 points between 0 and 5 for the x-axis. So we don't need to put x twice. We're putting two different graphs. We're putting this line and saying let's fill the data, let's fill in the blanks between these two. So that's why it's called fill between, is you put an X and then you put two Y graphs and you're filling the region between the two. The first X is declaring what is the X-axis. These define coordinates, right? So this defines a pair of coordinates, X, Y, 1, that we can plot on the graph like somewhere, right? X, Y, 1. And then these define alternative coordinates, X, Y, 2, which we can plot on the graph somewhere. Yeah, the X is common to both Y1 and Y2. That's right. So they share the same X-axis, which they should. They share the same X-axis. Yeah, so if they're sharing that, and notice that like by the way, most of the Matplotlib examples have X first. If you go back to our bar graph, for example, the x-axis is the categories, y-axis are values, and that creates these different bars here. Same thing with the scatter. Our x data goes first, our y data goes second because we're plotting coordinates. Same thing with the regular plot. Our x data goes first, our y data goes second. That plots all the coordinates together, which show up here on this graph. We have an x-axis and a y-axis data. So for this fill between, we have a shared x-axis and then two graphs that we're filling the region between them. Okay, so the next kind of graph I'm going to show us is going to be the polar plot, which we've already seen an example of. This one basically plots circles using angles and radius values to make the plot. And so these are angles that are going to be generated between 0 and 360. We're going to generate 100 different angle values. Let me write that down. So we generate 100 different, and they're not random, they're evenly spaced angles between 0 and 360 degrees. So 2 pi is the same as 360. And then what we do is we multiply that whatever angle by 2, and that gives us our radius value. So our radius to the plot is 2 times the angle. Okay, 2 times whatever the angle is. What's the variable value here? What do you mean? The r and the theta? The theta is the angle, the r is the radius, and we need both of those to plot a circle, to plot like a polar coordinate graph. So the reason that's the case is because basically every point on here has like a coordinate of an angle and a radius, a theta and an r, angle and a radius. Now, what does that mean? It means that in order to plot a point on the circle, we first pick an angle. So let's say it's 20 degrees. So that would be right about here. And then the radius tells us like how far along that angle we should be like plotting something. So 2 times that angle would probably be somewhere really short if it's a short angle. So to be 40, be about there. All those parameters are constants and yes, yeah. So these are the boundaries 0 to 360. Those are the first two arguments, and then this tells you how many points you want to generate. So n points. So we want to generate 100 evenly spaced points between 0 and 2 pi. Yeah, those are constants. So how do you use your categories? So you for this graph, you really wouldn't be plotting categories. This graph would only be used if you're dealing with like angular data. You would plot that. So this is a very special type of graph that's mainly only used for angular. Like if you had data that represented angles in different magnitudes, like radii, then you can use a polar plot. Okay. So it's it's not really categorical. It's a bit special. That's a really good question though. The graphs that are categorical are like bar graph, the earlier one that we saw with the spider. This is just a pure polar graph, in which case we don't have any categories. We would just have angles and magnitudes, which are the radius. It's just a value. That's a good question, JD, but it's just a value. So the radius would be measured in length, as you suggest, like centimeters or meters. So what this is signaling is in order to generate the radius, we just take whatever the theta is and multiply it by 2. Whatever that value is, we just multiply it by 2. The units should be the units should be in the length measurement. Yeah. Yeah, we just multiply it by 2. It's just the value. Yep. So this graph looks like this. Now, this is a very interesting graph. This is kind of a spiral, but the if you study the angles of this and their radii value, it kind of makes sense. Basically, the angles go from 0 to 360. So we start at the center, which is at 0 degrees, and we do plot values all the way around back to 360. That makes sense because all of our angles go from 0 to 360. And the radii are just different values. Every time the angle changes, we double that to get a magnitude. So when the angle is pointing this way, we double that and we get something over here. When the angle's pointing this way, we double that, get something over here, and it just keeps kind of spiraling because it gets bigger and bigger and bigger and bigger as the angle gets wider and wider and wider. So this graph kind of looks like this. Looks kind of strange, but if you actually think about the fact that it's generated by doubling the angle every single angle, it kind of makes sense. All right. So again, when would you use a graph like this? It's if for some reason you have angular data that you want to plot, that you need to plot on a circle, and you have things like angles and radii type of values. The radii can kind of represent a magnitude of some sort. We could plot that in polar coordinates, which is what this is, a polar graph. So if you have angles, you can use them in a polar graph and you can kind of visualize what your angles and magnitudes look like. Okay, so I have one more kind of special graph for you guys, which is going to be the tree map. This is actually something we're going to see later on, so I won't spend too much time on it at this moment because we're gonna do one of these much later when we get into doing clustering and those kind of things, where we'll see some hierarchical data structures. But a tree map is a way to kind of visualize a hierarchy of things in a tree, kind of structure with branches and leaves. And the thing that we have to use here to help us do that is this Squarify package, which you can install with this command. So if you uncomment this and run the pip install Squarify, you should be able to import this after you run that. And then we have a little bit of helper code here to essentially flatten this hierarchy so we can use it in the Squarify function. And so we do a basically a Squarify dot plot to in order to generate the tree map. Something I wanted to point out about this example, I don't want to go too much into detail on this. I'm basically going to skip this one in favor of doing other graphs because I think we'll come back to this and do it later. But it does have an important concept here, which we're going to get to in a little bit, which is this concept right here of subplots. So we haven't covered that yet. So plt.subplots generates a matrix of figures that we can plot against. So what do I mean by matrix? Essentially, when you do a subplot, what you're doing is giving yourself the ability to create a grid of plots. So you can take a grid and divide it into three different, you can actually define your dimensions, basically your shape, to say maybe I want a grid that looks like that. Maybe I want a subplot grid that looks like this. And I want to have a plot here. I want to have a plot here. I want to have a plot here, and I want to have a pie graph here, whatever you end up doing. But you can build different plots on different members of this grid by using subplots. So all you have to do is pass in the shape to say like, okay, I want a 1 by 3, which would be 1 row and 3 columns of graphs. So that would be this. So graph one, or I should say graph zero, graph one, graph two. And then in this situation over here, this shape is 2 by 2, 2 rows, 2 columns, and we can access basically like what we would do with a NumPy array. We can access data from the different or sorry, access plots from the different parts of this grid that we can then plot over. So for example, we could access this guy here. Let me draw it in a different color. This guy here is going to be available for us in grid position row 0, column 0. This guy would be in row 0, column 1. This guy would be in row 1, column 0. This guy would be available in row 1, column 1. Okay, and so the way we access those is through this ax object here. Through this ax object here, we can actually access. So let me show you an example. So what we could do is we can access the ax object by doing something like 0, 0. And then we could do, so think of this like, then we can do a plot against it like that. So we could draw a special plot there. We could do a bar graph there. We could do a scatter plot there, right? We can do all of those plotting functions that we want against those members of the grid, which will place a graph in that, in that section of the grid. Yeah, what's fig? So fig is a reference to the overall figure. So let me go back to the grid example. So in the grid, this is the subplot, which has like a 2 by 2. Fig is the reference to the whole thing. So it's the reference to the whole thing. So we can do like different manipulations like fig.save, fig.show. So those alter the entire figure together, not just like members of the grid. Okay. So we will do some examples with subplots. Yeah, exactly. Fig is the whole thing, acts as the individual sections. We'll do some examples with subplots coming up. So we'll see it again, but just pointing that out because it's the first time we're seeing it is plt.subplots creates the grid and it always returns this tuple, which is fig, comma, ax. Axe gives you the access to those grid members so you can do your plotting, and Fig gives you access to the whole object so you can like save it or show it or change the size of it, those kind of things. But yeah, so Axe is the one that you would use to manipulate individual graphs, kind of like this. You access the grid position, then you do like a graph function. Why 6 6? That's arbitrary. It doesn't really matter. It's yeah, so 6 6 is nothing special. It could be 7 7, 8 8, 10, 10 8. It could be whatever we want it to be. Nothing that special about 6 6. It's just the figure size. So yeah, nothing that special about it. Okay. So what I wanted to do in plot, yeah. So this uses the Squarify package. So we're using the plot function from the Squarify package. Essentially, what we're doing is we are giving it a couple of parameters. One is how big the relative boxes should be. And that's going to come from our flattened data. So when we flatten this hierarchy, that's going to give us like these numbers here. So they're like the relative size of the leaves in the tree. They come from those values. So item two is this number here that we are going to use to give the relative sizes of the boxes that we draw. The labels we supply from these guys here. So like leaf one, leaf three, leaf two, leaf four, also combined with branch one, branch two. So if we go, so basically this tree kind of looks like we have a root, then we have branch one, branch two. We have down in branch one, we have leaf one and then leaf two. So then we have leaf one, leaf two, and or leaf three, leaf four. So this has a value of 20, this has a value of 30, this has a value of 25, this has a value of 15. So essentially, we're plotting this kind of picture, but we're making it into these squares that are going to be different sizes. So we're making it in these squares that are going to be relatively different sizes. So you can see which one is the biggest. It looks like it's going to be leaf two inside of branch one is the biggest square, right? And then looks like leaf three in branch two is the second biggest, which it is. Okay, so these just provide these. So these gives us the relative sizes of the boxes, which are going to be based off of the data. These gives us the labels that go inside of the box, which come from these strings here, which branch we are in and what leaf we are in. And then this just gives us like a shading parameter. So how dark should we make the text? That's the alpha. This is an important parameter because it represents the subplot. We basically to create this square grid, we pass it our subplot and have it overlay the plot on top of the subplot. So you have to pass it your subplot axes in order to in order for Squarify to build the plot on top of the subplot. Yes, yeah, Roberto, it is. Yep. So it's something that gets installed separately. Yeah, it's its own library here. It's its own library. So I realize we haven't covered subplots extensively. We'll come back and do examples with that. We'll come back and do that. And we'll also, by the way, later on, we'll do examples of these tree maps that are going to be done in a different way than this. So if all of these things didn't make sense to you, no worries. We'll come back and cover it a little bit differently later on. But particularly the subplots, we'll see some more examples of as we go along. The thing I want us to take away from the subplots, though, is this picture of generating a grid that we have access to make different plots on different portions of this grid, right? I want us to think about that of subplots giving us a matrix of plots that we can then build individual plots on as we need to. Okay. All right, so one more. Here is the pie graph. So this is going to be one that's probably pretty familiar to you, and luckily it does exist inside of Matplotlib. So if we have different values that represent a percentage, so the assumption here, we assume these represent a percentage. So we have 30, 40, and 30%. And those 30% belongs to category A, 40% to category B, 30% to category C. If we have data that looks like this, we can do plt.py, PIE, and we just pass in our percentages inside of a list or a NumPy array, pass that in. We pass in our labels, which are category strings. We can have this parameter is some formatting of the percentage. So here we format it with 1 decimal point, but you could do 2 decimal points. You could do as many as you need. If, for example, your data had a bunch of percentages that were a bunch of floating point numbers that had a lot of decimals. So this will do some rounding and some formatting. So this is a format that's, whole number and then one floating point decimal. That's what the F represents, floating point decimal. So one of those. The other thing is just the orientation. So you can change the like starting angle. So it again, it's just for aesthetics, you can change like how this graph is rotated. So essentially like if you want this to be category A, that's more like on bottom left, you can rotate it by changing this angle to be like 0 degrees, 180 degrees. Different, you can play around with the different degree measurements and it will just rotate this pie graph a bit. But pretty simple. plt.py, pass in your percentages, pass in your labels, and you get a graph that looks like this. You see the 1 decimal formatting there, which can be nice to kind of format those floats in a certain number of decimals. You can see the labels get put right inside where their different pieces of the pie are. So yeah, this can be a really useful graph for categorical data, right? You guys have probably seen pie graphs before, but luckily we can do them with the code. plt.py, usual setup here where we have plt.py as our plotting function, and then we have some edits to the format with adding a title, and then we have our plt.show to display it. The color would be something inside of pi, so you can change the colors. See how the colors is an argument here. You can change the colors to be, you can have like a color per category. So you can have like a colors array inside of here. So you could have, I think you could have like a red. Does that make sense? Like you can put them inside of here, blue. I think you can do that. So you can pass in your colors. Yeah, so it's using default colors. Yep. If we don't mention it, it's using defaults. Yep. Default colors. Yep. Okay. Hopefully pretty straightforward. Again, plt.py. Then we have our PLT title. We have our PLT show. These are pretty standard. But the thing that's a little bit different is our graph type. And different graph types might require different parameters inside of these functions, as you guys have kind of picked up on. So that's good. Okay. All right. So what we're going to do is take a look at how we can do some plotting for 3D. But before we do that, we'll go ahead and take a short break. So take a 5-minute break. We'll come back. We'll do some Matplotlib for 3D, and then we'll move over to our other plotting libraries, which I think you guys will really like. The aesthetics are much nicer than Matplotlib in Seaborn, so we'll move over to that. But we're going to wrap up Matplotlib by taking a look at some of the basic 3D functionality. All the plots that we've done have been 2D. It does support 3D, and there may be occasions where we need to build 3D plots. Okay, so what I want to do is get into the 3D plotting next. So in order to work with this, we will be working with an example with some data that you guys should have as part of your data set. So it's this Adani ports.csv file, which tracks some prices at I think of some products sold in a port and like from different dates across like a couple years or something like that. So if you're working in Colab, this is a situation where you have to do the thing we've talked about before, where you have to upload the data. So you want to go to the files and then upload that file. And the file that you guys need, I can paste it inside of here, but it should be part of your data sets. Let me grab it for you. But essentially, if you're working in Colab, you want to download that and then do the upload here when you go into files and then you go and do this upload button here, which launches the uploader window. And you just upload that file. And then what you want to do is then copy that path and then just replace that path here in this code. So if you're uploading it into Colab, it will always be this. It'll be content slash the file name. Okay. So, and that's if you're running in Colab. If you're running on your own machine, you could just change this path to wherever you have that file. That should work too, if you're running on your own machine. Okay. And then, so assuming we can load that into a Pandas data frame. By the way, one of the things that we have not seen before is this parse dates set to true. So what this will do will automatically load in the dates as datetime objects. We haven't seen that before, but that's a convenience function of Pandas is that if we have any date string columns that Pandas identifies, it will automatically convert to date time objects. It will automatically convert that to a datetime object. So if you set this parse dates to true, when you load in a data frame, it will automatically convert any date string it comes across into a datetime object, which is pretty convenient. Otherwise, it's not that hard to just do the pd.to datetime. We've seen that before. It wouldn't be that, it would just be one extra line of code we have to run to convert those dates. But I put this in here, print df.head. I put this code in here right after we load it so that we can see a little bit of what the data looks like. So I wanted to go ahead and take a look at that. It kind of looks like this. Those dates ended up being parsed into datetime objects here. We have different port symbols for like think of them like stocks essentially. Basically they are stocks. And they have like opening and closing and high, low, and volume. And so they're just different data, different variables about each one of those dates and this stock essentially. Now, one of the things that we do is we're going to create a new column called high minus low, H minus L, by taking the difference between high minus low. And so one thing I want to point out is the proper way to do that would be doing this. I think it's a good habit to get into to use the accessor to access the column rather than doing dot high and dot low. There's technically those would work, but they're not very proper. It confuses readers of the code to think that those are properties of DF, which they're columns of the DF. So the to make sure people reading this know that you're actually accessing a column, usually you want to use the brackets and then put the column in the strings. That's a very clear indicator that, hey, I'm accessing a column from this data frame. So all we have to do is subtract those two columns, which we can do. Remember, every column is a series in Pandas. So one series minus another series, they share the same index because they're coming from the same data frame. That's okay. So this is a series subtraction, which is okay, right? So this will subtract high minus low and create a new column called H minus L. Okay. So nothing that fancy going on there, just subtracting the two. Now, one of the things now we're going to plot this. This is going to be one of the things we're going to plot. Another thing we're going to plot is a 100-day moving average of the closing price. So we're going to plot that. Now, how in the world do we create a 100-day moving average? Well, it's actually really easy in Pandas. It's going to be taking that column, the closing price column, and doing a dot rolling, which dot rolling is an aggregation of the dates to a certain number of rows. So this does rolling, so df column dot rolling, and then we put in rows uh, in rows, groups together last, or I should say previous in rows. So what this is doing is grouping together the previous 100 rows and taking the average of those. And that's how we get a 100-day moving average, because every row is a day. If you take a look at the data, every row is a day. So this is going to take the last 100 of those and do the moving average of those. And the reason it's a moving average is because it's going to do this 100 across the whole column. So it's going to go through the whole column and do 100 at a time and kind of slide that over the column, over the closing price column. And we're going to take an average for each one of those entries. So we get a kind of 100-day rolling average there. And of course, we could do whatever aggregation we wanted on that. So we could do the max, we could do the min, so 100-day minimum, 100-day maximum. We could do 100-day total, any aggregation we wanted, median, right? We could do that. But what we're doing is the average. So we're doing a 100-day average there. Hopefully this code makes sense what it's actually doing. Let me know if there's questions on that. Data type of series should be the same to subtract. Yes. Yeah. As long as it's numerical, it can be like an integer minus a float. That's okay. It'll just be a float result. But yeah, as long as it's numerical is what we care about. Okay. So we have the 100-day rolling average. And what we're going to do is build our 3D plot. Now, in order to build a 3D plot in Matplotlib, what you have to do is a PLT axes and do a 3D projection, a 3D graph. So this sets up a 3D plot. This sets up a 3D figure or a 3D plot. And what we can do, it's sort of like subplot. It sort of is kind of like subplot, because what we then have is an axes object, which we can then generate a plot against with three different variables and for the 3 dimensions. So what we do is we plot three different variables against each other in using the ax object. So notice how we do ax.scatter. So we do this will ensure that this plot ends up on the 3D plot. So ax.scatter, same way in which we do like ax, we access the grid and do dot something to do a subplot. Same thing here, ax.scatter to make sure it shows up on the 3D graph. And we're going to plot three different things. Okay, we're going to plot three different things. We're going to plot the index column, which is just going to be basically the row index. So nothing that special. It's like a generic x-axis. So nothing that interesting. It just is the typical row index. But we're going to plot that against the high minus low, and that is going to also be plotted against the 100-day moving average that we just created, right? The 100 MA that we just created here. So we're going to plot all three of those against each other. And so this truly will be a three-dimensional plot because we're going to have three different things that are going to be plotted in the scatter plot. So typically we only have two. Like we would only have a plt.scatter and we might have these two guys that we scatter against each other. So that may be something worth trying is typically we would just do plt.scatter of two variables. So just writing that generically, right? We would do two variables in a PLT scatter. Here we're doing three variables in an ax.scatter where the ax represents a 3D plot object. Okay. And because we have three variables, we have three axes we can label. So notice how we do some labeling here. We do ax dot set x label, ax dot set y label, and ax dot set z label because we have three variables. So the z is going to be the third variable, 100 MA. The y is always the second variable, which is the h minus l, and then the x is the first variable, which is just the index. So if you plot it, it kind of looks like this, which looks pretty dense. So if you take a look at this, it looks like you see most things as the index, like as the rows increase. By the way, as the rows increase, which is going this way, the row index increases, is the same thing as kind of the date increasing because these things are ordered based on the date. So what's really going on is it looks like it was growing. So the high minus low was growing quite a bit from left to right. It did have some dips. It kind of looks like it had some dips here in certain regions, like here and here, it kind of had a dip. It also looks like there's quite a bit from the early stages of a lot of data up here, this axis over here, I know this got cut off a little bit, is the moving average, right? The 100-day moving average of what the actual closing price was. So it looks like it kind of steadily goes up, and the high minus the low kind of increases in the height. No, that would be fantastic if you could. We are actually going to see an interactive plot with Plotly where we can do something like that coming up in a little bit. So unfortunately, that's one of the downsides of Matplotlib is it's not interactive. So no, we can't rotate it, unfortunately. But the Plotly graph, we will be able to. We will be able to rotate that. Okay. So not too bad. All we have to do again is if we want to do 3D plot, we do plt.axes projection 3D, and then we can plot three different variables on those axes like that. Let's try it one more time. We will plot we will do PLT axes 3D, same exact setup, but this time we will swap out that 100-day moving average and do the index. We will do the high minus low, and this time do the volume to see how the volume kind of changes. And we'll do the labels differently than before, where it's index H minus L, and this time it is volume. And you can see that here we get, some interesting points where this looks like we have some outliers for sure. It looks like we have some outliers here that are way up here in the this is the volume axis. So these are kind of high versus most of the values are kind of low volume, even if they have high minus low. These ones out here suggest that when the high minus low is pretty big, there's some pretty big volume. It's a pretty interesting graph. Most of the data is like pretty dense around here though. Pretty low volume. DF not defined. Did you run uh this first? This is what defines the DF is reading the data. Make sure you run this cell first so you can actually read the data first and then you can do the plotting. Okay, no worries. We're gonna have an interactive version of this coming up with Plotly, so stay tuned for that. But just some good example. By the way, these notebooks provide some good examples for references to go back and see if you ever want to do one of these basic types of plots, they're good references. So you can kind of go back and see like, oh, how do I make a 3D plot? You have a good example here to do that with some data, right? Or how do you make a pie plot? How do you make a scatter plot? You have some good references in the notebooks. Okay, very good. All right, so there's some extra practice for you guys. Maybe what we'll do is next time I can come back and start with walking through this with you guys. But give it a try on your own. I'm gonna write that down. Is that next time, so we can have some extra practice and go through that together. I will start with doing this. Okay, so I'll start by going through this extra practice. But essentially, give it a try on your own. What it is doing some of these plots that we just described in this notebook, but for the housing price data set. So load that into a data frame, build some plots to analyze some relationships here with some different variables. Give that a try. It's a very interesting exercise. And then give that a try when we meet next time. I will go through this together. Okay. All right, let's go to Seaborn then. Let's talk about so that's enough for basic Matplotlib. Let's go to Seaborn, which I think you're gonna really like. It adds some additional plotting and Plotly. So we'll cover those two libraries. Let's go over to there in the 5.02 notebook. So give you guys a moment to pull that one up, and we'll go through Seaborn together, which I think will be really, really interesting. It's going to have a lot of interesting plots in it that are more statistical oriented, but also just look nicer to the eye or more aesthetically interesting and visually appealing, I think. So, do you guys have this notebook, the 5.02 Seaborn? This is the one you want to open up. We'll go through this one. Okay, you do? Okay, perfect. Yeah, take a moment to open that one. We'll go through it. Okay. So let's talk about Seaborn. Seaborn is another plotting library, but it tends to lean towards building statistical plots, which is going to be useful for us working with data to build out plots of interest that we might need when we're analyzing our data and analyzing statistics of them and things like that. Now, this is a library that is built off of Matplotlib, so it's very compatible with Matplotlib. In fact, one of the interesting things about Seaborn is that the basically the things that we were doing before with our formatting will stay the same. We still use plt dot show, plt dot title, plt x label, plt y label. We can still do that formatting even if we're building our graph with Seaborn. The thing that changes is instead of doing plt dot scatter, we would do Seaborn dot scatter, and it might have a slightly different arguments and syntax there. So building the actual graph will require Seaborn, but doing the surrounding matplotlib figure manipulation still remains the same. It still remains using matplotlib. Seaborn is compatible with matplotlib. It's built off of matplotlib. So it makes sense that it's still going to manage the figure via Matplotlib. It's just going to build the graph using the internal Seaborn code to actually generate that graph. And what's nice is Seaborn has a lot of built-in graphs that Matplotlib does not. So it has some really nice graphs that Matplotlib just doesn't have. So that's pretty cool. Seaborn is really awesome too at dealing with data sets with multiple columns, which is most of the time what we're working with, right? When we load in a data frame, Usually it has many columns that are inside of that data frame. Seaborn's really fantastic at working with multiple columns at once. So that's pretty cool. So I want to show us an example to get started with. Not that I expect us to understand this example right away. It's just to show you the power of Seaborn, just to show you kind of what it looks like and how nice it is in terms of how convenient it is, how it can work with multiple columns. The first thing I want you to notice with this code example is how we import Seaborn is we use an industry standard alias, just like we do in Matplotlib, just like we do in NumPy, just like we do Pandas. So if you see in the code SNS, that is the shorthand alias for Seaborn. Okay, so that is very industry standard for people to import Seaborn as SNS. So industry standard to use SNS here. So anytime we need to refer to Seaborn in our code, it will be referred via the SNS alias. Okay, so that's why you see some various SNS functionality. One thing I'll point you to is Seaborn has some data sets that are already loaded into it. So Seaborn has various data sets for practicing plotting. So that's very nice. Like it already has data built into it that is basically can be used out of the box to practice implementing plotting using Seaborn. So in this example, we're going to load this fMRI data set, which is a healthcare MRI data set of the brain. It's got a bunch of different data related to those scans, and we're going to load that data set from Seaborn. Why SNS? It's probably historical reasons. I'm not 100% sure. Probably something to look up. I just know it's always been SNS ever since I've been using it for years and years. It's always been SNS. I get where the S and the N come from. It's SN, Seaborn. It starts with an S and ends with an N. I don't get where the extra S is from. I've never understood that. So I've always been surprised it's not SN, but yeah, there's some historical reason it's SNS. I don't know 100% why. Something I have to look up. Are these data sets fixed? Yeah, so they're in the package. Yes. And they have Seaborn's website lists what kind of data sets they have. So if you were to go to Seaborn's documentation, if you go to their documentation, they'll talk about what data sets they actually have. So yeah, these are built into the package and they're fixed. Inside joke reference to initials of Samuel Norman Seaborn, the TV show West Wing. I haven't seen the show. I've heard of it, but that's funny. It's funny that it's been used kind of as a joke the whole time. That's funny. But I tell you that it's stuck. I mean, everyone uses SNS. Everyone uses SNS for Seaborn. So it's definitely stuck around. I've heard it's a good show. I haven't seen it myself, but heard good things. All right, so we load this data set in here, the fMRI, and then we do our plotting here, SNS rel plot. Now, I'm not going to go through all the details of the rel plot just yet because we're going to go through a bunch of Seaborn examples where we'll work our way up to rel plot. But essentially, what RelPlot will do is build out a line graph. So RelPlot will do a line graph with the ability to group by different columns. And I should say more than just group, the ability to group and shade by different columns. So essentially what we do is we take our data and we do a line graph. So we specify what kind of graph it is by a line graph. We have our X and Y axis specified, which is the time versus signal power. Signal is just a quantity measured from the brain scan, the fMRI scan, so like a frequency signal. But very powerful idea of Seaborn is to make it really user friendly to build the graphs. So it's really user friendly from the perspective of you just pass in the data frame and say, here's the columns I want to use that are going to be my X and Y axis. So that's a really powerful notion in Seaborn that's used all over the place is pass in your data as data equals some data frame and then give your X and Y axis for your data as just a column from that data frame. So it's really user friendly from that perspective. The other thing that's really user friendly is the ability to split out this graph according to another column. So we can essentially group the data and filter it by a specified column. So inside of this data, there's a column called region, which we can basically split the graph into multiple graphs according to this column. So this like filters the data into the data where the region is parietal and the data where the region is frontal. So those are the two, that's a categorical column where it only equals two possible values. And so it splits the graph into multiple graphs, one where the data is equal to this value, one where the data is equal to this other value, frontal. The region is frontal. So that's really cool. That's a really powerful idea is just give it a column and allow the graph to split apart categorically. That's a really nice feature of Seaborn that's done automatically. It's like an automatic filter for you. It's not only that, it's like an automatic subplot for you, right? Where it's generating a subplot based on that column. And we could take it a step further, like more than that, you can actually then make different plots according to another column, such as you can have a hue filter, which is shading. Essentially, you shade the graph one color for when the event is a stem event and when the event is a queue event. Now, this is another categorical column. So some of the data falls into an event that is called stem. Another one is an event called queue. It's not important what those mean, but it is just a categorical column. In fact, we could even look at that if we did print fMRI.head and we just looked at some of the values in this data set. So let's load that and make sure we can see what some of the values are. So you can see this is the event column, and so it's going to have two possible values. The region is going to have two possible values, parietal or frontal. The event is going to be stem or queue. And so we build two different lines to represent that. And we can even style that line based on that event. So we can have the stem event be a solid line and the queue event be a very dashed line. So just this idea, this is way more advanced than basic Matplotlib. So just with some basic code here, we get something really powerful, way more than just basic Matplotlib. Okay, way more powerful than Matplotlib. So again, like I don't expect us to know all of this just yet. We're going to study some examples of Seaborn and we will get there. But just showing you the convenience, just showing the possibility of what Seaborn can provide. It also just looks nicer, right? The graph just looks pretty nice. It looks pretty clean. It looks just aesthetically nicer in Seaborn. That's another feature of it is they try to build on top of Matplotlib where Matplotlib is very basic. Seaborn is a little bit fancier, a little bit nicer. It's more powerful. It can do more. It came after Matplotlib and tried to have some enhancements on some typical use cases, and this rel plot is one of them. All right. Can you provide your own data set? Sure, you could. This is just a data frame. So as long as you have a data frame, you can pass in the data frame and then you put in your own X and Y axis. And maybe these, you can have your own column to split according to a subplot by. If you have a categorical feature, this will do that split into multiple graphs. So yeah, you can provide your own data for sure. And we'll do that. And I think we have a couple examples where we provide our own data frame. Like we load it in from a CSV, kind of like what we did in the 3D example. Okay. By the way, one of the big takeaways of this is Yeah, so it's a custom color setting. You can pass in the colors here inside if you give it a palette. So see how when I hover over this, you see how it has a palette argument? That is the color. Yeah, it's the color palette. So it uses a default one, but you can change that to like grayscale. You could change it to like there's different keywords there that represent the colors that are used. Yeah. The other thing you can do, by the way, and you see it right here, is you can set an overall theme. So you can set a theme for how you want the any color in this notebook to be represented. So in this, it's going to use the by default, this is going to use the default settings are the deep um, color palette. But you can use other color palettes. Definitely encourage you to research other palettes. And so you can pass in the palette at this level, which will make every other graph in the rest of the notebook use that palette. So you can pass in a palette here and you can change what that is. But right now it's just using the default. Yep. Okay. By the way, one big takeaway from this is that again, I want us to pay attention to the pattern of how Seaborn kind of functions here. This is going to be true for any Seaborn plot. It works the same way, where essentially we give our data frame as a data argument. So let me actually write that down in the comments. So all Seaborn graphs work by passing in a data frame, essentially a data frame argument, and then use column strings for X, Y axes. Okay, so so literally these are going to be from the data frame itself as column references. So this would signal to Seaborn, hey, there should exist a column called time point within this data frame. We know there is. We see the head of it that does exist. And so it's going to connect those two and essentially use this column from this data frame as the x-axis. It's going to use this column from the data frame as the y-axis. So there better be a column called signal. We know there is. We see it here. There better be a column called region, which we know there is. There better be a column called event, which we know there is. Okay. So that's a pretty typical pattern of Seaborn we're going to see over and over and over again. You basically pass in your data frame and then give it these columns as the x and y and anything else. Okay. Let's do a basic example doing a scatter plot. So a scatter plot is one of the types of plots that we would be interested in building generally, and we saw an example of that with plt.scatter. So now we're going to do an example with the tips data set. So if you take a look at this data set, we can take a look at it. It has data that looks like this. So it has a total bill, it has a tip, it has the person who left the tip. I think this is at like a coffee shop or a diner, something like that. And what time they were there, what day of the week they were there, what size party did they have. So this is just again, a data set that's from Seaborn, loaded into Seaborn called tips and we're going to make a scatter plot of that. And what I want you to see is the typical pattern. We pass in our data as the data frame, and we reference X and Y as columns from that data frame. We see that again, right? X axis is going to be the total bill for a scatter plot. Y axis is going to be the tip and we're going to do a PLT title and a PLT show. So one thing we see right away is we still use Matplotlib for figure formatting. So we still use Matplotlib for figure formatting. That does not go away. So if we want to add like a customized x-axis label, a customized y-axis label, a title, we want to display the graph in our code, we use plt.show. Those still stay the same. The thing that's different is Seaborn. We're using Seaborn to do our plot. So it's sns.scatterplot, pass in our data, pass in our y-axis string, our x-axis string. You can kind of look and see that the data is like this. One thing that's really cool about Seaborn is it will automatically create X and Y labels for you that mimic the column names. Okay, so this will be the X label and this will be the Y label for the axes. Now that's really convenient. Like if we wanted to customize it, we could. We could do plt.x label, plt.y label, and we could customize it. We certainly can overwrite that. But Seaborn by default will give us X and Y axis labels that match those column names. You can see here that's what it does. Total bill and tip. Um, do we think there's a correlation here between total bill and tip just looking at this? Do we think there's a relationship there? Does it look like there's a relationship if we look at this scatter plot between the total bill and the tip? Is there usually a relationship like just in the real life? Like we would expect that, wouldn't we? There to be some type of relationship there where it's basically just a percentage. It's more dense in the lower left corner. Yeah, that's true. That's definitely true. Mainly, what that would tell me is most of the bills are in this range. Most of the bills are pretty small. I think this is like a coffee shop or something where the total values aren't that big. There's some big ones, like there are some total bills that reach the like 40s and 30s and even one out here like all the way at 50. So there are some of those, but they're very rare. You're right, it's way more dense in here, meaning most of the data is in that range. But it looks like there is a relationship between the tip and the total bill, which we would expect. Like we wouldn't expect this to be kind of random all over the place. We would expect there to be some type of relationship, I think. That would make sense. Okay. Let's take a look at another type of plot. Let's do the line graph, but let's introduce an interesting twist to it, which is to do a line graph. So the equivalent to this, by the way, I'll just call that out, is the equivalent in Matplotlib. Matplotlib is plt.plot. So this is building a line graph. That's the equivalent in Matplotlib. In Seaborn, it's sns.lineplot. We're going to plot each day against the total bill. And this will give us kind of an aggregation of the total bill per day, and it automatically will aggregate that and create a line graph of the results where we can see the differences in the total, basically the average total bill per day, because it has to kind of do a grouping per day and generate a value on this graph per day. So it will automatically take like an average. Now, given that it's taking an average, I want you to see the shading that exists. See the blue. Do you guys see the blue and the orange shading that kind of exist around this average? What that means is this is giving us a sense of kind of the spread of the actual values. Like the actual data can go as high as this value, or as low as this value, but the average is right here. So the shading gives you a sense of what the true data is, whereas when we're building a line graph grouped by different days, we're getting an aggregate result, right? We're getting an average. Same thing with the orange. Like this is an average value, but you can see it goes as high as this and as low as this in the actual data. And that's the average. Same with this. This is the average. It goes as high as this, as low as this, at that time, or for that day. Okay. So, and then one of the things that's very interesting about this graph is we also can put in a shading parameter, which is to say, I do want to graph the total bill per day. So I want the day to be on the x-axis, the total bill to be on the y-axis, and the data that we're using is our data frame tips. That all makes sense. This hue parameter is to basically tell the line plot to filter, basically do a filter by this column. So filter by the sex column so that we end up with two different graphs according to whatever the category is there. So in this case, it's going to be male or female. So we end up with two different graphs according to this hue. So hue allows you to generate multiple graphs based on a column that is categorical. So this should be a categorical column that has a limited number of discrete categories to it. And we will basically build a line graph with different colors that represent each one of those categories. That's the hue. So if we didn't do that, it would just be the total data, not filtered into the sex category one way or the other. It would just be the total data, right? If we left out the hue parameter, which we could. So if we left out the hue parameter, let's actually try that. Let's leave out the hue. Let's run it as is. Let's actually leave out the hue parameter and see what that looks like. So if we leave out the hue parameter, this is the total data, right? So all data together without it being filtered and separated. But if we put in that hue parameter, we can then group it according to that category. So here now we're kind of grouping it according to male and female. So it looks like on most days males are outspending females for some reason. It looks like that on this graph. Don't know why, but that's kind of what it looks like, right? And it also looks like the prices go up on the weekends, right? It looks like more generally the total bills are higher on Saturdays and Sundays than they are on Thursdays and Fridays. Fridays they tend to be low, looks like. Okay. Okay, one more graph I want to show you, and then we can take another break. I want to show you the histogram. This is an incredibly important graph, which gives us basically the distribution of the data for a particular column. So, for instance, we can take that total bill and do the hist plot, which will the hist plot is the equivalent to this is the equivalent to histogram essentially for Matplotlib. So hist plot builds the histogram. Now, these arguments are optional, so we don't need to do these arguments technically, but the main thing you're passing in is a column of data. So you're passing in a single column of data here, mainly because we don't need to pass in an X and Y axis, so we don't need a full data frame. We're only using one array of data basically. So in this case, one column, the total bill. These are optional. The bins specify how many buckets we want to create to generate our histogram. So the bins are how many buckets we want to count our data in. So in this case, we're going to build 20 bins, and hopefully everyone knows how a histogram works. If not, I'll explain it. To build a histogram, what you do is you create your bins and then you basically sort your data into the bins and count the number of values that end up in each bin, right? So the purpose of that is to get a sense of how the data is distributed. So who has the most, which bucket or which bin ends up with the most values. And so these bars represent the frequencies or the counts of how many values from our data ended up in that bucket in that range. So you can specify how many buckets you want to build, and what it will do is it will take your range of your values and divide it into 20 different buckets, evenly spaced, and you can do that. You can actually leave this blank, and Seaborn will have an algorithm to determine what the optimal buckets should be based on what the data is. So it will analyze this data and come up with the optimal bucket ranges for you if you leave this out. So you can leave that out and it will come up with the buckets itself. And that's oftentimes that's actually good enough. The algorithm that they use is pretty good. It comes up with pretty good buckets. We normally actually would prefer to just leave it out and let Seaborn figure out the buckets. It's usually a good idea. So this is an optional param. We can leave it blank and it will just use the default. It will figure out how many there should be. Now, the KDE param is an interesting one. KDE is short for kernel density estimate. And what that means is it will try to fit a graph, it will try to estimate a graph that fits best around these buckets. So see how it builds a line that goes up and kind of gives us a smooth curve around our frequencies. That's what the KDE, so the KDE is this line. Kernel density estimate is this line that's built around to give us like basically a smooth picture of what that distribution kind of looks like. It's estimating what that kind of looks like based on the frequencies. So that's optional. You can turn it to false if you want, so we can see what it looks like without it. Um, Without it, it just looks like this. But I think it's a good idea generally to turn that on so that we can get that smooth kind of line. It gives you a nice visual of kind of what it represents. Okay. So the most important thing is the interpretation of this histogram. And the interpretation of this is that most values fall in these couple of buckets here. So what that tells me is most data is distributed around somewhere between 10 to 20. So most bills fall between 10 to 20. We knew that from the scatter plot, but here it is again in the histogram. Most bills are there. There's very few bills out here to the right. So the distribution kind of tails off to the right. There's not a lot of bills this way. There's not a lot of bills that are really small either. Not a lot there. Most of it is packed into this range. Most of it's packed into this range between 10 to 30. Essentially, the way you interpret this is that it would be very low probability to see a bill that is less than 10 or more than 30. Do we agree on that based on this picture? Like very low probability to see something out here, low probability to see something out here. That's kind of how you interpret this. So that's an incredibly important idea of how you interpret your data is based on frequencies and observations, right? And this histogram can give you a nice visual of those observations to tell you where the most common value is. We know the median is somewhere in here anyway, as we did the box plot. Sorry, we did the scatter plot and saw the most data is packed in that range. So the median is likely somewhere in there. Let me answer some of these questions. Looks like we were filtering the data here. Why can't we identify the same values above on the scatter plot? Because we can't pinpoint exact points. It's not interactive. But we could, so in the scatter plot, we could do the hue argument, and I encourage you to try that. So we could do a hue argument here. And color it according to that. So does that make sense? We could do that. You see how it changes to the points are colored according to that category? Yeah, you can do that. It's just not interactive, unfortunately. Like I can't zoom in on one of these points and tell you exactly what it is. We will be able to do that with Plotly, which we'll have examples of coming up at the end of this notebook. Can I explain again bins and buckets? How does it relate? Yeah, so sure, I can do that. Do we agree that the total bill takes on a bunch of different values. We can see here the total bill is a bunch of different floating point values. Let's start there, right? The total bill is a bunch of floating point values. Essentially, what we're going to do to create the histogram is take the number, take the range that it could be. So zero, let's say zero up to some maximum, max bill, let's say. Okay, we're going to take this range of possible values that total bill could be. Let me pause there. Does that make sense what I'm saying here? I haven't drawn any buckets yet, but let's just examine this range. Zero to the maximum bill. Let's examine this range. What we're saying is let's build some buckets here that represent different sections where the bill could fall into. These are the buckets. So like $0 to $5 to $10, $10 to $15, $15 to $20, $20 to $25, $25 to $30, $30 to $35, and on and on and on. There might be more in there. Okay, so we're going to generate some buckets here. Now, the reason to do that is we are now going to take our total bill and categorize them into belonging to these different buckets. And we're actually going to count how many we have in these different buckets. So a total bill of 16.99 falls inside of this bucket. So add a +1. So this falls inside of this bucket here. So we count 1 for that bucket, right? Then we go to the next row. 10.34, where does that fall into? Falls into this bucket. So add a +1. 21.01, where does that fall? Falls into this bucket. Add a +1, right? 23.68, where does that fall into? Falls into this bucket. So now we do a +2. This count is now 2. Does that make sense what I'm doing there? In terms of the buckets and counting where those values fall inside of those buckets? Does that make sense? And then, okay, perfect. And then do you see how that translates into the graph? Because if I go down to the graph, it's now see how the y-axis is the counts. See how those are now, we're plotting that across these buckets. So from 0 to 5, 10, 15, up to 20. Do we see, and then we build out a bar graph to represent the counts. So what this would tell me is that the most frequent bucket is this one here. This has the most values, which is somewhere around, the count ended up being like 45 or something, right? So 45 values fell into this bucket. It's the most frequent. So it tells us how our data is distributed. That's a really important idea, and we'll see that going forward. Okay, so SNS hist plot. Very powerful plot for building a histogram. SNS hist plot. Okay, so what we can do is we can take a little bit of a longer break. We can take a 10-minute break now so we've been going for a while. Let's take a 10-minute break. When we come back, we'll continue with some more Seaborn and then work our way into Plotly. So we'll talk about Plotly eventually, which will be our interactive plotting module. So that'll be pretty cool. But we have some more interesting Seaborn plots coming up, which I think will be really fascinating. We'll do some examples with those. Okay, so where we left off is we had just covered the histogram. I wanted to next give us another view of the distribution, which is the box plot. We covered that in Matplotlib, but I want you guys to see the box plot from the Seaborn perspective. And so the plot itself is, very simple code. It's just box plot. And now we have our data frame, and we pass in an x axis, which should be categorical. So something to note there is the x-axis should be categorical. So we want to do this per day. And then we want to have our y-axis be something numerical like the total bill. And this is going to give us the box and whisker graph of the total bill per day. So if we look at this graph, it looks a little bit different than the Matplotlib one, and that's because Seaborn makes a couple of enhancements to it. essentially what they do is they still do the box per usual. So the box still will have the median line. You can see that black line inside the box is the median, and the box width still represents the spread around that median. But we also have now some interesting things with the whiskers going on. So what Seaborn does is it actually identifies outliers for you and plots those. It plots those here. You can see those white dots that show up. These are going to be identified as potential outliers. So Seaborn has an algorithm to identify certain data points as outliers. And essentially, this whisker is going to be a specified range above the box. So there's a formula to it. This is essentially the 75th percentile plus. So remember, this is the 75th percentile. And then this goes all the way up to 75th plus 1.5 times the box height. Essentially, that's what they do for going up to there. And then the same thing here is down to here is the same thing. It's instead of plus 1.5, it's 25 percentile minus 1.5 times the box height. So they have a formula to generate those whiskers. So it's a little bit different. They make a statistical optimization. They try to identify outliers rather because the remember the Matplotlib would have built the whisker all the way up to the top. It would have built the whisker all the way up there to signal that's the maximum. Seaborn does it a little differently. It says, no, I actually think that's an outlier. I'm going to mark it as a dot, but I'm going to put the whisker cutoff at this specified formula range here. Okay. It's a little bit different, but pretty interesting. Let's focus on the interpretation of this. Based on this, which day has the highest median? Does it look like? Which day has the highest median? What do you guys think? Sunday. So for a restaurant or like a coffee, like a diner, like a coffee shop, do we think that seems reasonable that the weekend, and by the way, do the two weekend dates seem higher in its median than the weekdays? Do we see that? We can kind of easily tell that from this graph, right? The weekends seem to be higher than the weekdays. That seems to make sense. Which day has the least spread out values around the median? In other words, it's the most compact. So I'm looking for kind of the shortest box height. Thursday, very good. Thursday. So Thursday has the most compact, meaning that most of the data is going to be centered around this median. It has a very short box height versus the other days, which seem to all have very similar box heights, even though the medians of Saturday and Sunday seem to be higher. Okay? That's kind of how you would interpret it. And so, again, the style is a little bit different. You get this optimization here. I think it's very user friendly in terms of passing in your columns as strings, passing in your data frame here. Very user friendly, but it's a bit different, right? Just slightly different in how we are displaying this versus the Matplotlib. So one thing I would encourage you guys to maybe try is the equivalent. This is the equivalent to the plt.box plot of the data, the same kind of data. So you could try putting in this data and making the box plot in Matplotlib and see how that looks different than the SNS box plot. It's going to look different. Okay. All right, let's do a bar graph. So this is going to be the equivalent to plt.bar. We are going to do the SNS bar plot where again we put a categorical column as the X and a total bill or something numerical as the Y. We could have put tips or total bill. We're using our data as the tips data frame. and we are going to build multiple bars per sex. Now, do we need to do that? No, we could see the difference if we just did regular bars. So this would just give us the totals essentially per day, or I should say the average. So that's the thing is it's going to aggregate with the average per day and build that into the bar. So the bar that we're seeing is going to be the average for all the data that is on Thursday, the average for all the data that's on Friday, Saturday, and Sunday, respectively. So, but what we could do is split that out according to the sex category again, so we can see those split out according to that column. Now, you may be wondering, what are those black lines? Those, again, are going to tell us how spread out that data is within that category. So what that means is for Fridays, there is a decent amount of spread in the male total bills on a Friday. So this is kind of spread out a lot more, even though the average is sitting right around 20. This is the mean. But the spread around that mean is the black line. The bigger that is, the more spread out it is around the average. Okay. So this again is going to be the average. Like here, this is the average, but this black line is the spread around the average, kind of like the box height, very similar to the box height that we saw in the box and whisker graph. So pretty cool. Seaborn computes that for you, puts that on the graph for you. You don't have to do anything. That's pretty nice. Pretty nice that it does that for you. Okay. All right. So let's go on to a unique kind of graph called a violin plot, which we did not see in Matplotlib because there is no equivalent to this in Matplotlib. It is a very special graph that is in Seaborn as a very nice like statistical kind of graph. So a violin plot kind of merges the idea of density with a box plot. It kind of merges those two things together so that we get a picture that's kind of like this violin kind of shape. Essentially, in this, we're going to get the same kind of features we do in a box plot. We're going to get the median. Let me draw that. We're going to get the median here as the center marker. We're going to get the box here, which is the same as the 75th percentile, 25th percentile. Now, this here, this width of the violin is really important. The width, so the width of the violin is equivalent to the density of points. So, in other words, there's the wider that violin is, that means there's more points in that region. More points. So, like if it's really, really wide, that means there'd be a lot of points centered around the median if it was a picture like this. But it could be really wide up here. It could be really wide up here, which would signal there's a lot of points up here. This is going to be kind of more dense. There's a lot of points up here. And as we get lower, it could be skinnier, which means there's less points down here at the bottom. Very few points up here because it's very skinny. So the width of this violin gives us a sense of how many points there are, almost like a histogram, almost like the density that we saw in that histogram picture. Okay, so let me show you an example of this. So in order to build the plot, we're going to do sns.violin plot and see how simple it is. Again, we pass in our data, we pass in the total bill, and we're going to do it per day. We're going to graph this data per day, and we'll build the violin plot that way. See the shape here where we get a marker for each day of what the median is. So we get a median, median, a median, and a median. And then we get the box around it. So we have a sense of how spread out it is around the median, which is good to know. But take a look at the violin itself, right? This means that there's very few points up here because this region is very skinny. This region is very skinny, but it gets wider here, meaning there's more points centered around that area of the data. More points in that region. And if you take a look at does it make sense to us that this is really wide here? This is very wide on the Thursday. That's what we saw in the box plot. We saw it was very compact. A lot of points centered around that median. We see that with this density width, right? A lot of points are centered around that middle region, so it's so much wider there than the other graphs. The other graphs are kind of skinny, like the Sunday one, a bit more spread out. Its box is a lot higher. It's more spread out. It's skinnier. There's not as much width there. Hopefully that makes sense why that's the case, right? It's more spread out. It's not as dense in that region as say on the Thursday, way more compact. Look how skinny it gets beyond, like really beyond here, it's pretty skinny, which would signal there's not a lot of data there. Most of it is in this really dense region right here, right? So it's not that spread out as very compact. So think of the violin plot as combining the histogram with how spread out things are, histogram plus box plot, kind of in one. It was a pretty interesting graph. Does that make sense? Or is there any questions on kind of the interpretation of the violin? The thickness is the density, like how many points are in that area, in that total bill range. So we would, by the way, we would use this graph when we want to get a sense of how data is distributed. It's another view of that. Same as if we would use a histogram or just a box plot, we could actually combine those two ideas into the violin plot. So it will be useful from time to time to look at the violin plot to get a sense of how data is kind of distributed, especially per category. It's kind of interesting. Okay, very good. So that is the SNS violin plot. Very simple, very easy to do. And one thing I want to call out is that this is kind of unique to Seaborn. It's not really, it doesn't really have a Matplotlib equivalent. It's kind of unique to Seaborn here. We just, again, one of the enhancements of Seaborn is giving you these statistical oriented graphs that we don't see out of the box in Matplotlib. Okay. Next, I want to get to a really important graph that we will actually use quite a bit, probably as much as a histogram or more than the other ones that we've kind of studied to this point, is going to be the pair plot, which is a super convenient plotting function in Seaborn to basically take all of the numerical columns in a data frame and generate their scatter plots against each other automatically. That's huge. It saves us a lot of time and effort to generate all of those. It will do it for us. It's so useful for quickly eyeballing the relationships between two variables. Okay, we can easily see that. So what this code, the pair plot, all you have to do is pass in a data frame. So that's all you need is just the data frame. Seaborn, so inside of here, you just need the data frame. Okay. So we pass in the whole tips data frame and the hue is optional. Like we could color things and split apart things based on the hue, but we don't really need to. That's optional. So the hue is optional. But essentially what we're going to do is we're going to build a grid. We're going to build a grid where we're going to plot every variable against the other variable in a scatter plot. And then for the diagonal of that grid, it's actually going to be the variable against itself in a histogram. So it's just going to be a histogram of the data rather than a scatter plot against itself. So you can see here in this example, we're going, it basically we take this one data frame and generate this whole grid of plots where we're going to take, for example, in this first row, this plot is total bill. So this guy is total bill on the y-axis, and then the tip on the x-axis. So this is the tip on the x-axis and total bill on the y-axis. and it automatically generates that for us by plotting those against each other in a scatter plot. Now, why is that helpful? It's just a quick way and convenient way to get all of these plotted against each other, all of these variables, so we can quickly identify relationships. If I'm looking at this, I can tell there was a relationship between the tip and the total bill. We kind of already knew that from just doing a regular scatter plot, but we can do this scatter plot in a convenient one line of code for every combo of variables. That's what's so amazing is we get the scatter plot for all combos of numerical variables, or I should say numerical columns. And this is really convenient. This is really convenient, right? It does it for us. Not only that, but it also plots the histogram and the shape of the histogram of that total bill, of the tip, of the size of the party, for example. So the size is the party that was dining in, the party size. So we can get all of those, all of that information in one line of code, SNS pair plot. That's a really convenient function. Okay, so it looks like there's a relationship between total bill and tip. By the way, this graph is going to be essentially the same type of information when we invert it. So this is the same thing, just on the tip is now on the y-axis, total bill on the x-axis, but we get the same kind of same data really, or same relationship. We just see it kind of inverted. It does it automatically. Every variable against each other, against a different variable is going to be a scatter plot by default. It's always going to be a scatter plot. The ones on the diagonal represent the fact that it's not going to make sense to do a scatter plot of a variable against itself. Like I wouldn't do total bill on the y-axis and total bill on the x-axis, right? Like that wouldn't make sense. So the diagonal elements are always going to be histograms. Always. Those diagonal elements are always going to be histograms. So you can see like this one is the tip histogram. This bottom one is the size of the party size histogram. This is the total bill histogram. Okay. Yeah. What do we think about the pair plot? Does it seem pretty convenient? Does it seem pretty useful, pretty convenient? I think it's super powerful, pretty convenient because think about the manual labor we would have to do all these, right? We would have, if we wanted to do this, we'd have to do the Seaborn or Matplotlib. We'd have to go through and do scatter to every combination of these. But this does it for us. That's really big. It saves us a lot of time. So pretty cool. Pretty useful, the pair plot. We will use this quite a bit when we get into our data analysis and data prep for modeling. We're actually doing modeling. We will use pair plot to get a sense of how to get a sense of the relationship between variables. Okay. Let's talk about the heat map. This is going to be another really popular one where we can visualize the correlation of numerical variables in a data set. So here we're getting a sense of the relationship based on a scatter plot, but we can actually compute a numerical value called the correlation, which is using this correlation computation here. And we can pass in that correlation matrix computation into the SNS heat map. This is going to be a very common workflow for us when we get into modeling, because typically we will look at these values and determine if we should get rid of some variables or not because they are highly correlated one way or the other. So the heat map is going to show us bright red spots where there is very strong correlation positively and dark blue spots where there is very strong negative opposite correlation. And either case would be candidates for removing one of those variables because we don't want correlations to be present in our data. They actually really hinder modeling. They make modeling more difficult when there's correlations in there. So this is a very nice way of taking the correlation matrix and really making a nice visual of which variables are correlated to another. Based on these graphs, it looks as if total bill and tips are correlated. We can see that from the relationship. It looks like there's kind of a linear relationship there. So the guess would be there's probably going to be some bright red around total bill and tip. But let's see. Let's see what that value actually is. Maybe it's not as strong as we think. This is going to be a numerical calculation, and we're going to pass that data into this heat map to make those really strong correlations kind of pop out in the visualization. So let's see. We actually do, I'm sorry, we actually do the iris data set, but we can come back and do this one. I'll do this one next as an example. So here we do a different data set where we do the iris flower data set, which is a pretty famous collection of data related to different flower characteristics and then categorizing those into different types of flowers. But we can generate the correlation matrix of that and pass that into the heat map, and we can see which variables are correlated to another. The way you read this is you're taking a look at these values and you're looking for those really bright red sections. Now, on the diagonal, of course you get a 1 because what that represents is a variable correlated to itself, right? And that makes sense. Every variable is correlated to itself 100%. We know that. That's not a surprise. And so that we can ignore those on the diagonal. Those are always going to be 1 on that diagonal. What's more interesting is a number like this. This is a really high correlation and it is pretty red. This is also very red. This is a very high correlation as well. This is the petal length is very correlated to the petal width. So this is related to these flowers, right? The petal width is very correlated to the petal width. So because of this, when we get into modeling, this means we should get rid of one of these variables. We should choose one of them and get rid of it because they're so correlated. If I know one of them, I know the other, right? Because this is a very strong correlation. This is also a very strong correlation. The sepal length and the petal length are very similar. 0.87 correlation, that's very strong. I would get rid of one of those. Those are very strongly correlated, would get rid of one of those and only keep one of them. Even the 0.82, that's very strong as well. Really, anything above zero point 0.7, yeah, so that's a good question. Is there a standard threshold? Anything above 0.75, zero point 0.8, anything in that range, like 0.8 is going to be strong correlation that we should consider getting rid of one of those variables. Okay. So 0.82, that's strong. 0.87, pretty strong. Include equals number. So if you do include equals number, you see the actual value here on the graph. Instead of just having red and blue, you see the number. It actually displays the raw like correlation value, which we usually do want to see. Okay. So let's try this on the total bill. So it should pretty much be the same code. Let's try this on the total bill. So essentially what we want to do is core matrix should be tips.core, tips.core, and we want to do numeric only equals true so that we ensure we're only doing the numerical columns of tips. Okay. And then we want to do an SNS.heatmap of this correlation matrix. So core matrix. And we want to do annotate as true. And the color map is going to be the same one. Cool, warm. And we're going to format the the correlation percentages to 2 floating point decimals, so 0.2f. Okay, let's run that. So it looks like we have some correlation between total bill and tip, but it's a little strong, but not strong enough. A little strong. So we suspected it might be somewhat strong. It kind of is. It's about a medium strength, but it's not enough to where I would consider getting rid of one of them. It's strong, but not overly strong above 80%. So I would keep, if we were modeling, we would keep both. Okay. But you see how easy that code was to build. It's just doing this here. I can paste this in if you guys want to run it yourself. But you can see that first we build a correlation matrix, and then we just plot the heat map from Seaborn. SNS heat map, we pass in that correlation matrix. We make sure we have annotated true, which will ensure the numbers show up here. And then we do, these are just formatting of the numbers and the colors. Okay. I wanted to take a look at this other plot, which is kind of the same idea of the scatter plot. It's a bit more detailed in the sense that if you give the joint plot, so a joint plot is like an enhanced scatter plot. Essentially, what it does is it plots two variables against each other, kind of like in a scatter plot, but it shows you their density, meaning where are the places where those points overlap the most in the data. So we see a lot of it basically gives you a sense of where the most dense regions of the data are between those two variables, kind of like in a scatter plot if we had a lot of points. The joint plot is kind of like a 2D scatter plot histogram kind of merged together. So pretty useful. We're going to use a different data set for this one called the diamonds data, which has different diamond jewels that have different carats and different prices. And we're going to use hexagons to represent the different regions where the data is scattered. So notice that we create it from the joint plot, and we give a title. Now, this is all fancy. We don't actually need to do it this way. We could just do, in fact, I would encourage just doing it this way where we do SNS joint plot like this, and then we do just PLT. I would just do PLT dot title. The reason it's done this way is to purposely put it up here at the top as a super, basically what's called a super title. So it's spaced above this individual plot that's here, but we don't need to do that. I would just use PLT dot title. I think that makes more sense to do than doing that. Okay. And so this goes through the trouble of adjusting it a bit. I don't think that's that big of a deal. I don't think we need to adjust it. I would just do plt.title and just do that as normal. So I would do the joint plot. I would just pass this in here as it is, and I would just do that. I think that makes the most sense. Unfortunately, it gets a little overwritten by this, which is why we do that, but I'm not that concerned with that. So you have to do this is the case where you have to do a little bit of maneuvering with the joint plot to move the title above this secondary plot. But I'm not too worried about the title on this. I mainly want to get the point across of what this graph does. Basically, what it does, you can see here, is it plots like a scatter. So this is kind of like a scatter, but we basically have darker hexagon regions where more points are located. So you can see we actually use hexagons, and what this means is there's a lot more points down here where it's dark and kind of in here where it's dark, then all the way up here where it's pretty light. So this would tell me there's not that many values that are up there in the scatter. Most of the points are down here. So this gives us a sense of the density of the scatter plot. So that's what the joint plot really is getting at, is what is the density? Where are the most points located if we plotted one variable against another in a scatter plot? Where are the most points? You can see that most of the data is below 1 carat and below $2,500. And one thing that's really nice about the joint plot is it also gives you a histogram of both. You can see that most of the prices are down here in this low range. Most of the prices are down here in this low range, which makes sense because this is where the most dark region is. This is where you see most of the points. So that kind of makes sense. And then if you look at the price, most of the prices are kind of most of the prices are the most frequent prices are down here in this low region. There is a little bit more spread out to the price. There are some that are over here this way. So it wouldn't be rare to see prices kind of over here in this region. That's possible. But the issue is with the joint plot is even though some of the prices are over here, we don't see a lot of the carats over there. We see most of the carat data in the lower ranges. Or sorry, we see most of the prices in the lower ranges. So that's why the most dense region is kind of here in this lower corner. Okay. So think of this joint plot as like an enhanced scatter plot to tell you where the most dense regions of the data is. This would tell me most of the data is low carats, low price. That's what that would tell me. Most of it is low price, low carats. There are some examples of higher price, higher carats. Most of it's going to be low price, low carats. The histogram on top is the carats. It's the carats because it's correlated to this x-axis and the price is this axis. Does that make sense? I know it seems like it's a little inverted, but that's the way it is. The histograms are relative to the axis that they're kind of like facing. So this is facing the price axis. So this is the price histogram. And the carat one is at the top is facing the carat axis. So that's the carat histogram. Are still questions on that? Okay. So if we were to build a joint plot of the total bill versus tip, so this was a random, this was the diamonds data set. We go back to the tips data set versus the total bill. We can see this is a really good one to see where most of the data is low, kind of in this like the total bill is between 10 and 20. We kind of already knew that. And the tips are also in this low range as well. So this is showing that most of the region is kind of here, kind of like this. Most of the data is like that. That again, the dark are the really heavily overlapped points. So this would tell me there's a lot of scenarios where the total bill is somewhere between 10 to 15 and the tip is like $2. That's what that would tell me. This is very dark regions right here. Very dark. Okay. I wanted to show you this swarm plot, which is it's basically like doing a scatter plot, but with the x-axis being a categorical variable. So that's all that the swarm plot is, a categorical scatter plot. So think of it like that, where we have basically on the x-axis is going to be some category, and on the y-axis is going to be some numerical value that we're building a scatter plot off of. So what you typically see is kind of like columns of scatter plots where all the points that belong to that filter for that category are going to be scattered amongst that column. So let me show you what that looks like. This is called a swarm plot. And the thing that this is useful for is visualizing the distribution across different days and across different categories like male and female. those kind of things. So here we're loading that flower data set again, and we're going to do the petal length, but against the species. So the x-axis is always going to be categorical instead of a numerical value like we do in a typical scatter plot. So we have a categorical x-axis always for the swarm plot. Okay, categorical x-axis. So we can do SNS swarm plot. We pass in the x, y, our data, and we can build the plot. Um, Here's what it looks like. You can see we have the different species of the flowers. We have Setosa, versicolor, and virginica. And we can see the petal length kind of distributed amongst those various species. So what's really cool about this plot is you get a sense of how the data is distributed, kind of like a box plot, but you see the raw points plotted for each of these different categories. So the Setosa, you can see that most of the values are around 1.5, it looks like. Most of them are there. It's not very spread out. If you go to the Virginica, most of these values are kind of spread out. This would be like a tall box kind of situation, like in a box plot. So think of this like merged, a box plot merged with a scatter, kind of merged together is kind of what this plot resembles. Okay, so we were talking about Seaborn, and one of the comparisons that we will see to it is from this to Matplotlib is the 3D plotting is going to look kind of similar but be a little different. So let's take a look at doing the 3D plot. It's actually going to be somewhat similar in the setup of doing a 3D projection in a subplot, but we are going to build a scatter plot of three different variables against each other. And you can see it's a 3D projection here. We're adding a subplot here, which is kind of what we need to do a 3D graph. So this is necessary in Seaborn to do 3D graph is to build a subplot. Now, the 111 is essentially a three-dimensional graph. It's a 1 by 1 by 1 grid. So it has three axes, essentially, as a three-dimensional graph. So that's what we're doing. And once we do this, we can then put on our 3D graph three different variables that we're going to plot against each other. So let me make that comment is the 111 means we have a shape of 1 by 1 by 1 means we have a shape of 1 by 1 by 1 for the 3D graph. So we have three axes essentially. Okay. So three axes. And what we can do is do axes.scatter, and we can do our three different variables on that. One of the things we're doing is coloring this according to a shade based on the petal width. We don't need to do that, but the C argument will shade the points according to the petal width, according to their petal width. We don't need to do that, but it's optional. This C argument is basically like, okay, go ahead and color things according to this extra variable. So according to the petal width, we're going to color these points. We don't need to do that, but we are. And then we're providing a color scheme of viridis, which is going to be more like a red, more going to be like a green, yellow type of color scheme rather than like a blue, red, orange. So be a just different color scheme there. That's going to be optional. So and then we can set our labels. So this is the same exact setup that we had. It's basically same as in 3D plots for Matplotlib. Same setup as that. And then we could do our plt.show, and it's going to build our 3D graph. So you can see here we have sepal length, sepal width, and then the z-axis, which is the height, is the petal length. You can kind of see how the data is distributed in 3 dimensions in a 3D scatter plot. One of the things that we're going to do is we're going to study Plotly next, which is going to make this much more interactive. Unfortunately, we can't rotate this. We could change the size of it. If we entered a fig size here and we put in a fig size argument, we can make it a little bit bigger, maybe like 15 by 15. Try to make it bigger. This helps a little bit. This makes it bigger. So you can always do that. This is actually probably a little too big. Maybe we can make it 10 by 10. It's a little, maybe that one is a little too big. Yeah, there we go. It's a little bit better. So it's zoomed in a little bit. So if you ever want to change the size, you can put that in here, this fig size argument in the plt.figure. The fig size, we can change that. Okay. And then we plt.show, we can see that. All right, one other type of 3D graph that we have here before we move on to Plotly is a spiral graph. So we can do this is a little bit simpler of a graph, is that we can do, basically we have values between 0 to 10, we do 100 of them, and then we take the cosine and the sine, so we do trigonometric values of those, and then we do a 3D plot, and then we do axes.plot 3D. Now, this is an alternative. So this is an alternative to the above example. So you can create the subplot and do it that way. You can also do plot 3D, which is a simple way to plot to plot like a line graph. So this plots a line graph in 3 dimensions. Okay, so we have our x values, which are going to be the cosines, we have our sines, and we have our points 0 to 10. We'll plot those. And you can see when we plot those, it kind of connects all of those points, 0 to 10. And kind of this actually generates a spiral because we're taking sine and cosine, and it just rotates around over and over and over. It's pretty cool graph. But the main purpose of this example is just to show you, if you're just doing a simple line graph, you can do plot 3D. You don't have to go to the trouble of setting up a subplot, which we do in this scenario because we're doing a scatter, which is a little bit more advanced of a graph than a basic line graph. So we're scattering 3 variables. It's a little more involved. Okay, and then there's one final example here of doing a 3D surface, which is another type of plot we can do on the PLT axes. We can do a plot surface, which is going to build like basically like a 2-dimensional surface in 3D. So you can kind of see what that looks like here. This is a very interesting graph. Essentially, we generate the z values by a function of the x and y. So that's why it's a surface. Z is actually a function of the other 2 variables. So we generate the x and the y's. We generate the z's by using those in a function, and then we can go ahead and plot those 3 variables in the plot surface, and it kind of looks like this. So pretty interesting. Pretty interesting. And one of the things is we're setting the style to be a white grid. That's what makes it look like this, with the kind of grid in the background and the color scheme of the blue and the white is this white grid style. All right, so let's move on then to Plotly. So we'll look at one more plotting library. So we looked at Matplotlib, we looked at Seaborn, which has some really useful graphs in it, especially for statistics and looking at the distribution of the data. let's look at Plotly. This is going to be the last plotting library we will look at. What Plotly does really well that the other two do not do is creating a interactive visualization. Plotly is really fantastic for creating graphs that we can actually click into, visualize points, like actually get the values that are on the graph, hover over it and see different values, or like zoom in, zoom out. We get a really interactive graph out of Plotly, which can be very, very useful, especially when you're like sharing a notebook with someone or sharing your code, giving the ability for people to kind of visualize that data along with you in an interactive way. So Plotly is really nice. We If you don't have Plotly, you are likely going to have to install it. So you are going to want to pip install on your own machine, pip install Plotly. This is if you don't have it. It comes built into Colab. So if you're working in Colab or you're working in like the lab environment, Simplilearn, it already has Plotly, so you don't need to do this. But if you don't have it, you may need to run this. Okay. All right. So here we have an industry standard import. So the main package or the main module within Plotly that is used to make interactive plots is the plotly.express module, which gets alias to px. So this is another industry standard alias is doing express to px. Okay, so pretty simple conversion there, plotly.express as px. Now, this also has data built into it. So you can see from px, we're getting some sample data. This comes from Plotly, which is really nice. We can just use that data out of the box and it's a data frame. It kind of is similar to Seaborn. Plotly is built off of Matplotlib in a similar way that Seaborn is. Notice that with the px.scatter, we're going to build an interactive scatter plot. We're going to pass in our data and we have an X and a Y. So we're going to plot our sepal width against our sepal length, and we're going to color things according to their species. And we're going to do a relative size of so the size is the relative point size, which is determined by the variable petal length. So this is very interesting. We can color our points according to the species, but we can generate the size of the point relative to this variable, the petal length. Okay. And one thing that's interesting is this px.scatter returns a figure object, which is kind of like the figures in Matplotlib. In fact, it is a figure from Matplotlib. So we can do fig.show, or which is essentially basically launching the interactive plot. So this basically launches the interactive figure. Basically launches the interactive figure by doing figure.show. Okay. So you can see what it looks like. What's really cool about this is we can hover over points. We can hover over them and see what their exact value is. So do you guys see on my screen when I hover over this green point, it gives me all the data about that point. It says what the species is, which makes sense. Our legend is over here to the right. The green dots are going to be points that have a species of Virginica. We can see what the data is behind this point. The sepal width is 3.8, sepal length is 7.9, petal length is 6.4. We get those, by the way, those data points we get because we're plotting those in our scatter, right? The sepal width and length are X and Y axes. The petal length shows, that's why you see these dots so much bigger than these dots, because their petal lengths are so much smaller. We said to make the size according to the petal length. You can see these setosas have a much smaller petal length generally, even than these versicolors, which have a little bit bigger petal lengths. Okay, so this is pretty cool. You can hover over it. You can zoom in, so you can pick a region of the plot and kind of like zoom in on that region. Do you guys see how I did that? And you see this little interactive menu where I can basically zoom out. I can go to reset, so I can go back to the beginning. Um, for you guys running this in Colab, do you guys see this menu? Do you see this menu of like zoom in, download as a file? Do you guys see this right above the graph to the right? Perfect, perfect. Yeah, I was hoping that would be there. Very nice. And then you guys can try like you can click on a point. You can try zooming in by dragging and dropping like a region. That zooms in on it. And then you can, I think you can double click to reset, or you can go back up and hit the home button here, which will reset your zoom. So if I zoom in on this, I can always go back by double clicking. Just go back to the original view. Pretty cool, right? It's m way more interactive, and it looks pretty clean. Plotly does a good job, I think, with the aesthetic, but pretty cool that we can now kind of hover over points and see them pretty cleanly. So that's always nice. That's pretty cool. All right. Hopefully we see how easy that was. It's just px.scatter. It mimics the Seaborn kind of style, right? Where we're passing in the whole data frame and then doing an X and a Y for those axes, which are just the columns. We could get rid of this color and we could get rid of the size. I want to show you the difference when we do that. So let me just remove that and show you the difference. It's going to be a much more plain graph, but it's going to show us all of the points at least scattered about. It just doesn't have as much interesting detail to it when we remove that stuff, right? So this is without coloring all the points by the species and doing their different relative sizes. You can see the difference. It's still interactive. We can still, we can still zoom in on a region and hover over them and see the different values. So still get that aspect. It's just not as interesting. So let's actually put that back in. See that, and then we get this plot again. Okay, pretty useful. One thing too is it automatically produces a legend for us, which is nice. We don't have to do that. It automatically produces an X and Y label axis, which comes from our columns. So it's kind of like Seaborn in that way, which it produces those for us. So that's pretty nice. Anything you put in this color, that's what's going to generate the legend. So species is the name. That's the column we're using to generate the different colors. That's just going to populate the legend. But we could try to customize that if we wanted to rename it. Okay. Let's do a box plot. Let's see that. Unless were there any questions about the scatter? What do you guys think of Plotly? Any thoughts? Any thoughts on Plotly, the differences? Think it's better? Better. So here's my opinion on it is that I think it's better for certain things. I think the thing that we are going to see is that a package like Seaborn has more types of convenient graphs for the types of problems we're going to solve, like the types of statistical modeling, data modeling that we're going to do. Seaborn is going to have more useful graphs than Plotly will out of the box. So unfortunately, Plotly doesn't have all of those like pair plot or hist plot that we see with Seaborn. So I'm going to say most of the time we're going to be using Seaborn, but if we're doing a basic scatter plot, it probably makes sense to do it in Plotly as well, just for like a single scatter plot or a single box plot. It probably makes sense to try to do it in Plotly because it's so much more interactive. But if we're doing things for convenience and we have to produce a bunch of scatter plots for all of our data, that pair plot is going to be extremely useful from Seaborn, right? Okay, let's do a box plot. So in this code, it is px.box. So of course, Plotly Express is the PX alias, so px.box. And same thing as usual, we pass in a data frame and we have the x-axis is going to be categorical, in this case, the species. Y-axis is going to be numerical, which is the petal length. We have a title, and then we have some labels. So the labels are what get put as the X and Y axis labels. So the species will be down here on the X axis because it's first, and then the petal length will get put as the Y axis because that's second. Again, this is a customization. We don't have to put this because Plotly will infer those from these. It will infer those from that. But if we wanted to have custom labels for the X and Y axis, we can do that. So let me actually make a note of that. So we can have custom X and Y axis labels. We use the labels argument here. We can also have a custom title to the graph, kind of like how we do with plt.title. We can put a title on this Plotly Express graph by doing the title argument inside of here. Okay. So if we run this, we get the interactive box plot. Now, what's interesting is this produces the box plot that we are accustomed to with the whiskers and the box. Now, what's really cool is when you hover over this, it gives you a bunch of data about the box. So it tells you exactly what the median is. So in the versicolor species, the median is 4.35. It tells you what the Q1 and Q3 values are, which are those upper and lower box heights. So the Q3 is the 75th percentile, that's 4.6. The Q1 is the 25th percentile, which is 4. That's the top and bottom of the box. It gives you the minimum, it gives you the maximum, it gives you the upper fence and lower fence, which is those are your essentially your whiskers, which are the basically the box plus a certain 1.5 times the box height. It's that formula again, that the same formula that kind of Seaborn uses, and it also gives you an outlier. So it tells you that this guy right here, it thinks is an outlier. So it has its own way of computing an outlier. It looks like this one, it thinks that the petal length of 3 is an outlier, mainly because most of the data is going to be right there. Actually, that's the minimum. I'm sorry. It doesn't think that's an outlier. It thinks that's the minimum. This whisker is the formula version of the whisker, so it's not the minimum. So this is the 25th percentile minus 1.5 times the box 1.5 times the box height. Okay. So that comes from that formula. This is the actual minimum, which is below that value. So what's really cool is you can hover over any one of these boxes and see the values. You can see the values of them, which is pretty cool. Let me ask you guys, which is the most compact? Which one do you think has the least amount of spread to it? Which species? Setosa, very good. Yeah, the Setosa, because it's the most compact box. I mean, look how compact it is. The median is 1.5. Look at where Q1 and Q3 are. They're essentially right on top of 1.5, which means it's a very compact box. The maximum is only at 1.9. That's not that far away from the median of 1.5, right? So yeah, it's super compact, not very spread out at all. These other flower species have much more spread to them, even though their boxes aren't that tall, so they are not that spread out away from each other in terms of the data values. Okay, so we could zoom in to a single box, by the way, and get more of a detail on the box height. Um, and then we could reset. reset to that. Okay. Now, I told you about Seaborn having the pair plot. It turns out that Plotly has a very similar idea. I the downside to the Plotly one is you do not get the nice histogram on the diagonal that you do with the Seaborn, which is kind of a miss in my opinion. From the Plotly library, it would have been nice to have that. But you still get somewhat of a pair plot here where you can see in this scenario, they call it a scatter matrix, and we pass in our data frame, and the dimensions is, this is the unfortunate thing, is you have to include all of the variables you want to do the combinations of. So that's the downside too, is you have more of a manual declaration of the variables we want to create the pair plot of. So these are all the guys that we want to do the pair plot of. The advantage of the Seaborn version is we didn't have to do that. We just gave it the data frame and it does that automatically. It just takes all the numerical combinations automatically, which is typically what we want. Here we actually have to specify which ones we want, which can be a disadvantage if we have a lot of them and we have to go through and kind of list all of those out, right? A little bit of a disadvantage there. We are going to color code things according to their species. Do we need to do that? No. So the color here is optional. Color coding is optional. Here we color code according to the species, right? But that is definitely optional. But you can see we get the pair plots, and what's cool about these pair plots though is we do get interactive pair plots. So we can zoom in on any one of them. So we could zoom in on this region if we want to, and take a look at, we could save an image of it. We could select it, auto scale, zoom in. So I zoomed in on that one region, but I'll reset it. So you can see you have some customization there. So if I zoom in, we zoom in a little bit on that region. You can zoom in again. So it's zooming in on all of those graphs. We can reset. Okay, so you get the interactive pair plot there, which is pretty interesting. All right.
And with that, we have come to the end of this course. If you have any doubts or questions, ask them in the comment section below.